Okay, good morning, everyone. Thanks for coming, 8:30. So I'm Erdem Bıyık from University of Southern California, and I'll be co-chairing this session with Harald So from National University of Singapore. And without further ado, I think we can start with the first paper. Harald, do you want to introduce the...
Yep. For the first speaker, we have Sunil, who will be presenting work on action hierarchies using language. Sunil.
Should I get started? Okay.
Go ahead.
All right. Hi, everybody. Yeah, I'm Sunil. So I'll be presenting our work, RTH, action hierarchies using language. So, let it advance. Playing? Okay, cool. So language allows us to understand complex concepts by breaking them down into simpler ones that we already know. This compositionality is key to how we reason and learn. In robotics, recent imitation learning works have used language to represent tasks in multitask data sets. For example, we might ask the robot to pick up a Coke can or pick up a chip bag. These tasks share similar behaviors, and language encourages data sharing across tasks by encoding these similarities. But as multitask data sets grow, the task instructions become semantically diverse, and it becomes harder to share data across tasks. For example, picking up a Coke can and knocking a water bottle over are semantically different tasks, but they share a lot of underlying behaviors like reaching and grasping. Yet the model might learn to treat these as completely separate. So while diverse tasks might not overlap in task language, we observe that they do overlap in the lower level motions that the robot follows. So both pick the Coke can and knock the water ball over involve first moving the arm left and then grasping the object. So we can actually represent these with language motion expressions like move arm left or close gripper, and this is quite easy. And then these language motions can better capture the more fine-grained similarities that exist between all of these tasks. So our insight in this work is to use language motions as an intermediate prediction layer before actions. This enables a hierarchy of action reasoning going from task to motion to action. So language motions enable better data sharing across semantically diverse multitask data sets by capturing these shared fine-grained behaviors. Language motions are also contextual to the task and the scene, which enables us to intervene entirely in natural language to correct behaviors and then learn from these corrections. So we instantiate this action hierarchy with RTH, a single VLM that goes from task to motion to action. So given a task like close the pistachio jar, the VLM first outputs the language motion conditioned on the task and the image. We call this the language motion query. So for example, here it's move arm forward. Then conditioned on this predicted language motion, the task and the image, we output the action, and we call this the action query. So RTH also responds quite naturally to language corrections. So if a human notices an incorrect behavior, they can provide a better language motion. So for example, saying move arm forward here instead of move arm left. We can then feed this correction into the VLM to get an updated robot action. This is the action query portion. And with just a few correction examples, we can even go one step further and actually improve the model. So we can collect a data set of only language motions and then fine-tune just the language query on these examples. And this is pretty sample efficient and very intuitive for the users to do. So we train RTH on a diverse multitask data set that consists of 100K demonstrations that vary in task complexity. And then we choose 8 tasks to evaluate on that are quite challenging. So like, close the pistachio jar or pull the napkin out. So to extract language motions from the data, we avoid the need for top-down human labeling and instead label things bottom-up from proprioception. So this is quite easy. So if we sense the robot is moving left, we can just sense this from proprioception and label it as move arm left. So next we do our evaluation. So we compare RT2, which is a flat model, to several variants of our method. So RTH joint predicts language motion and action in one query, while RTH does 2 separate queries. These are both autoregressive. We find that both RTH and RTH joint outperform RT2 by 15% on average by better capturing some of these fine-grained similarities in the data. So here's RTH putting a bowl under a cereal dispenser using language motions. So you can see that these language motions are quite contextual to the task and the scene. So you can repeat language motions and get different behaviors, basically. So next we improve RTH by intervening on incorrect language motions and then fine-tuning from these corrections. And we compare this to fine-tuning RT2 on VR teleoperated demonstrations using intervention-rated regression. So while RT2 regresses by 12%, we find that RTH intervene actually improves by 23%. So here RTH fails because the arm is too low, so it hits the top of the lid. But in language corrections, we can actually just correct with move arm up at the relevant time online and get a successful policy execution. And then we can train on that. And here you can see the output of the train policy, where it goes high enough to actually clear the object quite easily. So we find that this language is very intuitive and very sample efficient, basically. So yeah, in summary, we presented RTH, which describes language in motion to enable more fine-grained data sharing across tasks and instructions. RTH enables contextual corrections that are entirely in language space, that are quite flexible to intervention. And we find that this intervention can be much more sample efficient than teleoperated corrections. So thanks, and please come check out our paper for more details.
Questions? Okay, while people are waking up, I'll ask a question. So regarding the fine-tuning approach, so something we've tried in the lab is fine-tune these VLMs or large language models, and we find that overfitting is a concern. So how did you face that as well? Did you have techniques to overcome that problem?
Yeah, so I think because this model is trained on such a large prior data set, it's like 100K demonstrations, like I said. I think the overfitting problem also becomes less likely because we co-train actually the model for the intervention part. So we keep all the prior data and then we upweight the intervention data. So I think this helps prevent like some of the overfitting issues. Yeah.
Thanks.
Hi, thank you for the presentation. So the last statement you say is that it's more data efficient than teleoperation. I'm here.
Oh, yeah.
But the correction you give is like go higher. Is this not ambiguous that you will not need more of these commands to actually give the correct corrections that you need?
So yeah, so there's an implicit assumption that the language motion can actually be followed contextually by the action query portion of this, right? So that is one of the assumptions that we hope can be extracted more easily from data. And so yeah, I think it is limited by the kinds of tasks where the action responds appropriately to changes in this like language motion, right? So if you're trying to detail more fine-grained corrections, like pick it up by like I don't know, the corner of the object instead of the center, that's something that this kind of language motion struggles with. But I think we're hoping in follow-up works to kind of explore these more like fine-grained like language motions to capture like a more broad set of correction behavior. But we found for a lot of like standard pick-and-place tasks, actually this ends up being enough. And a lot of the times the model actually responds appropriately to commands that seem ambiguous, but actually are interpretable by the model. Because you got to remember the action query here takes in not just the predicted language motion, but also the task and the image. So it has full context, basically, of the scene. So yeah.
Okay, so when you have to go higher, like can you give him multiple incremental corrections, so go higher, 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 something like this?
Yeah, exactly. So you can keep intervening, right? It's the language motion is getting predicted at every time step. So you can intervene at every time step if you wanted to.
Great, thank you.
Yeah.
Okay, let's thank Sunil again. Next, we have Soroush Nasriani, and the presentation title is RoboCasa, Large-Scale Simulation of Household Tasks for Generalist Robots.
Hi, my name is Soroush, and I'll be presenting RoboCasa, Large-Scale Simulation of Everyday Tasks for Generalist Robots. Recently, there have been a number of efforts towards building robot foundation models by collecting and learning from large robot datasets. Despite promising results, we are still far from deploying these robots in the wild, as the scope of these datasets is extremely small. Now, continuing to scale robot data collection in the real world is extremely challenging. So how can we sidestep this challenge? We explore how simulation can be used to more effectively scale robot datasets. We note 3 key potentials of simulation. First, simulation can be used to more effectively scale simulation can allow us to synthesize large, high-quality robot datasets autonomously with minimal human effort. Furthermore, we can increase the diversity of these datasets at scale by procedurally generating scenes, objects, and tasks with generative AI. And third, we can run large-scale evaluations at little cost. To realize this potential, we need simulation to satisfy 3 goals. First, it must offer realistic physics and rendering. Second, it must offer diversity in the scenes, objects, and tasks and embodiments that it offers. And it must offer large-scale robot datasets with which we can use to train robot foundation models. Now, recent work in simulation has made large strides towards these goals, but significant work remains in scaling them up to make them useful for the real world. We introduced Robocasa, a large-scale simulation framework with diverse scenes, objects, tasks, and massive training datasets. Now, in this initial release, we focus on kitchen scenes. To capture the complexity and the diversity of real-world environments, we consult numerous architecture and home design magazines and compile a collection of kitchen layouts and styles that reflect the vast diversity of kitchens in homes around the world. We model these kitchens with dozens of interactable appliances spanning microwaves, coffee machines, stoves, sinks, and more. Each scene can be further customized by replacing the textures from a large selection of high-quality AI-generated textures. Robocasa also offers cross-embodiment support for diverse robots. We additionally provide 3D assets that span over 150 object categories, the majority of which are AI-generated from text to 3D models. Our scenes and objects give rise to diverse robot tasks. Here, we focus on 8 foundational skills that serve as the basic building blocks with which to scaffold our long horizon manipulation tasks. They include pick and place, opening and closing doors, opening and closing drawers, turning levers, twisting knobs, pressing buttons, insertion, and navigation. The current release includes 25 atomic tasks for systematically training and evaluating these skills. We can also compose these skills to solve long horizon tasks. We use the guidance of large language models, or LLMs, to define these tasks. First, we prompt the LLM to provide us with a list of high-level kitchen activities. For each kitchen activity, we then prompt the LLM to propose tasks corresponding to that activity. The LLM responds with a task blueprint containing a description of the task and the objects and the skills that are involved. And then we proceed to implement the task blueprint. Here's an example task under the steaming vegetables activity. The task requires invoking diverse skills like pick and place, navigation, opening and closing doors, and pressing buttons. Now, we generate high-quality datasets for our tasks at scale. Given a small number of human demonstrations, we feed these to MimicGen, a data generation system which yields thousands of new demonstrations, all autonomously. Across 24 tasks, we see that training on the full MimicGen dataset of 3,000 demonstrations per task yields a 65% relative improvement in policy success rate compared to just learning on the source human demonstrations. We also show the utility of our datasets in aiding transfer to real-world tasks. On 3 pick-and-place tasks in the real world, we find that co-training with Robocasa data nearly doubles the overall policy success rate. In summary, we have presented Robocasa. It provides diverse scenes and objects created with the aid of generative AI, cross-embodiment support, a large suite of tasks, and massive training datasets. In the future, we are interested in extending Robocasa to support home and office settings, and also training robot foundation models that combine large simulation and real-world datasets. Please visit robocasa.ai for additional details. Thank you.
Questions? Okay, there is one.
Hello, thanks for talk. And my question is, you mentioned that your data set is large and realistic, and you also show some real-world results. So my question is, since like your real-world success rate seems not very high, so what can be the most of the failure cases?
Yeah, so we just really scratched the surface with those experiments. I think there's a number of factors that could explain what happened there. So the real-world setup that we had was completely separate from simulation. We didn't really calibrate anything to do with the robot controllers. It had a completely separate hardware stack with different cameras. Some of the things that we can do, I think, is to make sure that the robot controller in simulation and in the real world are more in sync with each other and calibrated with each other. And also, one of the things we want to do is add more visual diversity by randomizing the camera poses and adding scene clutter. And I think that that can help to bridge the gap.
Thank you.
Yeah, hi, over here, to your right.
In the front row. of the
Doesn't
room.
matter really. But yeah, thank you. So you touched on it there, I guess, in your answer to the last question, but all of those kitchen scenes you showed were very pristine, low clutter, perfectly clean, things like that. I mean, in terms of getting these sorts of things into the actual real world rather than just hardware in a lab, I feel like the robots are going to have to be able to deal with, I don't know, greasy surfaces and butter and all of those things. Are you thinking about how you might incorporate those sorts of extra challenges and imperfections into your simulations?
Yeah, so I see maybe two immediate next steps. One is just to have generally clutter around the kitchen, like rigid body objects around the kitchen, but also to have more support for deformable manipulation, like you mentioned, the grease and the butter, plastic bags and things like that. Yeah.
Yeah, if we maybe have time for another one. So is your focus of this Robocaster the task planning part or is it the grasp planning? Because how realistic are the interactions with environments in terms of, well, forces applied? I mean, there are plenty of these simulators out there, and I was wondering, is your focus the task planning or is it really the interaction?
So we tried to make Robocasa quite broad so that various people in the community from different fields can find it useful for their research. So you know, you can use this for you know, if you do just perception research, you know, we support all kinds of like modalities, and you know, you can also use it for high-level task planning, for training low-level skills, for large-scale imitation learning, task and motion planning. So I'd say really all of the above.
Okay.
Let's thank the speaker again. For the next paper on aligning image and action spaces for diffusion-based policy learning, we have Vitalis Vasilios.
Hello everyone, I'm Vitalis and I'm happy to present Render and Diffuse, a method that aligns image and action spaces for more efficient imitation learning. So all of us want to see robots in the real world doing useful things. For example, if a robot would put the toilet seat down, maybe it would make your life a little bit easier and we can avoid fighting over it. And nowadays, the most common way of teaching robot new skills is by learning the mapping between high-dimensional observations, such as images, to robot actions. However, learning this mapping between two very inherently different spaces can require a lot of data. And a way to alleviate this and simplify the learning problem is to more closely align these spaces. So to this end, we introduce Render and Diffuse, a method that uses virtual renders of the robot and a diffusion process that iteratively updates them, allowing us to learn precise low-level control. So at the core of our approach is the way we represent actions. We don't represent actions as end effector velocities or poses, expressed as vectors, but we rather represent them inside an image by rendering the robot in a configuration it would end up kinematically if certain action was executed. So this way of expressing actions in the image still leaves us with one choice of how we're going to update them during the diffusion process. And this choice leads to several R&D variants, each combining image and action spaces in unique ways. In case of the image space, we predict per pixel predictions that say how each part of the robot should move to more closely resemble the desired actions. And we learn to make these predictions using a transformal model. It fuses information coming from multiple cameras and any additional inputs, such as gripper states or diffusion time step, and all of it can be trained end-to-end using a data set of demonstrations. So during deployment, we start with an RGB observation. We render action sampled from a normal distribution. We make our predictions with a learned model, and then we project these predictions to 3D. And we can do that because rendering gives us the ground truth information about depth. We can then calculate how these low-level actions need to be updated and do it iteratively. And at the end, what we're left with is the desired low-level actions that the robot can then execute. And this is how it looks when the robot executes real-world tasks in the real world. Here you can see what the robot sees from the shoulder camera and from the wrist camera. Note that for the wrist camera, we render only the fingers of the gripper, not to cause severe visual occlusions. So there's two main advantages of using this image and action space unification. First, it's more sample efficient, and second, it increases the spatial generalization capabilities. And to test that, we conducted extensive simulation experiments. So for example, here you can see a setting where a task is to lift the lid of the saucepan. We provide 5 demonstrations in this case that sparsely populate the workspace. And when we evaluate the workspace densely, we can see that R&D exhibits strong generalization capabilities with just a few demonstrations. We also tested sample efficiency of R&D by increasing the number of demonstrations that more densely cover the workspace. And as we can see, it outperforms the baselines, especially in the low data regime because of this action and image space unification. It also scales well with increasing number of demonstrations. We also show that Render and Diffuse is capable of learning various robot tasks in the real world without requiring extensive amounts of data. Here we provided 20 demonstrations for each task. So in general, we are really excited about this image and action space unification that R&D provides and all the possible future directions. For example, because we are staying in the image space solely, we can integrate image foundation models to increase the generalization capabilities even further. Because we can easily swap out what kind of model we render during training or inference, maybe we can learn cross-embodiment policies easier, or maybe even learn from human videos. So I'm really excited to see where this goes and what the community can think of. With that, I would like to thank you, and if you're interested, please come to my poster or contact me anytime. Thank you.
Hello? Yeah. Hi, thank you for the great presentation. That's a pretty cool idea. I noticed in some of the tasks, you obviously have to open and close the end effector for manipulating the objects. But in the video preview that you've shown, with the overlay of the target for the end effector, it seems that the end effector is static. It never actually closed the fingers. So my question was, in this render and diffuse work, are the end effector poses rendered on the image only for the pose of the end effector, or do they also include the target opening?
Yeah, thank you. That's a great observation. In our current implementation, yes, we render only the open gripper, just to visualize how the gripper would move. And then we also have another separate prediction that predicts whether a gripper should be open or closed. So this is just to simplify the kind of initial implementation of it. In the future, you could honestly render the predicted width and then update everything through a kinematic chain. And this also would allow you to control the opening and closing of the gripper more continuously, but you can also do it with the full configuration of the arm rather than just the gripper.
Yep.
Have you considered using the depth channel as well beyond RGB, where perhaps the gap between rendered image and observation may also be smaller?
Yes. Initial experiments for me show that it doesn't really have that much effect if you add depth or not. And just for pureness, kind of, I left it out. But it does have certain advantages. So if you have depth, you could render the robot more precisely, mimicking what's occluded and what's not. So that in the future might be actually a very nice way to do it, yeah.
Thanks, very interesting.
We have a question over there, yeah.
Since you render the actions to the images, does it limit the accuracy of the actions, and does it work for example, highly dynamic tasks? Thanks.
So the first part of the question, yes, it does affect it a little bit because the input and output spaces are very high dimensional in this case, because if you want to predict multiple time steps in the future, it's pretty much becoming a video generation problem. And if you want to learn very precise tasks, you need to learn the predictions very precisely in this high-dimensional space. That's quite hard. Generally, if you just leave it training for longer, it will learn the very precise and complex motions quite well. But also we can use one of the variants of R&D called R&D AI that combines both action spaces. So you can diffuse first chunk of time steps in the image space, and when you commit to one mode, you can also take a couple of diffusion updates in the action space directly. That's lower dimensional to have that high frequency modulation at the end.
Okay, let's thank Vitalis again. And next up we have Vidhi Jain presenting end-to-end video conditioned policy learning with cross-attention transformers.
Hi everyone, I'm Vidhi, and today I'll be presenting with to Robot. And this is a joint work with Google, DeepMind, CMU, and U of T. So imagine your future home robot. In what ways would you like to communicate with this robot and tell it to do useful things? Maybe you want to tell it to do something. And this has been used in models like RT1 and RT2. But consider this. If you want to tell it to open a drawer, a fridge, a book, or a bottle, all these have very different low-level motion control. So how can that word embedding capture that nuance? Another very common way is to show what the final state's gonna look like. But tasks like holding a mug or moving or swirling the mug all can have the same end state. So how do we resolve the task ambiguity here? Maybe we want to show a video, show it how to do that task. And this is what we explored in our work. We tried to show how the robot should do a particular task, and then the robot should execute it in its own environment. And prior work has looked at this. They have either considered to just focus on hands of the actor, or in Paint the hand, ignore the actor completely and just the moving objects. But why leave out information when we can do it end-to-end? And in 2020, BCZ was one of this work which tried to encode human videos, and Mutex is more recent work where that was shown with a limited workspace. What we try to do is use 100K publicly available robot trajectories with diverse background, distractor objects, and lighting conditions, and show that we can use a video, which is shown here in blue, as a prompt, and use the other half as the robot state, and train a policy to predict the right actions. So here we are showing how the architecture looks like, and we have inputs as the prompt video and the robot state observations, and we predict the regular standard actions of gripper pose and closeness, and the rollout of successful trajectory is on the right. What we are using in this model is cross-attention layers, and in comparison to standard self-attentions, cross-attention help to reduce the memory requirements, which is especially important for videos. And in training this model, we use behavior cloning, but we also use auxiliary losses like video alignment loss and contrastive losses between the two videos we have and the text embedding. So how well does this perform? Here we show one successful example where the model is able to pick up a Coke can and place it on the counter. In this example, the model can open the middle drawer. In both of these scenarios, BCZ kind of failed to perform, and several such examples exist. But what if now we have a prompt video, but the state does not have that in its environment? That object does not exist. So in that case, we also experiment with cross-object motion transfer. The prompt shown here has a Coke can, which needs to be placed upright, but now we place different objects in front of the robot and see what it does. So the policy has not seen this during training, but it's able to manipulate a bunch of these objects, and most surprising was the banana. We also tried to chain these prompt videos and see the longer horizon tasks. So here we are showing 3 prompts of opening a drawer, placing something into drawer, and then closing it. You can note they have different objects, very different distractor objects as well, and background. But we were able to execute all 3 tasks sequentially in the same environment. But video condition models have a long way to go, and we observed certain kinds of failures. So one of them, most prominent, was grasping. It failed to grasp properly objects which were like this bottle. It kind of also self-occluded itself sometimes and was not able to see this. And there could be ambiguous prompts. So just like language instructions could be ambiguous, videos could be ambiguous. And in this case, it was unclear whether the chip's back was moving to the right or just moving near a Coke can. So the final takeaway is that Vid2Robot is enabling video condition policies, and in future, we hope that this can enable learning new skills on the go. Thank you.
Questions? While waiting, I can ask a question. So there have been some work on learning like reward functions from videos or human demonstrations. Like, what do you think some of the advantages or maybe even disadvantages of learning a policy over learning a reward with these human videos?
Yeah, learning a reward function is showing what the final state is going to look like, in my opinion, to some extent, whereas learning from videos has the chance of learning how to do the task. So there's a question between whether we want to show what to achieve or how to achieve it.
Thank you. Any other question from the audience?
Yeah, I'm the volunteer.
Okay,
Hello.
I can ask one more.
Oh. I have a question.
Okay.
Yeah.
Go ahead.
So in the demonstration you are given as video, I realize you upsample the video, right? Or downsample the video a little bit, right? What if the keyframes are missing? Like for some crucial tasks, one of the keyframe that is missing because of the sample, will that influence your learning? Will that influence your result?
Yes, that's a good question. So the question is, we did downsample some frames from the video, and would that influence the result? And that really depends on the computational power of the policy. So I would agree that would influence the result, and we spent a lot of time figuring out what is the size of task videos that we require. So these are roughly very small tasks, as you can see, and therefore sampling 16 frames was kind of enough for showing the entire task performed, what was the task to be performed. But as we want to do it for longer videos, we thought it would really affect the performance. So longer horizon task is something that we tried with chaining these videos together.
Okay, thank you.
Okay. Let's thank the speaker again. Okay, for the next paper on offline imitation learning through graph search and retrieval, the authors couldn't make it, but we have a surrogate speaker, Carlos Ferraza, who has kindly agreed to give the presentation. Go ahead.
Thank you. Hi, everyone. I'm presenting this work on behalf of my colleagues. Imitation learning has shown impressive results these days, but collecting high-quality human demos for precise dexterous manipulation is still pretty challenging. As you can see in this video on the right, we're trying to tie an elastic band onto 2 wheels, and there are a lot of failure cases in the process. But we still want to learn from these behaviors. We could use offline RL, but as you know, in practice, it can be quite brittle. So how can we do it? We present this new algorithm, GSR, which is a simple yet effective algorithm that learns from suboptimal demos through graph search and retrieval by improving again upon the suboptimal trials. Background, many offline reinforcement learning algorithms are based on weighted behavior cloning, where we basically try to assign some weights to transitions in a data set. We consider a robotic manipulation problem where we have a goal condition nature in this case, And what we would like to do intuitively in this case is assigning high weights to transitions that bring us closer to the goal. We could also implement this in a soft manner, as you can see in this formula here, where Z is a normalizer. In reality, this normalizer, but also the distance measure, are hard to compute in a non-tabular case. We'll look at this a bit more closely. The key idea here is that instead of computing Z across all possible actions, we retrieve nearest neighbors of the state and compute an approximation of Z. And now if we can organize the data set into a graph, we can also calculate the graph distance measure. This presentation will focus mostly on the retrieval part. So again, the key idea in the tabular case would be we have some states, we know the actions that depart from the states, and you compute Z over those transitions. But in a more general case, what we do is we compute the nearest neighbors, for example, S1 and S2, and then take the transition starting from all these states and compute the normalizer over those. So for each state in the dataset, we basically retrieve nearest neighbors, and then we can redistribute the default weight, which is usually 1, across all of these transitions. And particularly, we assign higher weight to the transitions that are actually good, that have higher value. In reality, some of this sample state can be more relevant than others. So we also add a similarity measure, a similarity term to this weighting function that basically accounts for the fact that we want high weight on transitions that are both very relevant but also have high value. The similarity function is based on frozen or fine-tuned pre-trained representations. So here's the full scheme of the architecture. We have a demonstration dataset that we want to reweight. We build a graph based on this dataset, and we use nearest neighbor retrieval to compute these weightings. These weightings are based on a similarity measure and on their value. So in the end, we reweight this dataset, and we can just use it for classical behavioral cloning. So experiments, we consider several challenging tasks in both simulation and the real world, with challenges both in perception and control. We have 2 to 4 RGB cameras on all tasks, and there are very dexterous tasks like, again, tying this elastic band over 2 wheels or using a tweezer, for example. We compare with behavioral cloning and IQL baselines, both of them using diffusion policy as our method. And our method shows to improve both success rates, but also the time that it takes until completion. Now you'll see an experimental comparison with one of the baseline IQL. Again, in the task of tie and bend around the 2 wheels. And you can see that the baseline tends to replay the suboptimal data that's present in the data set and gets stuck or struggles at some of the states. While on the right, our approach can smoothly insert the elastic band around the 2 wheels. And you'll see a few more time this example now. So we looked at our weighting function resulting from this approach, and we see that it has a filtering behavior. It basically filters out trajectories or transitions that are dangerous or non-optimal, while it keeps or gives higher weight to failure recovery modes or trajectories that are actually good. So in summary, we can use graph search and retrieval to improve learning from suboptimal demonstrations. We plan to extend this work on even more challenging scenarios, and you can see some of the future directions up on the slide. Thank you.
Any questions?
Congratulations, always an amazing job. In the last slide, you mentioned as future directions issues related to multitask. What do you mean? That you can combine or discretize a complex problem, and you like to combine the same database of experiments? On what is the idea of multitasking?
Yeah, I'm not entirely sure. You would have to check with the authors, but I think the idea is really like to have data sets, as you said, that have transitions from multiple tasks and hopefully improve by using this multitask data set upon learning from a single task.
Okay, thank you.
Okay, thank you.
Thank you.
I'm sure if there are more questions, maybe you should contact the authors directly. Okay, so next up we have Ankit Goyal, and he will be talking about learning precise manipulation from few demonstrations.
Hello everyone, I'm Ankit Goyal, and hope you're having a nice conference and enjoying the city. I'll be presenting our work RVT2, Learning Precise Manipulation from Few Demonstrations. So this work was done at NVIDIA's Seattle Robotics Lab with awesome collaborators, Vals Blukist, Jay Shu, E.J. Gaw, Yue Chow, and Professor Dieter Fox. Recently, we have seen a significant progress being made at behavior cloning methods that can learn from few demonstrations. So these include RVT, diffusion policy, VQBet, and many others, including 3D diffusion policy, ACT, and ACT3D. Most of these methods are evaluated on tasks that are coarse. For high precision, the method of choice is still reinforcement learning, which make finer adjustments at the contact. So in this work, we wanted to explore, can we push behavior cloning methods to handle high precision tasks which have millimeter level precision requirements? So before I go into our method, I'd like to explain our setup as to what we do. So here, we want to learn from very few demonstrations. So for example, picking up and inserting peg, these are the 10 demonstration cases that we use for learning this task. Also, we want to learn a single policy that can handle multiple tasks, and each task can have different variations, which is specified by the language. So here are the 7 tasks that we considered in the real world, and we learn a single policy that can handle all these tasks. In terms of the pose variation of the objects, we consider variations in the range of feet square. So for this peg insertion and plug insertions asked, these were the differences. And we consider a single RGBD camera as input to the robot. So here I'm showing some of the eval time executions of RVT2 on some of the high precision tasks that require millimeter level precision. We also evaluate on SIM, where we achieve state-of-the-art results. Along with being the best performing method, specifically on RL bench, we are also able to achieve increase the inference speed. So the method is also faster, and it is like twice as fast as the prior version of the method, VT. So let me quickly give an overview of RVT so that I can explain RVT2. So given a language instruction and a scene, so the scene can, the sensor input that the robot gets is either a single or multiple RGBD calibrated camera images. These camera images are then fused together to construct a point cloud, and the point cloud is rendered at fixed locations with respect to the robot, which we call these virtual views. And from given these virtual views, we run a transformer network that predicts heat map corresponding to each of the virtual views. You can notice that these heat maps are multimodal in nature. And given these 2D heat maps, we fuse them together in 3D. And the 3D heat maps are also multimodal. And given the heat map and the feature predictions, we predict the next gripper pose and execute the action. In RVT2, we use a culmination of architectural and system level changes on top of RVT, and one of the design features was this multi-scale design, where we make a coarse level prediction and then re-render images at closer locations and to make another finer scale prediction, and this helps us in achieving much higher precision pose. We also write a custom accelerated renderer for our use case because our use case is very specific. Instead of relying on general purpose renderers, we write our own CUDA renderer, and that helps us in speed. We also change some of the layers in RVT. One of the tricks was using this convex upsampling operation, which without affecting the performance helps us in save memory and hence is improving speed. There are many other changes, improvements that we make that I'm happy to talk about at the poster, and the code is online. And please visit us at our poster. Thank you.
Okay, questions?
First, thanks for the nice talk. Just one question. How could you solve the correspondence problem between different viewpoints heat maps?
Yeah, so that's a good question. So along with the heat map, we also render the XYZ correspondence values. So the heat map that we render, the virtual views that we render, along with RGB, they also have this XYZ value which uniquely identifies each point, and that value is same across views. So that information is explicitly provided to the model.
Okay, thanks.
Any other question? I'm curious if, like, all these vision and rendering processes that you introduce, like, do they add some latency to the system, or are you able to run this in real time?
Yeah, so they do add latency, and the final inference speed that we report is like including everything. So still we can run it at 20 hertz.
Okay, let's thank the speaker again.
Okay, for this last paper of the session, we on imitation learning to bootstrap reinforcement learning, we have Heng-Wan Hu.
Okay, yeah, spoiler alert, this is not so much about imitation. Instead, we're going to look at how we can use imitation policies to accelerate reinforcement learning on robotics tasks, especially in the real world. Or from a different perspective, how can we improve upon imitation policies by running sample-efficient RL while leveraging the capabilities of those powerful policies? So let's start with some brief motivations. Imitation learning is popular for learning neural network policies. However, it has some drawbacks, and we argue that running RL on top can address some of them. For example, the data set for imitation learning often have a limited coverage, leading to poor generalization. Robots often need to adapt for changes such as deformation of object over time, which requires recollecting data. In comparison, RL can improve beyond the success rate of the static data set, and it will be a critical component for autonomous self-improvement. In this work, we assume access to a small demonstration data set, a success detector for 0, 1, sparse reward, and a function to reset between episodes. We propose IBRL, imitation bootstrap reinforcement learning. As the name suggests, IBRL uses imitation learning to assist and accelerate reinforcement learning for better sample efficiency and performance. It starts with the imitation learning policy. Assuming access to expert demonstrations, this can be done with any off-the-shelf imitation learning methods such as behavioral cloning. Then, we use the imitation policy in two phases in RL. Note that during RL, the imitation policy is a separate fixed policy that does not change. First, we use it to improve online exploration. For every online interaction step, we fit the observation of into the RL policy being trained, as well as imitation policy to get two actions. Then, we query the target Q function to execute the action that has higher Q value. This helps exploration by providing some safe alternatives that we can always fall back to when RL policy is bad. Similarly, during training, we bootstrap from the higher Q value between the Q of the RL action and the Q of the IL action. Essentially, we replace the RL policy with a hybrid RL plus IL policy in both training and inference. First, we evaluate IBRL in the meta-world benchmark. We compare IBRL against 3 baselines. RFT, the green line, stands for regularized fine-tuning, which basically just adds a weighted BC loss to the policy loss in RL. RLPD, the blue line, uses vanilla RL loss, but oversamples the demonstration so that half of the data in each batch are demonstrations. MODEM is a model-based RL method with demonstration that has achieved strong performance on this benchmark. In aggregation, IBR performed much better than RLPD and MODEM on this benchmark. It performs similarly with RFT, as we find this benchmark to be too simple to distinguish two. It's also worth noting that we have tuned RFT to use the best coefficient for the BC loss, but we don't have to do so for RL because it automatically balances the RL and imitation. In a more complicated robot mimic benchmark, we see a much bigger gap between IBRL and existing method, both in learning from pixel and learning from states. The gap is also bigger in a more complicated square task. To highlight one of the ablations, we show that it is important to have the imitation policy in both inference and training stage. And most importantly, we also evaluate IBRL in these 3 real-world tasks with wide range of initial locations, including one with deformable object. IBRL achieves significantly better performance than the baselines. Let's look at some detailed numbers for the real-world tasks. Note that we use the hyperparameter from the sim without any additional tuning. So all methods can solve the simple lift task pretty well, but IBRL excels in the harder eval mode where the block is initialized on the boundary because it learns faster and has seen more initial conditions. Note that the original BC policy completely failed in this out-of-distribution eval. And the sample efficiency of IBRL is more prominent in the harder drawer opening task, especially if we had performed early stopping at 10K steps. And finally, in the hardest deformable clause hanging task, IBRL performs significantly better than the baselines. So we visualize the learning process of our method by rolling out a few checkpoints with different amount of real-world interactions. Here, we take 4 checkpoints from no training to 24 minutes of training. IBRL learns to open the drawer from random location pretty efficiently, as we can see here. And this task is particularly interesting because it will be hard to simulate the deformable clause. And also, IBRL can also adapt to the fact that the clause becomes softer after many interactions, but the original imitation policy wouldn't be able to do so. Yeah, that concludes my talk. Thank you.
Yeah, if understood correctly, here you're doing here on the right, right?
Oh.
You're doing a max operation, right? So whichever action, the imitation action or the RL action has the highest Q, that's the one that you are executing,
yes.
Right? And you're doing this. Have you tried other ways of integrating them? Let's say the RL is a residual policy to the imitation learning, and then you add these actions and how this would behave relative to what you're trying?
Yes. So residual policy, I think we actually tried residual policy as well, but we formulate the RL policy as a residual policy on top of the imitation learning. So basically now the RL policy output a residual on top of the imitation policy, but then we still select which one to take, either the original action from the imitation or the combined action from RL by looking at the Q value under this framework. So that only changes, I guess, policy parameterization, but not the full story. So yeah, that kind of helps sometimes, but it's not, yeah.
Okay. And that's not your final proposal here. Your final proposal here is RL, the RL policy is not a residual, is a full action.
Eventually, we execute the hybrid policy at inference time according to which action has higher. So if we remove the imitation policy after training, we see like a 5% to 10% performance drop if we only use the RL policy. So the imitation policy still plays a role in the final product. Yeah.
A question on the left.
Yeah. Maybe I missed it, but what was the speed gain or sample efficiency gain for the reinforcement learning algorithm after including imitation learning?
So yeah, so if we look at like the learning curves, for example, in this real world drawer opening task, IBRL learns converges to like open the drawer 100% of time with 60% less real world interactions. So that's an improvement in sample efficiency. Or you're asking why it improves?
No, just how much. Yeah, we couldn't see it on the screen.
Oh, yeah. Okay. You can come to poster.
Thank you.
Any other questions? If not, I have one. Regarding the setup, so there's been prior attempts actually to use imitation learning policies. In fact, it's quite common to seed reinforcement learning policies with imitation learning policies, but the setup there seems to be a little more straightforward, where you just train a model directly using IL and then just use that as the seed and start RL there. So sorry, I didn't quite get whether you compared against this very basic naive approach or not, and whether there were improvements of that.
So one of the baselines, the RFT, is exactly doing that. So it initialized the RL policy with the imitation, and then keep a regularization loss where just the regularization loss is just a BC loss, and then keeps running it online. So there are a few downside of it. First, like for example, the two losses, the RL loss and the BC loss, are dragging the policy into different directions sometimes because we're trying to fix where the VC fails, right? And then also something we found that BC and RL, because the laws of formulation are so different, the gradients are different, they tend to benefit from having different architectures, completely different architectures. So we can separate the two by having separate policies and keep imitation fixed at RL training time.
Thank you. Yeah. Okay, let's thank the speaker again. Oh. Sorry, we'll carry that. Okay. So thanks everybody for attending the session. This brings us to the end. This coffee break is open now.
Hello everyone. Let's get started. Welcome to the session of Perception and Navigation. My name is Jay. I'm from Google DeepMind, and I'm one of the session chairs.
Hi, I'm Dee from the University of Post and Telecommunications. And let's from the first speaker and Lucas, and a unified approach for spatial temporal metric semantic SLAM in dynamic environments.
So welcome everyone. It's a great pleasure to be here and tell you about our work on Chronos, a unified approach for spatial temporal metric semantic SLAM. So we all want humans to be, or robots to be part of our everyday environments. However, these scenes are typically shared with humans and they are highly dynamic. This includes both short-term dynamics, meaning robots or agents moving in front of the robot, as well as long-term dynamics, which are agents interacting with the scene and causing changes while the robot is not looking, which have a very distinct nature. So an ideal perception solution needs to deal with both of those, which wasn't possible before. We therefore posed a spatial-temporal metric semantic SLAM problem, where the goal is we want to build a spatial-temporal representation, so not only a best running estimate, but a representation of the scene at all previous times and its evolution through time. We also want to have a dense reconstruction and an object-level scene understanding so that the map that we build is useful for interaction, planning, and reasoning. Finally, we want to do all of that in a simultaneous localization and mapping fashion, means it has to run incrementally and in real time on board compute-constrained mobile robots. We can frame this as a maximum a posteriori estimation problem, where we try to estimate the state of all objects and the background at all times. So each object has a deformable surface, a changeable pose, and a semantic label. We also want to estimate the robot state based on measurements of the scene and ego motion. This is a really, really hard problem because there's a large number of variables, everything is time dependent, the problem grows extremely quickly over time, and there is strong coupling between all of the variables and sources of error. In the paper, we show that using the assumption of local consistency, we can actually derive a factorized version of this problem that is much more manageable. Where essentially we can use locally consistent fragments, which are these Ys, representing by parts of the measurement, optimize them spatially, and finally use this optimized latent representation to reconstruct the history of the entire scene in a dense representation. And we actually use this very factorization to propose a novel system that we call Chronos. In our approach for the local estimation part, we leverage this local consistency to use geometric verification to do essentially short-term motion detection. We also use semantic cues to detect currently static objects and reconstruct those. All of these object fragments can be extracted at an arbitrary representation, such as multi-resolution reconstruction. Most importantly, we asynchronously track every piece of background and every fragment to ensure that this assumption of local consistency holds. We can then globally optimize over these using a joint formulation over the robot poses, the background deformation, as well as the poses and associations between different object fragments. And we formalize this as a robust vector graph estimation problem. Finally, in the reconciliation step, we use an additional deformable change detection technique to globally estimate the history of all of the objects, when and whether they have appeared and disappeared. So if we now run all of these steps on a mobile robot, this is what it's going to look like. We here have a Jackal robot equipped with an RGBD sensing camera, mapping this real-world environment. And to really highlight the four-dimensional nature of our approach, we have this 3D grid where we see on the z-axis the number of objects estimated to be present. We see on the right-hand side the elapsed time in reality, and on the left side the belief about the state at previous times. So naturally, the real-time axis is on the diagonal. As expected, as the robot moves around and detects more objects, we see that the number of objects estimated to be present increases. We are able to correctly detect also shorter moving objects and reconstruct their deformable surface and trajectory. Soon, the robot will be closing the loop, and we can see how the robot poses and the background are being optimized. In addition, the robot now observed that this chair that was previously there is now observed to be absent, and we see that we decrement the numbers of objects present. Furthermore, Kronos correctly detects that this cooler has now appeared on the table, so we increment the number of objects. To show our understanding about the task, we can now play back our state belief, given all of the information the robot has collected so far. And we see that we have a good estimate of where all the different objects were in time, but most importantly, we've updated our belief when objects have appeared or disappeared based on when they first and last seen. Now, if we keep our query time fixed and have the robot gather more data in the future, we see that this information flows back in time, and we optimize our belief about how many objects are present, the completeness and accuracy of the poses and the background. In this fashion, Kronos is able to continually build and maintain this four-dimensional dense representation of the scene at all times. Kronos is available as open source. Please give it a try if you're interested in it, and we're very happy if you have questions now, come catch us at the poster or shoot us an email. Thanks a lot for your attention.
Any questions? In the middle.
Okay, my question is, do you use later measurement to update the previous understanding of the environment?
Yes, the idea is we always, at every time step, we use all the measurements we have so far to essentially maximize or build the representation that best explains all of the measurements. But the key idea is we can group the measurements in a way that this problem actually becomes tractable, because otherwise it's a very hard problem.
So does that mean it's a kind of offline approach rather than incremental approach?
This is fully incremental, and it runs in real time. So the local window, we can actually run at around 20 frames per second on CPU only, if we exclude the semantic segmentation. And then we can run the change detection, for example, at slower threads if there is a loop closure, but it also only takes less than a second.
Thank you.
Any other question? We still have time for a quick question, I think.
Sometimes an object appears on the scene while you are not looking at it. Apparently you are optimizing for the best time it appeared or something, but in this case you don't have any idea when the object did appear. So what is your estimate, or do you have some uncertainty about this?
That is a fantastic question, and it's actually also a bit of a philosophical problem. So usually what happens, we use this change detection technique to figure out, is there, do we observe there to be free space before or after an object is there? And if we have this observation of absence and an observation of presence, we can estimate that the essentially risk minimizing estimate is somewhere in the middle between these two things. If you only have a singular estimate, for example, you detect a new object, but you didn't see that there was no object before, you can either say it has appeared immediately, or you can say we believe it's always been there because we have no evidence to the contrary, and currently we do the latter.
Thanks.
Okay, let's thank the speaker again.
Thank you very much.
Next, let's come to demonstrating agile flight from pixels without state estimation.
Good morning, I'm Davide Scaramuzza, and together with my student Ismail, I'll be presenting our paper entitled Demonstrating Agile Flight from Pixels Without State Estimation. But before I start, I would like to make an emotional connection because it was exactly 15 years ago that we demonstrated the first vision-based flight, and it was actually happening here at TU Delft during a competition. You see a video ongoing here. The drone was completely autonomous, although we had to secure it with a fishing rod and used only a single onboard camera and an inertial sensor. The key enabler was a state estimation algorithm that would keep the drone flying despite noise and uncertainty, because in computer vision, the uncertainty scales quadratically with the distance from the scene. And one of the people in my team, Stefan Weiss, that you will see in a moment in the video, then after this work joined the NASA Jet Propulsion Laboratory and contributed to the navigation algorithm of the Ingenuity Mars helicopter, which actually also used a single onboard camera and an inertial sensor, very similar to what we demonstrated at TU Delft at the time. Since then, we have done tremendous progress, and what we've been working on over the past few years is studying what it takes to fly autonomous drones better than human pilots. The reasons is to increase the productivity of a drone, because a drone that flies faster can fly longer distances. And last year, after 7 years of work, we demonstrated for the first time that an autonomous vision-based drone powered by a neural network controller trained in simulation with the reinforcement learning could outperform the world champions of drone racing. The state was estimated using only onboard images and an inertial measurement unit, but differently from this, human pilots do not do state estimation, neither they access IMU data. So in this paper, we asked the question, how can we fly from pixels without state estimation?
So in this work, we are able to fly from pixels directly for the first time by using an image abstraction. You can see here our drone flying with speeds up to 40 kilometers through a complex racetrack. The image abstraction we use are the edges of the gates. So we use a model to detect the edges of the gates as an intermediate representation. This has multiple benefits, such as high rendering speeds when training our model, and also when we transfer our model, we do not rely on background information, for example. As you can see here, the drone only sees a black and white image with the edges, such as an Atari game would look like, for example. While at deployment time, you can also see the RGB image here on board. We use a very similar hardware to professional human pilots by transmitting our video to a workstation, which is acting as the AI pilot. And the benefit of that is we can use very large-scale models, such as a transformer-based detector. In terms of architecture, we train our policy by rendering very fast this image abstraction, encoding it through a CNN, and then training with a reinforcement learning algorithm, PPO. We also use an asymmetric actor critic. In that case, the critic has a privileged information from the simulator, while at deployment time, we only use the actor. In terms of history, we use the 3 past actions as an additional input. And here you can see an animation of our training, comparing state-based with pixel-based. In yellow, you can see the state-based policies are learning much faster. However, the pixel-based policies in blue, they are also learning the CNN encoder from the large state space. So therefore, it takes longer to train the policy. But eventually, you can see how the policy is converging to very similar performance. And finally, if we deploy our policy in the real world, you can see how we can fly directly without any intermediate state estimation, but only using the image feed. Just like human pilots, we can only fly from pixels to actions. And in case you haven't seen our drone demo yesterday, we're going to present it today again at 12 at the Mechanical Engineering Department. Or if you want to see it again, come by and have a chat. Thank you.
Questions?
Thanks a lot for the presentation. I have one question. So you're taking in the state of the gates and you encode the state in this image again, and then you learn from this image. What do you think is the gap to directly learn from the raw RGB image? Because it seems like you encode the state in this image representation that contains all the information about the state.
I would not say that it contains all the image information, since it is a partially observable problem still. But the benefit of using that is that we don't have to simulate all effects such as motion blur, rolling shutter effects, different light conditions, but we can bring our demo here to Delft and still fly.
Okay, thanks a lot.
Hi, thank you for the great talk. So I'm wondering, have you started applying your method to other tasks or other systems, or do you have plans for this? Thank you.
So far, this is our first work, directly mapping pixels to actions, but we are definitely considering it for the future. Yeah.
Great. Thanks for the great talk. Can you provide some more motivation for why not use an IMU if it's available?
I think in our case, it's more of a challenge to perform similar agile flight as human, more as a challenge of intelligence than rather than an engineering problem, because you could equip the drone also with many more sensors.
We only had time for one quick question.
Okay, I think it's a very cool demo. Just wonder, from a theoretical point of view, what's some key difference from this with visual surveying kind of technique?
Sorry, compared
What's
to...
the key difference between this kind of problem with a visual surveying problem?
I didn't hear the last part, sorry.
Visual surveying problem.
Uh-huh.
Visual surveying. I can take the question. It is similar in the sense that you want to, in visual surveying, you minimize the photometric error in order to get to the target image, right? You have to align basically your action space to that. So far, there was never a visual surveying algorithm that was ever applied to this kind of flying fast problems. I think the problem has to do with robustness, motion blur, noise, intermittence of frames. That is also another issue. I mean, we can talk a lot about the fact that the stream is not coming continuously. Okay, there is also that issue. So if you rely on these methods, of course, they actually may fail. So, but of course, that is still that does mean that you cannot formulate the drone racing problem as a visual surveying problem. Actually, that would be an interesting research problem.
Okay, I think we could get more information from the demo session. And let's thank the speakers again. Now let's welcome the third speaker. You've got to feel it to believe it. Multimodal Bayesian inference for semantic and property prediction.
Hi everyone, my name's Parker. I'll be presenting our work. You've got to feel it to believe it. So our primary focus in this paper was on legged locomotion. And over the past decade, we've seen, big advancements in this area. But there's still a lot of cases where these algorithms can fail. And we see here the robot slipping on ice, and we'll see next that it can't really climb a hill and it slips back down. And the reason for this is really because the properties of the surface that the robot is trying to walk over really do affect this task. And so the goal of this paper is really how do we address this property estimation. And so the contribution that we provide is a way of doing real-time Bayesian inference over the semantic estimates as well as physical properties together. And so we use both vision and tactile sensing in this work. Why do we use tactile sensing? Well, we compare against our previous method that uses only vision. And in this case, we see that it's not able to visually distinguish between snow and ice. It thinks the entire region is snow. And similarly, if we compare against state-of-the-art traversability estimation methods that only use vision, we see that these methods are likewise unable to distinguish that there's ice in front of the robot, and this can cause failures. And so if we relied only on vision, the robot tries to walk across the surface, and we can all expect what happens next. It slips and falls. So in this work, we start with vision, and again, the robot is not able to distinguish between the snow and ice. But we tell the robot this time to go and take a tactile measurement of that surface, similar to the way a human would scuff their shoe on the ground to determine what the coefficient of friction is. And we can use this tactile measurement to jointly update both the semantics and physical property estimates using Bayesian inference. And then the planner can take this information and decide to switch to a maybe more static stable gate in order to successfully traverse this surface. So the algorithm in this paper goes as follows. We start with a data collection step. So we can take RGBD images from an onboard sensor and pass these through some off-the-shelf semantic segmentation network in order to get terrain property estimates, or terrain class estimates. We use the depth information to create a local geometric map of the robot's surroundings, and then we project these semantic estimates onto this map in order to recursively estimate terrain class. We then provide a data set which allows us to probabilistically relate physical properties to these terrain class estimates. And because we're using tactile sensing, we can actually measure these physical properties directly, right? And so by measuring these physical properties directly, we show that we can then do Bayesian inference over the joint semantic estimates and physical property estimates. So if we look at a map of a robot's surroundings, in this case a voxel map, and we look at one discrete element of this map, in this work, we focus on estimating the joint probability of the semantic class and physical properties of this discrete element, and we can do this over the entire map that the robot generates. We break our algorithm into two steps. There's the vision step and the tactile sensing step. So from vision, we get these semantic segmentation images as observations. And what we show in our paper is that if we consider some family of distributions representing the prior estimate on the semantic class, when we use Bayesian inference and apply Bayes' theorem to these semantic segmentation observations, the posterior can be computed in closed form and is actually in the same family of distributions as the prior. And so this allows us to do really fast closed form Bayesian inference given semantic segmentation images, and we do this over the entire map that the robot sees. Now, tactile sensing was a bit more challenging. So when the robot actually goes and measured these properties directly, this affects both the semantic class estimates as well as physical property estimates. And unfortunately, if we look at the family of prior distributions for this joint estimate, when we apply Bayesian inference to this tactile sensing measurement, the posterior is actually not in the same family of distributions as the prior. So we see here that the posterior estimate kind of gets pushed out of this family, and this creates two main challenges. The first is that we have to then iteratively recompute what the family of distributions of that posterior is, and this leads to an exponential increase in the number of parameters we actually need to track. So in order to avoid both of these challenges, we use the method of moments, which allows us to functionally project that posterior back into the same family of distributions as the prior. And then this allows us to do, once again, really fast closed-form Bayesian inference given that tactile sensing measurement. And so, we were primarily focused on legged locomotion in that first video, but we show in our paper that this actually, translates really well into other robotic tasks. So in the case of door opening, doors are, inherently multimodal. They're either push or pull to open, and we want to determine how much force is required to, open this door. And so the robot can have some prior estimate over the force required to open this door. We can take then a measurement of the robot actually going and, touching the handle and moving the door. And we can use this to update the posterior. And likewise, in our paper, we show that using tactile sensing, we can also improve semantic segmentation performance over vision-only methods. So if you have any more questions, please come see our poster. We have code available on our project page, and if you're interested in our method, I would highly recommend you read our paper. Thank you.
Hey, Parker. Really good talk. So one question I have for you is, how do you determine when to touch or where to touch? So you talked about with the ice that you couldn't tell visually what was the difference, right? So
yes. Yeah. So currently it's a human operator. We have in our code the ability to go and touch a region in the RViz simulation, and you can tell it to go take a measurement there. So right now it's human operators, but the next phase of this is because we have uncertainty over both the semantics and properties, we can use that uncertainty to have the robot maybe do active perception over where it should go take this tactile measurement.
Awesome. Thanks.
Here on the right.
Hey, yeah. Great talk. So one question I had was with that assumption, is it assumption, I guess, where you want your posterior to still be in the same family of distributions? What if, inherently it's not?
Yeah, so actually in this case, it isn't. Okay. So a bit, theoretically we're using the notion of conjugate priors in probability theory. Yeah. And the reason we want to use that and we want the prior and posterior to be in the same families is to have a close set of parameters we're updating, and we just can do that very, very fast, even with, hundreds of thousands of discrete elements within our map. The issue is if the prior and posterior are not in the same family, you lead to an explosion of the number of parameters that you need to update. And we show in the paper that this is actually an exponential increase. So even for if you start with 10 parameters. After you've taken 2 or 3 friction measurements, you're quickly like in the hundreds, thousands of parameters. So it gets out of hand very, very quickly and becomes computationally intractable.
Thank you.
Last question, I think.
Is it possible to use the tactile sensor on the legs and continuously getting measurements instead of on the arm? And
Yes, I get this question a lot. We just didn't have access to the legs at this point, so Boston Dynamics only very recently allowed us to do joint torque control of those legs. So we relied on the joint torque control of the arm. But yes, you can use legs in this case.
Okay, thank you for the speaker. Now let's go to the any feature vSLAM, automating the usage of any features into Visual SLAM.
Hi everyone, thanks for coming to this session today. My name is Alejandro Fontan, and I'm presenting today a work, Any Feature Visual SLAM, developed at the Queensland University of Technology in collaboration with the University of Zaragoza, in how to automate the usage of any feature into Visual SLAM. Allow me first to give a brief overview of what SLAM is. So SLAM stands for simultaneous localization and mapping. And it's the problem of a robot when it is exploring a new environment to build a map of this new environment and locate itself within that map. The video is not running, or?
Could we play the video? Anyone can help? Oh, it's running.
It's running now? It's just super long?
It's running now. We can see there.
Okay, well, so then I have more time to explain this. So I'm not going to repeat what is Visual SLAM, but we call it visual because we want to use the information from the images to perform this task. So within all the approaches that have been developed in the last 20 years for Visual SLAM, feature-based approaches have been and are still widely used. And their functioning is very simple. So as you can see on the images of the table, we extract the salient key points on the images, we match them in a multi-view setup, and from those correspondences, from those matches, we can estimate the trajectory of the robot and the 3D points of the point cloud on the scene. One strength that is worth noticing of these systems is that if we get the tracking of the features or the matching of the features accurately and robustly, we can perform SLAM for a very wide array of scenarios. As you can see on the images, we can use Visual SLAM for indoor applications, but also for outdoor applications, going even farther for extremely unstructured environments like planetary exploration, or going even more deep inside and use it for intracorporeal Visual SLAM with medical purposes. However, if we take a look at the baselines that have been developed in the last years, all of them have in common that they all commit to one specific feature, even though they have the potential to be feature agnostic, and also neglecting the fact, or not using the newest features that are available and that have the potential to be more powerful, such as Superpoint or R2D2. For that, we have developed any feature Visual SLAM. We built on top of OrbSLAM, and we have modified 6 processes inside OrbSLAM that were tightly coupled with the Orb feature to make it possible to run with any other feature. Processes like key point detection and feature matching, but also how the pipeline is using the size and the covariance of the feature in the pipeline. And we've run experiments with 6 classical feature descriptors, such as a case, brisk, but also shift, and also with the newest ones, such as R2D2. And we have run a huge bunch of experiments, and we've got some interesting results, as you can see in the corner. For example, when we use Orb to track that white column, there is no enough features, the matches are wrong or are bad, and we cannot track. But when we use R2D2, which is more powerful, we can have more correspondences, and we can successfully track even in that white, almost featureless scenario. We have publicly code available. If you want to try it, you can try the features that we have already implemented, but also you can implement the newest ones or the ones that you like yourself. We provide the scripts to do the implementation very easy and seamlessly, even the vocabulary creation, which is usually the bottleneck for these pipelines. We actively keep working on this baseline. We will make the randomized molecular, but we will make the extension to RGBD, stereo, and potentially visual inertial. So any feature is the first step for our future work. We plan to explore how we can choose a priori the feature that better give us the trade-off between accuracy and robustness for a particular application or a scenario. And the next step would be also, how can we do that online? Can we get the system to understand which feature is better for that trade-off? Or even better, if we can bring all together in the same optimization and get the best of all the features in the same pipeline. At the same time, we've been working in another project, Visual Slam Lab. This is a framework that we want to create to unify the run and evaluation of Visual Lab. So basically, the idea is that you can design your own experiments, or say, I want to run these baselines in these particular sequences and datasets, and with just one command, you will download the datasets, run the baselines there, run the experiments, get the evaluation, and get the results all with one command. And we hope that this will bring Slam, will make Slam easy to run, and it will be broadly more useful. Again, we also have code available, so if you are interested in contributing or making any questions, please check it there. It's already functioning. Yeah, that's it. As I mentioned, we have code available for both any feature and Visual Slam. So if you want to have more details or contribute or help us building this framework, please come talk to us in the poster session or find the other QTs in the room. Thank you very much.
Any questions?
Yeah, it's an interesting work. I just wonder, after you switch to another type of features, when you go back as kind of loop closer, will you be able to keep the previously observed feature, or you just ignore the previously observed feature?
Yeah, thanks for the question. That's one of the main bottlenecks for online switching of features, because features are not only used for tracking and mapping, but also particularly in Opslam for loop closure. So if we switch online the key point, we won't be able to match against the previous map if we completely get rid of the previous information. That's why the idea of combining all of them in the same image or in the same optimization, I think is very powerful, and we will be able to leverage all the information available.
Thank you.
Thank you.
And does the frame export depth features as well? Was it only RGB? And like, what is the combining RGB, RGBD?
So right now we are just running the monocular version because it was the first approach. The extension to RGBD and stereo will come in the next weeks because the way Opslam is doing it is very easy to implement. So yeah, and then for visual inertia, which I think it will be also make sense, we will take a bit more time. Thank you.
Thank you.
So let's thank our speaker again.
Thank you.
The next paper is IMESA, Incremental Distributed Optimization for Collaborative Simultaneous Localization Mapping.
Hi, folks. My name is Dan McGann, and my talk today is going to be on this paper, IMESA. Collaborative SLAM is a fundamental capability for multi-robot teams. It's classically formulated as a factor graph, and state estimates are therefore computed using a nonlinear least squares optimization. Importantly, for multi-robot teams actually deployed in the real world, we need algorithms that can solve this optimization, that are accurate so that robots can correctly plan their next set of actions, general so we can make use of all available sensing modalities, and online so that we can have up-to-date state estimates for navigation. A key challenge in collaborative SLAM is that measurements and variables are distributed across the team, and inter-robot measurements result in some of these variables being shared by different agents. As such, robots need to communicate to optimize this problem, and the need for communication additionally requires that algorithms are consistent so all robots agree on a single solution, and resilient to the behaviors of real-world communication networks. In general, prior works have struggled to achieve all of these goals. The most promising are DDF-SAM2 and distributed loopy Gaussian belief propagation, but these algorithms struggle to provide accurate and consistent results. In this work, we introduce IMESA that's designed to achieve all of these goals. We build on the batch algorithm MESA. MESA formulates the collaborative SLAM problem as a constrained optimization in which each robot solves a local factor graph enabling general and accurate solving. All shared variables are constrained to be equal to ensure consistent solutions, And constraints are written using augmented edge variables that permit distributed asynchronous behavior. MESA solves this using consensus ADMM, where consensus ADMM iteratively optimizes the problem's augmented Lagrangian for the state, edge, and dual variables. State variables are optimized by solving the robot's local factor graph that's been augmented with biased priors. Edge variables are solved simply by interpolating local state estimates whenever there's communication. And dual variables are updated to tighten constraints over time so that robots converge to a consistent solution. On real data, this process looks like the following. Robots quickly optimize their local graph, and over time, communication allows them to utilize information from neighbors to improve their local estimates and converge the problem globally. However, MESA is a batch algorithm. It can take hundreds of thousands of iterations to converge, making it very, very difficult to run online. To develop a solution that can run online, let's look at the constraints of an incremental problem. We assume that at each time step, robots' states change, they take new measurements, and they need to quickly update their SLAM solutions. At this time step, they also have the chance to communicate with a single other robot. We assume that this communication is range limited and can randomly fail. The communication model that we're using is pessimistic, but representative of what robot teams may experience in field deployments in places like disaster areas, remote wilderness, or outer space. In this work, we adapt MESA to function within the difficult communication model that I just outlined. An iteration of MESA can be broadly broken down into two steps, a local optimization step and a communication step. The biggest bottleneck of this process in the incremental case is that communication is very limited. The key idea of iMesa is to amortize this algorithm over time as communication is available. This is enabled by three insights. First is that the communication step is asynchronous, so pairs of robots can communicate opportunistically. Second, MESA converges relatively quickly, meaning we can get good solutions even when this process is amortized over time. Finally, the communication step only requires that we have access to a solution. It doesn't prescribe how we compute it. Because the local optimization is formulated as a factor graph, we can leverage existing incremental solvers like ISAM2 to quickly update our solutions. So to summarize this process, we use ISAM2 to incrementally incorporate new measurements and solve the local optimization. When communication is available between robots, they only need share their estimates to any shared variables to update and tighten constraints. Here, tighter constraints are shown by darker purple. When new shared variables are introduced, we can update their constraints in all the future iterations. And these steps, along with a parallel bookkeeping process, make up the entirety of the algorithm. Here we can see the algorithm in action on a synthetic data set with 5 robots. You can see that iMesa is able to achieve accurate results and outperform prior works. This is an example of a larger set of experiments that we ran that evaluated iMesa across different scenarios like different problem conditions, different team sizes, and different durations of operation. In all of the scenarios, iMesa is able to achieve the closest solution to that found by a centralized solver. We can additionally see that iMesa is very efficient. It can achieve nearly the same efficiency as single robot ISAM2. And since we're familiar with this algorithm's ability to run in real time in real world deployments, we're optimistic that iMesa should be able to do so as well. Finally, we demonstrate our algorithm continues to provide quality results even on real world data, like on this data from the DARPA Sub-T Challenge. So to conclude, in this talk, I presented iMesa, a distributed incremental optimization algorithm for collaborative SLAM that's able to provide accurate and consistent solutions to general SLAM problems within online runtimes and under very limited communication. If you'd like to learn more, please stop by our poster, and thank you all for your attention.
Questions?
Hey Dan, excellent talk. Really, really good work. One question I have for you is how limited is the communication? Because if you have underwater vehicles, it's like bits per minute, right? So I'm just wondering about how much data do you actually have to send between vehicles?
Yeah, this is a great question. Unfortunately, there's never a single answer. What I can tell you is that the communication is proportional to the amount of variables that are shared between robots. So this can be limited by a number of engineering decisions, like the amount of past states that you choose to marginalize out. And so there's a lot of flexibility in kind of the amount of data that you can restrict given your problem conditions.
Okay, and then is that communication two ways at every point in time where you're trying to share data?
Another great question. Yes, so the assumption is that all communication is bidirectional, so 2 robots need to pass information both back and forth to maintain the algorithm invariance.
Awesome, thanks.
Thank you.
Nice talks. I wonder if the ADMM is the best choice of distributed SLAM.
It's a great question. So I won't try to stand up here and claim that it's the best choice, but from all available evidence, it seems to be a really good option. You know, I'm hoping that one day someone thinks up a great idea that blows this out of the water, right? That's always the goal of research. But for now, it seems that this method seems to perform very well, and I'm excited just how well it can perform in real-world deployments.
Okay, the ADM may take many iterations to convergence, so that's my idea. Yes, thank you, thank you.
Thank you.
So we're a bit behind of schedule. Sorry about that. Let's move on to the next talk. So the next talk is scalable distance-based multi-agent relative state estimation via block multi-context optimization.
Hello everyone, my name is Tianyue. I'm honored to present our work about scalable distance-based multi-agent state estimation. This video is of a 700 Jones formation light show. This achievement, however, is under the shade of some external localization devices. The natural question is that, can we achieve state estimation at scale using only onboard sensors? To achieve this, some hardware configurations are worth considering. However, they all have some fatal flaws when deployed at the large-scale system, as shown in the slide. In our work, we considered the distance-based setup, considering they are more scalable, including distance-only setup and the distance proprioception setup that also takes attitude measurements as input. This is a tiny example of the system where a single agent can be equipped with multiple distance sensors to estimate the force state. Especially, we use a quadratic measurement model of distance measurements, which can be derived from the primal distance measurement. Then we can formulate the MLE problem according to the topology and the model of measurements. We know that some components of the rotation is measured via proprioception depending on the specific sensor setup, for example, using the 4-axis MU. However, this problem is hard to solve effectively since it is very high-dimensional and non-convex. In particular, semi-definite realization methods where robust to initial guesses are centralized and not scale well. Moreover, they are not tight on the noisy measurements, requiring further refinement, which can be inefficient and struggles on a non-convex landscape. The main idea of our solution are one, a reformulation of the problem called generalized graph realization, and two, decomposable and multi-convex optimization models that can be solved in a distributed manner using block coordinate design. The rule of the generalized graph realization is to transform the solution space from a rigid body state to point coordinates. This is very natural but effective. The relevant statement in the paper justifies doing so. We can rewrite this formulation as a rank-constrained semi-definite conic programming. That is, if we drop the rank constraint, we get a convex programming. However, we want to solve it as it is not scalable with a very large con constraint. Instead, we employ a further realization of it. The motivation of doing so is to use block coordinate design on a specific structure called block multi-convexity. This helps us to raise convergence guarantee and scalable solution and efficient solution implementations. The realization model is called age-based semi-definite realization, where the large con constraint is decomposed into its principal submatrix with some necessary modification. This results in an optimization model called encode ESDP. With some specific block division in BCD, we get subproblems that are strongly convex and with constraints only between neighbors. We also derive a multi-convex refinement model to refine the solution by the first method, and the subproblems has closed form solution. The theoretical properties of block multi-complexity can be applied to guarantee convergence to critical points. We simulate our methods in large-scale systems as visualized in the pictures. When using the local search method standalone, we found that the proposed methods are more robust and more efficient than other methods. Both in distance proprioception and distance-only setups, we demonstrate that the proposed method can be more or fairly accurate compared to the straightforward SDP methods and other specialized methods. Then to the distributed and parallel nature of BCD, the runtime of proposed method can be invariant to the scale of the system. Other realization methods fail to perform in a scalable way. We also conduct an experiment that includes the real-world data. If you want to know the details, please phone me while the post time. Thank you.
Questions?
Thank you for your talk. Sorry. So for your formulation, is it a relaxation or like just a reformulation? So for the like multi-block, multi-convex formulation, is it like a SDP is a relaxation or like another reformulation?
Yes, it is first a reformulation and then a relaxation.
Okay. So the final relaxation is still to solve SDP or like another like convex problem, like a decomposable convex problem?
Yes. The realization is also a convex programming, and each sub-problem is a strongly convex SDP.
Okay. But it is like decomposable, right? So you can decompose it to like a multiple smaller cones?
Yes, exactly.
Okay. So in your graph, your graph is code or like have other structures, or you have to relax it when after your reformulation. So the original graph of your
and the original problem has a Euclidean distance matrix. It is convenient to first reformulate it and then relax it. Yes, that's my opinion.
Thank you.
Okay, we have time for one quick question.
Hi, thank you for the talk. So after you solve the convex relaxation, do you obtain tight solutions, or do you have to do some kind of local rounding or something like this to obtain feasible solutions?
The solution of the first relaxation is not a feasible solution. And then we employ a very fast refinement stage to get critical points of the original problem. Yes.
And can you comment on how you do that, that rounding towards the end?
We first solve a relaxation problem and get an initial guess, and then put this initial guess into the second stage, the refinement model, to get the final solution. Yes.
Okay, thank you.
Let's thank our speaker again.
Thank you.
The next talk is experience-based multi-agent pathfinding with narrow corridors.
Hi, everyone. My name is Rachel, and today I'll be talking about our work, experience-based multi-agent pathfinding with narrow corridors. So multi-agent pathfinding is the problem of finding collision-free paths for several robots that are operating in any discrete environment. And this problem has many applications, including things like robots that are operating in a warehouse. So most planners solve this problem by first planning decoupled paths for every robot, and then resolving conflicts locally. Classical methods, however, are usually too slow when it comes to challenging problems such as high numbers of robots or environments that contain narrow passages. One way that we can get around this complexity issue is to use something called experience. So experience-based planners resolve conflicts by querying a database of solutions. An example of this is called DDM. So DDM has access to a database of exhaustive solutions to every possible 2x3 or 3x3 problem. So when a conflict occurs, DDM simply takes one of these two subproblem templates and places it over the conflict, and then it resolves that subproblem by querying their database of exhaustive solutions. So in this way, DDM is able to resolve any conflict that occurs in a obstacle-free 2x3 or 3x3 section of the grid. And this algorithm works very well. DDM offers significant speedups over classical methods because querying the database takes fractions of a second. However, since DDM only uses these two subproblem templates, it's limited to environments that have a lot of open space, such as the warehouse environment shown here. You can't use DDM on any environment that contains any type of narrow passage, meaning only one robot can pass through that space at a time. We present an experience-based planner that can handle environments with narrow passages of width 1 or doorways. Specifically, our contributions include a new subproblem template called the 5x2 that you can use to resolve conflicts in doorways. This new template, however, is only solvable for a maximum of 6 robots, so we also introduced the notion of subproblem capacity constraints to prevent these doorways from becoming overcrowded. Lastly, we also introduced new conflict resolution strategies that result in fewer waiting steps per robot and final paths closer to the optimal decoupled path. Our algorithm works the same way as DDM at a high level. So first we plan decoupled paths, and then we resolve conflicts locally by using subproblems. So this is an example of a conflict. So the robot's current positions are shown in solid circles, and their next desired cell is indicated by an arrow. And as you can see, the purple and green robots is about to collide, so we place a subproblem shown in blue to cover that conflict. Once we place that subproblem, we have to assign temporary goals to every robot inside of it in order to query the database later. And our goal assignment is prioritized. This means that robots further from their final goals are assigned goals on their desired or decoupled path. So once we have these temporary goals, we can query the database. Our database is exhaustive. We have every possible solution. So we provide the starts and goals as shown here, and the database will give us back collision-free paths for all the robots. Now, as I mentioned earlier, our new subproblem template is only solvable for 6 robots. If there's more than that, we can't solve it. So to prevent doorways from becoming unsolvable, we use waiting. So here, for example, the red robot wants to enter this doorway, but there's already 6 robots there. So the red one will have to wait until there's space there for him to proceed. So not only does our algorithm work on a wider range of environments than DDM, we also find that our work results in fewer waiting steps per robot and final paths that are closer to the original optimal decoupled path. And this is a result of our new conflict resolution strategies, such as the goal assignment. Our work also scales better than classical methods. So conflict-based search failed 17 out of 20 trials on this very difficult environment with lots of doorways. Our planner succeeded all 20 times. So overall, we present an algorithm that offers the same scalability as prior experience-based work, while extending to a wider range of environments. In the future, we'd be interested in exploring how we can use this new subproblem template to extend to long, narrow passages by extending that. And then we would also be interested in looking into how we can use experience in the continuous space. Thank you.
Thanks for your talk. Could you comment on completeness and optimality of your approach?
Yes, so we don't prove any completeness or optimality. So we didn't make any comments on that. DDM makes an argument that it's close to optimal because when you do these problems, you deviate very little from your original optimal decoupled path. So you can make that argument, but we don't make any claims about that in our paper.
Okay, I have a second one. Can you comment on your choice of 2x5 Why not anything else?
So we chose the 2x5 instead of something bigger because when we generate this database, we need to find solutions to every possible problem, and that can take a long time. So we didn't want to make it too big, and we thought that this would be one that was useful enough while also being manageable enough for us to make a database with all the possible solutions.
Any other questions? This one there.
So I guess your database has a lot of symmetries in there.
Yes.
Do you have some way of compressing those?
Yes, so when we made the database, we account for all the symmetries. So we can rotate the subproblem a few times and also flip it and rotate it. So we don't actually solve every possible subproblem. We solve every possible in counting for symmetries. So it takes a lot less time and takes up less space.
Yeah. What's the compression factor of this?
I don't know exactly. You can come to our poster. I have the numbers on the poster, but a lot smaller. Yeah. I think that the 3x3, we exploit up to 16 symmetries, so it's 16 times smaller.
Let's thank our speaker again. The last paper in this session is event-based visual inertial velometer.
Hi everyone, my name is Joey, and I'm going to present our work, Event-Based Visual Inertial Velometer, a joint research project from Hong Kong UST and Hunan University. Vision-based state estimation, also known as visual odometry or SLAM, is a fundamental problem for mobile robots. However, its applicability degenerates in high-speed scenarios due to the limited sensing capability of standard cameras. This challenge poses inevitable demands for advanced sensing principles that can perceive the scene dynamics effectively, and also for compatible algorithms and software. Neuromorphic event-based cameras are biologically inspired visual sensors with asynchronous pixels and extremely high temporal resolution. And such favorable properties make them an excellent choice for solving state estimation tasks under aggressive ego motion. Nevertheless, failures of camera pose tracking are frequently witnessed in state-of-the-art event-based visual odometry systems when the local map cannot be updated in time. So to resolve this issue, prior works resort to visual inertial fusion or feature-based method. But one of the biggest roadblocks in this specific area is the absence of efficient and robust methods for data association without imposing any assumption on the environment. However, this problem seems unlikely to be addressed as in standard vision due to the motion-dependent observability of event data. And all these issues drive us to think about the following question. Is there a more rational design for an event-based visual inertial system that is more consistent with the differential working principle of event cameras? And to answer it, we propose a novel design of state estimator, which exploits the differential working principle of event cameras, and it recovers the first-order kinematics, namely the instantaneous linear velocity, by fusing events and the inertial measurements. So our method goes like this. Giving us input the raw events from a stereo event camera and the measurements from an IMU, the goal is to recover the instantaneous linear velocity in metric scale. And the front end computes the normal flow and the depth information respectively from the input events. And to this end, we provide a rigorous derivation for computing the normal flow from the spatial and temporal profile of event data. And as for the depth estimation, we simply apply a static stereo matching method. Our backend considers the synchronous property and high streaming rate of event cameras. Yeah, so basically we just proposed a continuous time pipeline which can handle the asynchronous event data and also can establish the data association with temporally non-aligned measurements from the accelerometer. And specifically, the objective of this task is to fit a cubic B-spline in the velocity domain that simultaneously satisfies the following two criteria. The first one is that the predicted normal flow must be maximally consistent with the normal flow observation. And the second one is that the first order derivative of such a B-spline must maximally comply with the acceleration measurements. So to evaluate our method, we use an event camera simulator to generate sequences which feature the aggressive maneuvers of a drone. Basically, two synthetic scenes are generated, including a circular corridor, as you will see, in which the drone undergoes a high-speed detour, and the second one features a drone traveling through randomly distributed boxes. And we compare our method against several alternative solutions that can determine the linear velocity, and the results show that our method outperforms others in terms of both absolute and relative velocity error. Besides, we also perform evaluation using some self-collected real data, and as you can see in this video, the accurate linear velocity recovered by our method leads to better trajectories in terms of a global consistency, indicating that our method is a better solution to the problem of dead reckoning. So that's pretty much about my talk, and we hope that our design can inspire future research in this specific area. So if you feel interested, please stop by our poster. Thank you.
We have time for one quick question. Okay, maybe I can ask a question if there's no audience question. So what is the limitation of this work?
So the limitation, as far as I see, there are basically two of them. The first one is that the measurements cannot go beyond the measurement limits of the IMU. So if it fails, okay, the system definitely failed. And also the performance of our system is quite relying on the quality of the normal flow, which is a visual input. So we do not explicitly explain how much texture must exist in the environment, but vision-based method, we must have some textures which can induce the brightness changes somehow can be used by our method. Yes.
Great, thank you. Yeah. So this concludes the session. Let's thank all our speakers again. The next session is locomotion and manipulation.
Titled Locomotion and Manipulation. We have our first speaker, Rethinking Robustness Assessment, Adversarial Attacks on Learning-Based Quadrupedal Locomotion Controllers. Are we good to start?
Sorry, not this one. Yeah, our title is Rethinking Robustness, so not this video.
Yeah, it's the wrong video.
Yeah. Okay, yeah, this one. So, hello everyone, thanks for waiting. I'm Fan Shi.
And I'm Cheng Zhang.
Here we are talking about our paper, adversary attack on the state-of-the-art reinforced learning-based locomotion controller and won DARPA's robotic challenge. So locomotion become more and more robust and complex with the advance in learning-based methods. However, being black box, we still do not know how to evaluate the worst case of this learned policy. One important but missing part is safety validation, which leaves huge risk before the large-scale deployment in the real world. Meanwhile, being long-tail and time-sequential, failure cases such as falling over are becoming more and more difficult to identify. Finding the failure case is non-trivial. We first demonstrate 4 standard testing methods are difficult to find the failure case, even on a very naive open-source reinforcement learning controller. Expert intelligence is also difficult. We invite 100 robot experts around our department. Only 3 persons could successfully find a failure case on this trivial IR controller. Therefore, we think computational method is critical. We propose reinforcement learning to learn the adversary sequence. It falls over the robot with shorter survival time and higher falling velocity to cause larger damages. It could also fail the state-of-the-art, very robust DARPA subjective learning controller, even on the simplest flight terrain. Our adversary outputs are the robot velocity command and additional state estimator error, less than 0.5 meter per second and 3 degrees in row PGL angles. All of these settings are reasonable and realistic in the real world. We did a lot of tests to show the failure case found in simulation could be trusted and transferred in the actual robot with similar behavior. Do we really identify the weak spot? The adversary agent with perceptive information could actively leverage a terrain feature to smartly fall over the robot. So we leverage the expert domain knowledge based on the ground truth data to decide the range of the adversary noise to be reasonable. Meanwhile, we use techniques such as Lipschitz laws to generate the mild output to approximate the realistic failure scenarios. After identifying this failure case, we can further retrain the previous controller to improve its robustness to close the loop.
And here on the left is our original controller, and it can fail under very challenging scenarios. And on the right is our fine-tuned controller from our learned adversaries, and it shows more robustness. And here we conducted a lot of stress tests with malicious commands and perturbations and also changing terrains. And here we did more and more stress tests. And okay, more tests. Yeah. And we also did a lot of field tests, and due to time reason, we cannot show all of them here, but you can come to our poster session to watch them. And our method is not limited to any specific robot platform or controller, and here we also show that we can work on an MPC controller on an A1 robot. And we can adjust our reward function to help identify different and diverse failure cases, such as talk over limits and falling over, and also self-collision. And the main takeaways of our work are: first, attacks can be used to evaluate the robustness of different policies' worst-case performance. And second, multimodal attacks are stronger than single-modal ones. And third, the commonly used domain randomization cannot guarantee the safety against attacks. And fourth, our adversaries can leverage terrain features. And fifth, learned adversaries can be complementary to our human intelligence. And the limitations of our future work will be that our current method is not suitable to generate very high-dimensional attacks. And although diverse failures can be identified, we cannot theoretically guarantee to cover all of them. So we have some follow-ups on this. And one more thing, our method can also be generalized to dexterous manipulation and navigation, and more details can be shown in the poster session. And thank you for your attention.
Questions?
Hi. For the stress test that you guys were doing, how were you quantifying like failure in that case?
Okay, so thanks for the question. Your question is how to quantify the failure.
Yeah.
Okay, so first I want to say how we define the failure. So our definition is based on the physical hardware. So one case is like robot fallover, other case like the talk over limitation and also self-collision. So that's our definition. So in order to do it, we train another reinforcement learning agent to generate the adversary sequence of like sensor noise and also the command of the robot, and in order to achieve the objective as we mentioned before. Yeah, so that's how we train it.
Yeah, and during the robot test, so for there are two kinds of tests. The first kind is that we can like control what our adversaries are. It's based on our command on our like state estimation noise. We can manually add some noises, so we can control this adversary and make it fall. And the second type is like humans adding more perturbations on the robot, but this is kind of hard to control. But we ask our like testers to try to control it, and generally we found our control is more robust. Yeah.
Okay, that makes sense. Thank you.
Thank you. Maybe one more short question.
So what is the sorry? What is the loss function? Is it a sparse reward that failure is seen, or do you have to do some reward engineering for the RL for failure discovery?
Yeah, that's a great question. That's a great question. So the question is like, because it looks like very sparse reward, so how to trigger such kind of termination case? Yeah, so I and a colleague, so first I think termination reward is very important. And meanwhile, my colleague developed some kind of dense reward like angular velocity and yeah, maybe you can.
Yeah, like here we define different auxiliary rewards for different like failure cases, but we have only one major term, that's only the Boolean failure reward, and in total we have fewer than 5 reward terms, so there is no much engineering here.
Yeah, and one more important thing in our last two slides is like, if we change the weight of each reward term, we will trigger diverse failure case, because each term will related to kind of different failure scenario. And more detail you can check in our poster, and we are welcome for more discussion on this. Thank you.
Thank you. Let's thank the speakers again. Our next talk is Advancing Humanoid Locomotion, Mastering Challenging Terrains with Denoising World Model Learning.
Hello everyone, I'm Yan Zhen, and this is Xin Yang. Today we are happy to share Denoising World Model Learning, DWL. Our work makes humanoid robots to work across challenging terrain using zero-shot end-to-end reinforcement learning. Robot locomotion is a fundamental skill for humanoid robots to effectively perform daily tasks. For humanoid locomotion, previous study typically focus on model-based control, such as zero moment points, model predictive control, and so on. However, this approach relies on the accurate modeling of nonlinear dynamic system, which is very challenging. On the other hand, reinforcement learning became popular. This method involves creating numerous simulated environments and train policy in parallel before transferring them to real robots. However, the sim-to-real gap remains a significant problem for IO-based controller due to the mismatched dynamics and physical properties between simulation and the real world. So previous work has only allowed humanoid robot to work on some simple terrain. Therefore, in this work, we focus on designing RLO-based controller. By analyzing the cause of the RLO sim-to-real gap, we have further improved this issue, enabling humanoid robot to work on more complex surface. So, what factors lead to sim-to-real gap? I believe this factor can be categorized into 4 types of noise. First, environmental noise, which comes from the external environment, not the robot itself, such as the external forces and terrain changes. Second, dynamics noise. Accurately simulating real-world dynamics is invisible, resulting in oversimplifications. For example, approximation of ground friction and object deformability. Third, sensory noise. Physical sensors inherently contain measurement noise, such as IMU drift and inaccuracy in joint position and reading. The last one is masking noise. Some information may be unobtainable in reality due to the absence of specific sensor on the robot, such as the linear velocity and contact force measurements. And we believe that all the above type of noise will be reflected in the robot's observations. Based on this motivation, we propose denoising world model learning. This diagram shows the information flow from sensory input to action output in both simulated and real-world setting. Raw observations are created by adding masking and domain representation noise to privileged information, encoded into a latent state, then decoded to reconstruct the true state through denoising. The encoder process observation history followed by policy learning and predictive model deployment for robust locomotion via the MLP decoder. This architecture integrates privileged information into the state representation, enhancing performance and generalization. This is our indoor experiment. These 4 clips demonstrate the robot's capabilities, working on slope and stair, and resisting interference from dynamic terrain. The video in the lower right corner offers a close-up of the robot footstep. Our OLO policy also enables the robot to work outdoor in the snow, which is a very challenging task. Besides the deformability of the snow, the robot must also manage the high risk of sleeping. We also verify DWLO on another full-size humanoid robot with high degree of freedom. In addition to slope and steps, we also test deformable carpet with slope and irregular rise terrains. To test the robustness, we give the robot some external force, dynamically add a 10-kilogram dumbbell, and let the robot push a 60-kilogram me. I hope the above video clearly illustrates the effectiveness and robustness of DWLO. And thank you for your listening. If you are interested in DWLO, feel free to visit our poster for the detail. Thank you.
Questions? Hi. Did you quantify the performance of your policy without this denoising process?
Yeah, we have some quantified result on our poster, but we don't show here. In our quantification, our successful rate is almost 100% compared to other methods, so it's a pretty robust policy.
Hi, thanks for the talk. And I'd like to ask about, like, in the future, if you want to make a perceptive controller, then, like, when you walk and some new terrains will appear, so it is not controlled and it's also some kind of unexpected terrains. So do you think you should denoise them or should have some more tricky designs?
Yeah, when you consider perceptive RL, you need to add the perceptive, maybe the depth image or the sky height into the observation. So when we, in this area, the denoising process is like you have a noisy sensor input, like a noisy depth camera, and your denoising object is a ground truth depth camera, and this is really useful. We have some future work on this, and we successfully climbed the Great Wall by this method. Yeah.
I understand the sensor noise part, but the problem is, like, when you are talking about denoising, you're talking about some, like, you're denoising the MDP part that you cannot control right. So, like, when you are doing locomotion, you are moving over new terrains. So when you make one step forward, you can see new terrains. So these new terrains are also not controlled by you. So do you think it should be denoised, and do you think you should have some further designs for it.
Yeah, thanks. So our denoising process is based on the observation history, and we denoising current state. So we are not like a prediction model or a dynamic model. We are just like denoising the state from the observation history. So we don't have action involved or the future involved. That's one advantage of method, because we don't need to predict the future. And as everybody knows, prediction future is really, really hard. Thanks.
Thank you. Let's thank the speakers again. The next talk is titled Agile but Safe, Learning Collision-Free High-Speed Legged Locomotion.
Okay, thank you. Yeah, let's start. Yeah, it's me again. I'm Cheng Zhang from ETH Zurich, and I'm here presenting our work with CMU, Agile but Safe, Learning Collision-Free High-Speed Legged Locomotion. So leg robots are often used in urgent situations like search and rescue or disaster response, where the time is very crucial and you need them to move very fast without collisions. However, like existing works can show a huge gap between how fast the robots can move and how fast the robots can safely move around obstacles. So if we don't have obstacles, it can move about 3 meters per second. But if we want some safety, it's typically bounded by 1 meter per second. So our work allows a Go1 robot to move above 3 meters per second at the peak speed around obstacles in the real world. So the first question is, how can we improve agility around obstacles? In existing works, this is often achieved by decoupled locomotion and collision avoidance. That's to say, a high-level planner generates collision avoidance plans and then a lower controller checks these velocity commands. However, this makes the locomotion controller unaware of collision avoidance and also the planner uncertain about the checking performance. Hence, the planner must be very conservative to ensure safety. Also, some works use model-based optimization where high-speed running can lead to things like model mismatch or constraint violations such as slippage and also high computational burden. And what's our solution? First, we learn an end-to-end controller that maps observations directly to joint outputs and help the robot reach a goal rather than track the velocity. Second, we use model-free reinforcement learning to learn real-time and agile motions. To train such an agile goal-reaching policy, the observations include proprioception, exteroception, and goal commands. The policy outputs joint touches, which are then checked by multiple PD controls. The rules are dominated by 3 terms: the goal-reaching term, the velocity maximizing term, and the collision avoidance. And this can lead to a very agile policy that can also avoid some obstacles. However, as you can see, safety is not guaranteed here. Hence, we use the agile policy only when it's safe. And for the risk cases, we have another recovery policy as a shield, which maps proprioception and twist or velocity commands to joint touches. And this recovery policy is trained to track twist commands as fast as possible. And we have another reach avoid module to tell when it's safe, and also search for the optimal twist command to recover safety. This is based on value network to predict whether the agile policy alone will inevitably fail, and with guarantees from attributability analysis. So if the predicted value is close to positive, it means we need recovery. And to find what is the optimal twist command, we assume that the robot can accurately check the twist command. Then the optimal twist should bring the robot closer to the goal while staying safe based on our value function. And this can be efficiently solved by gradient-based methods. And to enable collision avoidance with onboard sensing, we use a low-dimensional exteroception representation, the sparse rate distances. And for deployment, we train another rate prediction network to map depth images to these rate distances. And to this end, we further collect some labeled image and rate distance data in simulation with different objects. And then we can train this prediction network with very mature CV techniques such as data augmentation. And what are the benefits of such a low-dimensional design? First, we can learn the controllers and the reachable values very efficiently. Second, it's highly interpretable. And third, we can handle high-dimensional image noises with supervised learning rather than leaving this burden to RL. And here are some real-world demos. So ABS is very agile. Here, the green light means it's using the agile policy, and the red light means it's using the recovery policy. And it's also very safe. And it's very robust, especially when carried the payload of its own weight. And we open sourced our codes, and here's our paper and website, and you can visit our poster session for more information. Thank you.
Hi, thank you for the very cool talk. Over here to your right. So something that I'm wondering is, you're using reach-avoid analysis to predict when your agile policy is going to inevitably fail, and then you use this recovery policy to hopefully save it from failing.
Yes.
But what happens if you get into a state from which your recovery policy is also going to fail? And so your reach-avoid analysis says, hey, careful, your agile policy is going to fail from here, but it turns out that your recovery policy is not good enough to save you from
Yes, that's always a problem.
crisis.
So the problem is like our agile policy is not aware of the capability of the recovery policy. So currently we are doing some follow-ups. The first thing is that we can make these modules more adaptive. The second thing is that we are trying to make it as a whole entire thing that are aware of each other, so it can be more adaptive and more safe.
So quick follow-up, could you just do the reach-avoid safety analysis for the recovery policy instead, and then intervene with your safety filter when failure to do so would mean that the recovery policy wouldn't be able to save you anymore?
Yeah, but it's kind of like a chicken and egg problem. Yeah, so currently it's very hard to save.
All right, thanks.
Thanks. Let's thank the speaker again. The next talk is RL2AC, Reinforcement Learning-Based Rapid Online Adaptive Control for Legged Robust Locomotion.
Hello everyone, my name is Shang Ke. I represent all the courses, Xin Rang, Han Zhao, Hong Yin Zhang, Peng Xiangding, and Donglin Wang to present our work on IO-based locomotion control by using online adapt mechanism. So first, let's look at this control framework that is widely used in IO-based locomotion control. The policy generates an action and send it to the PD controller. Normally, for PD control, it's supposed to well check the given command. Well, we found that it's different in our case. Specifically, for PD checking error of our policy, in the leg swing phase, the PD can check the given command well indeed. While in the stand phase, there's always a position gap layer. We also found that on different terrains, the position gap is also different. So we wonder why this happened. Does this position gap represent something? If we look at the system dynamics model, when the robot walks on the different terrains, it results in different reaction force. So this naturally leads to the idea that whether there's some connection between the position gap and the ground reaction force. So another observation is that in model-based control framework, you also use a PD controller. Well, PD control now is asked to well check the given command, no matter in swing phase or stand phase. So what's the difference here? So it is worth to note that in model-based control framework, it designs a feed-forward item that is used to regulate reaction force. Whether our policy do a similar thing and regulate contact force by changing the position gap. To figure out this, we design a test and we change a policy to work on the rough terrain. Due to the change of terrain, the robot may receive different reaction force. So we measure the contact force and calculate the corresponding position gap. Then we found that they can well match each other. So this implies that I'll try to then a good representation of the ground reaction force and regulate it to keep the robot to move stably. Hence, this provides a way to compensate additional reaction force based on such representation without conflicting with our policy, similarly like the regressive-based adaptive control, so as to improve its performance against the unknown environment. Hence, we propose an algorithm called IO2AC that combine the IO and the adaptive control together. Adaptive control is mainly used to compensate the mismatched model or uncertain kinetic force. The adaptive control part can run in 1000 Hz much faster than IO policy. So this enables the robot to quickly react to the dynamic change. Second, it does not require a training and can be directly used when the policy deployment. We can target several simulation and experiment to verify the performance. First, we tested the performance against a heavy payload. As seen from video, when now the adaptive control, the center mass of the robot is pressed down by the heavy payload, and the proposed method can handle the heavy payload better since the adaptive control can generate torque to compensate. Then we did another test to verify its performance against out-of-distribution data. We manually add an additional torque disturbance to one leg. Such configuration is never seen during training. The post method still demonstrates better performance over the baseline. We also directly implement our proposed method on a real robot. We put a shape on the robot base to intentionally enlarge the center-real gap. So the existence of lateral torque on the robot base results in the robot deviating to a lift, while the proposed method can ensure the robot to move straightly. Due to the friction, the center-real gap is more serious under a slow speed motion. So when now the proposed method, it observes that the back leg of the robot forces the front leg to move forward. This is also clearly shown in the figure. So in contrast, the robot can move more smoothly by using the proposed method. Eventually, we tested the proposed method on the front configuration and the terrains. The improvement of the command checking is obvious. So thank you, that's all my presentation.
Questions from the audience? If not, I might ask, could you comment on some of the limitations of combining this RL and adaptive control?
Okay. Currently, for this method, the performance when you need to deal with the time varying disturbance is limit. I mean, since the adaptation, as we know, for the adaptation, we need some P condition, but here to converge but here we cannot guarantee that. So for the time varying disturbance, the performance is not very good.
Thank you. Is there one more question from the audience? If not, then let's thank the speaker again.
So our next paper is humanoid bench, simulated humanoid benchmark for whole body locomotion and manipulation.
Hi, everyone. We've experienced something unique in the last year. We like to call this the humanoid summer in contrast to the AI winters. We've seen so many humanoids coming into development and soon into the market. So very exciting. But the appeal of humanoids can be summarized in this sentence. Solve human tasks in human-like environments using tools made for humans. Humanoids feature this nice perk of having minimal cross-embodiment gap with humans, but they are complex high-dimensional systems, and their experimental setups are often costly and somewhat unsafe to operate. At the same time, Sim2Real, especially in other domains, has shown very impressive results, proving once more the role of simulation in developing successful robot control policies. This has pushed us to introduce this first-of-its-kind comprehensive humanoid benchmark that we called Humanoid Bench. The main feature of Humanoid Bench is that it features a wide diversity of tasks, 27 in total, each addressing different challenges. These challenges go from locomotion, stabilization, navigation, to more complex dynamic manipulation tasks, including interesting practical applications, such as truck unloading, kitchen cleaning, and room cleaning. We feature a robot humanoid body in our simulation environment, Munjoko, for example, a Unity H1, with dexterous hands, for example, shadow hands. This way, we have no hardware limitations for addressing human tasks. And we, at the same time, anticipate the trend in the industry, where we see more and more humanoids equipped with sleek and dexterous hands. We feature a diverse set of observations, among which privileged observation, proprioception, egocentric vision at the eyes, and all-body tactile sensing with high resolution at the hands and the feet and lower resolution over the rest of the body. We also feature other robot configurations and end effectors, and we keep adding more, again, exploiting the modularity of our framework. We do not only provide simulation environments, we also provide an extensive set of benchmarking results. We benchmark state-of-the-art reinforcement learning algorithms on all the tasks, and we see that all of these algorithms really struggle on the most complex tasks. Even in a simple setup, which is dense rewards and the privileged observation. But why is that? Well, we did some experiments where we remove the hands from our humanoid or freeze their degrees of freedom. And in both cases, we see that performance increases significantly on some of these tasks. So it seems that this experiment indicates that these algorithms really struggle dealing with the high-dimensional action space of our simulation environment. How can we address this? Well, in different ways. A first option would be to decouple degrees of freedom, for example, the upper body and the lower body control. But this would sacrifice the whole body control capabilities of our systems. So we choose another option, which is to use hierarchical reinforcement learning. The key idea here is to identify a core low-level skill in the form of a reaching policy. So basically, we train this reaching policy to reach any point in space with the two hands of the humanoid. And this policy will learn to walk if it's needed to reach farther away points. Then we freeze this reaching policy, and we train a high-level policy on top of that that prescribes reaching targets to the reaching policy, and ideally we can solve more complex tasks. So the way we train this reaching policy is by simplifying the simulation environment and make it run very fast on a highly parallelized Munjoko MJX environment. We can train then a PPO policy on 4 billion steps. For 4 billion steps, it takes about 2 days, but this policy is reusable across tasks. Then we use Dreamer v3 to train the high-level policy that again sends outputs like to targets to the reaching policy. And finally, we can solve more complex manipulation tasks, as you can see here. So in summary, I presented the humanoid bench, which is a benchmark with a wide diversity of whole-body control tasks. We've shown that reinforcement learning algorithms still fail on most complex tasks. At the same time, we've seen that hierarchical reinforcement learning shows a great potential in addressing some of these tasks and dealing with the high-dimensional action spaces. We envision a lot of future research opportunities with Humanoid Bench. For this reason, I invite you to go on GitHub and try out Humanoid Bench. It is a fantastic playground for robotics research. Thank you for listening, and a huge thank you for my collaborators, too.
If there is any question?
Could you comment on the reward function design? Because some reward can make the task difficult to solve, and some, like your reward, might be not necessarily the best reward for this task. And also, when do you consider, or how would you consider the task is solved? Thank you.
Yeah, these are great questions. As I said, we provide dense rewards, and usually these rewards are a weighted sum of what really matters to solve the task. For example, a task that is about reaching something will have a combination of a stabilization reward plus a reward term that actually is related to the task of reaching. And usually these are weighted average, and what happens in the reinforcement learning algorithm training is that often there are contrasting objectives across all these terms, which makes learning very difficult. We use gym environments in our code base, so it's very easy for the community to modify rewards and propose better rewards. We just try to help the system as much as we could. The way we provide success detection instead is we kind of took great care in making sure that we can script somehow successful policies or successful tasks. and we compute the rewards that it takes to get there. And then we provide some thresholding rewards that actually represent task success.
Hi, thanks for the talk. I'm wondering if you can comment on your choice of using Dreamer v3 or other like how did you choose that versus, let's say, TD MPC2 or other model-based RL frameworks for training your high-level policy?
Yeah, we tried also TD-MPC2. What we noticed is that TD-MPC2 worked better for when we train things from scratch, while for the high-level policy, Dreamer v3 just worked better.
Great, thanks.
Okay, one last question.
Okay. Can you comment on the realism of your task about the sim-to-real gap, for instance, and if you have any idea of how it can be bring to realistic demonstration?
Can you repeat the question? There is some echo.
So sorry. The question is about the realism of your task compared to real tasks. So you mentioned.
The focus of this work was not in sim-to-real. We tried to make our best efforts, especially asking Unit3 for motor gains and things like that, to make sure that what we have in simulation is kind of realistic. We haven't really focused on transferring. The focus here was really trying to understand what are the algorithms that we want to transfer in the first place.
Last question.
Okay,
Hello?
Sorry. Okay, one last one.
Do you have human, or you plan to have human in your environment, interacting with robot?
Yeah, it would be amazing. We don't. It would be also great to have more humanoids doing collaborative tasks. This is something we're actually actively thinking about.
Okay, let's thank the speaker again.
Thank you.
So the next talk is just the video, and it's called MoCA, Open World Robotic Manipulation through Mark-Based Visual Prompting. So I guess the video should play now.
Hi everyone, I'm presenting MoCA, Open World Robotic Manipulation through Mark-Based Visual Prompting. In this work, we aim to command robots to perform manipulation tasks given free-form language instructions. Without any prior experiences, we would like the robot to solve an open set of tasks using diverse skills. Each task can involve unseen instructions and objects. Recent advances in vision language models, or VLMs, have provided us with unprecedented opportunities to solve open-world problems. With their emerging reasoning capabilities, VLMs can now understand complicated visual concepts and infer the object relationships. However, the state-of-the-art VLMs are trained for general visual question-answering problems. Without a profound understanding of the physical world and robot control, how can we employ VLMs to solve manipulation tasks? Using an affordance representation consists of a set of points, we bridge the reasoning capabilities of VLMs and the robot motions. For example, this sweeping motion can be represented by a grasp key point specifying where to grasp on the tool object, a function key point specifying where on the tool contacts with the environment, a target key point specifying where the contact is made in the environment, and a sequence of waypoints specifying the motion trajectory. These points can be predicted on a 2D image and used to specify diverse motions. The definition of the representation is also agnostic to the embodiment. To this end, we propose marking open world key point affordances, or MoCA, which employs a pre-trained VLM to predict the point-based affordances. The key insight of MoCA is to convert the affordance prediction problem into a series of question-answering problems that the VLM can solve. MoCA takes the free-form language instruction and the observed 2D image as inputs. To facilitate reasoning, A crucial design choice in Mocha is to annotate the input image with a set of marks consisting of candidate key points and a grid that divides the space. These marks help the VLM to focus on task-relevant information. Moreover, the candidate points and grids enable the VLM to solve multiple choice problems instead of directly predicting point coordinates, which significantly simplifies the problem. Mocha takes a hierarchical prompting approach. On the high level, Mocha employs the VLM to decompose a task into a sequence of subtasks. For each subtask, Mocha extracts the description of relevant objects and computes the segmentation mask. Then, a set of marks are computed based on the segmentation and annotated on the input image. Finally, on the low level, the point-based affordances are predicted given the marked image. Without any training data, Mocha can solve an open set of tasks. Examples include deformable object manipulation, interactions with electronics, tool use, articulated object manipulation, and more. Mocha can robustly solve the same task given different instructions and initial object poses, as well as various unseen objects. To summarize, Mocha bridged the VLM prediction with the robot motion using a point-based affordance representation. It generates the motion through hierarchical reasoning using the VLM, and it facilitates affordance reasoning using mark-based visual prompting. For more information, please visit our website. Thank you.
So unfortunately, we cannot do questions because the speakers are not here. So let's move on to the next, which is a collaborative planar pushing of polytopic objects with multiple robots in complex scenes.
Okay, hello everyone. I'm Zili Tom from Peking University, and I'm here to present our work on collaborative planar pushing of polytopic objects with multiple robots in complex scenes. As a fundamental skill, pushing is widely used by both humans and robots to interact with their environment, and typically used as a non-prehensile motion primitive in the field of manipulations. However, it can be hard to predict and control due to the uncertainty and the diversity in the content conditions. And this work focuses on how this pushing skill can be beneficial for low-cost mobile robots without manipulators, so then they can collaboratively pushing the polytopic objects with general shapes in the unstructured environment. And to achieve this task mentioned above, the challenges including dealing with high-dimensional searching space, the content dynamics involving hybrid reach, and the controlling under-actuated systems. Given the map and the pushing task, our method starts with a path planner like A-star algorithm to get a collision-free guiding path. And then a keyframe-guided hybrid search algorithm is proposed to generate a hybrid plan, which consists of the reshaped trajectory and the corresponding mode sequence. And finally, this hybrid plan is sent to the controller for online executing. To notice then, as the noise and mode mismatching is widely exists in the real-world scenarios, thus the replanning process is necessary to guarantee the overall performance. And one of the key modules of our algorithm is free space mode generation. And here the mode is defined as a set of content points and robot select to push the object. And to conduct the theoretical derivation, we consider a quasi-static pushing process, where the robots apply constant pushing forces in a fixed content mode. And this process results in an arc trajectory in the 2D space and the spiral trajectory in the 3D space. And to generate the most suitable modes for an arc trajectory, we defined a multi-directional feasibility estimation to evaluate the feasibility and the robustness. And finally, the mode generation is formulated as a sparse optimization problem, and which can be efficiently solved by using linear programming techniques. Furthermore, we propose the keyframe-guided hybrid search algorithm for extending the mode generation method to cluster environments. By extracting and inserting keyframes into the hybrid plan and generating a sufficient set modes for each arc, this algorithm guarantees the collision-free guiding paths, resulting paths with each arc transition allowed within the corresponding mode. To fully validate the effectiveness and the generality of our algorithm, we conducted high-fidelity simulation in the Pi-Bully simulators. And our algorithm was tested with various types of object shapes and various types of the map scenarios, consistently demonstrating a high success rate and robustness against noise. Furthermore, to assess the scalability of our proposed method across different fleet sizes, we conducted several tests involving a task of pushing a T-shaped object using 1, 2, 4, 6, and even 40 robots. And interestingly, even a single robot can complete the task, albeit with the highest number of mode switches and the highest time. Conversely, when employing more than 6 robots, no mode switches are needed. And we also test the 60 pushing of the L-shaped object with 4 and 6 robots in a non-gravity 3D space. And due to the increased degree of freedom, a greater number of robots is necessary for the stable pushing in the 3D space. And finally, we test pushing of the rectangular and L-shaped object in the real-world scenarios, demonstrating results consistent with the simulation. Okay, that's all. Thank you.
Thank you, speaker. Any question?
Very nice work. So if I understood correctly, it seems to be centralized.
Yeah, it's centralized.
So do you have some thoughts on how could we make it distributed among the different robots in the team?
Well, this algorithm may not be transferred to the decentralized version because we have to plan a centralized trajectory for the slider, and maybe the control part for the robots can be decentralized. But we have to plan a trajectory for the slider and which is known to all the robots.
Mm-hmm. Okay, thanks.
Okay.
Hello. What are your thoughts on extending this work to kind of like object-on-object contact? So if like I'm pushing the sofa, then the sofa is pushing another sofa, and like you considered multiple robots, but are you thinking of considering multiple objects and object-on-object interaction, as well as object-on-environment interaction? Like I push it and it slides against the wall. These kinds of things. Thanks.
It's part of our future work, and we want to do this multi-object, multitask in our journal version. Okay. Thank you.
Thank you. This is it's interesting. I'm curious, you mentioned noise, but I'm curious if you can say more about that, because there is a fair amount of indeterminacy about these kind of pushing operations. And how are you thinking about that, and how do you factor that in?
Okay, well, actually we use a simple way to add the noise to the slider. In our experiment, we add a velocity noise, such as I give about 0.1 meters per second distributions to the slider's velocity with a frequency of 10 per second. And our algorithm can work well with this modal noise. And we also test our algorithm with observation noise about 0.1 meters per second velocity estimation error of the robots. Okay.
Any other question? Okay, one last one.
Hi, thank you for the talk. So I'm curious, after you plan the position trajectory for the object, you do the contact mode planning. How do you get around the the bilinear constraints, where you have the products of like contact locations and contact forces? Thank you. I mean, you said you solve it using linear programming, so I'm just curious how you make it, or how you get around the non-convexities.
Okay, well, the linear programming is only for the mode generation, and I can give you more details about it. We actually calculate about 40 optional content points around the object's edge, and we allowed each point to give a content force, and then we will have we use a linear programming to calculate the weight at each point and select some content points from this optional content point set with the weights and calculated by the linear programming. Okay.
I see. Thank you.
Okay, let's thank the speaker again. And we move on to the last talk of the session, which is Automate, the specialist and generalist assembly policies over diverse geometries.
All right. Hello, everyone. We present Automate, specialist and generalist assembly policies over diverse geometries. This work is a collaboration between University of Southern California and the NVIDIA Seattle Robotics Lab. Here we briefly summarize our previous works. In Factory, we presented simulation methods and robot learning tools for context-rich interactions, enables faster than real-time simulation for efficient policy learning, which we demonstrated for robotic assembly. And in industrial, we presented a set of algorithms, systems, and tools that enable effective simulation-based policy learning and a successful zero-shot sim-to-real transfer on a small number of assembly tasks. In Automate, we focus on learning specialist and generalist assembly policies that can solve a much wider range of assemblies and demonstrating zero-shot sim-to-real transfer over such a range. We define specialists as part-specific policies that can solve one specific assembly, and generalists as a unified policy that solves multi-assemblies. Our contributions include, I'll wait until our contribution shows up, a data set of 100 interpenetration-free assemblies in ready-to-use simulation environments, a method for training specialists that is a novel combination of 3 distinct algorithms, assembly by disassembly, reinforcement learning with the imitation objective, and dynamic time warping. Our specialist policies can solve approximately 80 assemblies with an 80% or higher success rate. We also proposed a method for training a generalist that is an effective synthesis of policy distillation via behavior cloning and dataset aggregation, as well as curriculum-based RL fine-tuning. Our generalist policy can solve 20 different assemblies with an 80% success rate. And finally, a real-world system that can deploy our specialist policies in zero-shot with an 86.5% success rate over 20 assemblies, and our generalist policy in zero-shot with an 84.5% success rate over 20 assemblies. In total, we evaluated our system with more than 5 million simulated trials and 500 real-world trials. Here we first show an example of a single simulated environment that includes a widely used Franco robot arm, a plug, and a socket. We use the term plug to refer to a part that must be inserted, and the term socket to refer to a part that mates with the plug. Now we show deployments of specialist and generalist policies in simulation. In these trials, the plug is pre-grasped and it must be inserted into the socket. Here we show our real-world experimental setup that mirrors the simulated environment. And now we show real-world deployment of our specialist and generalist policies. Finally, we present the results of our specialist and generalist policies as part of a full assembly workflow. For these trials, we place the plug haphazardly on a foam block and place the socket haphazardly within a table-mounted shunt gripper. We capture an RGBD image through a wrist-mounted camera, estimate the 60 poses of the parts, grasp the plug, transport it to the socket, and deploy a specialist or generalist assembly policy. Here we show specialist policy deployment as part of full assembly workflow. For 5 distinct assemblies, we deploy the corresponding specialist policy 10 times for a total of 50 trials. The mean success rate is 90%. And here we show generalist policy deployment as part of full assembly workflow. For the same set of assemblies, we deploy our generalist policy 10 times on each assembly for a total of 50 trials. The mean success rate is 86%. These results indicate that 6-DOF post-estimation, grasp optimization, and our proposed methods for learning specialist and generalist policies can be effectively combined to achieve a reliable assembly under realistic conditions using research-grade hardware. Thank you. Through this work, we aim to gradually build towards the large model paradigm for industrial robotics, while staying grounded in real-world deployment. We look forward to seeing you at the poster session. For more information, please also check out our project website.
Any question from the audience?
Thank you. This is very interesting. When you're encountering the failures, is there a sense of retries, of being able to, I'm just curious more about how it concludes failure, and is there a way that, it seems like it would continue to retry until it was successful. Can you say more about that and maybe how you might retrain it to continue?
Yeah, so in this case, we don't do any failure recoveries at the moment in this work.
Okay.
But in the hardware experiments, when we detect failures, we detect the height of the gripper and effector positions. When it's like below a certain threshold, we consider it's done with the policy deployment. We just stop executing any robot actions.
I see. So if you just, when you detect that, you might just lift it and retry. Do you have a sense of how that would work?
So currently, we don't track the in-hand poses of the plug in the robot hand gripper. It would require that to be incorporated into the pipeline in order to do failure recoveries, because a lot of our failure cases are due to in-hand motions of the parts.
I see. So it slips inside the.
Yeah.
Got it. Thank you.
Okay. Any other question? Here.
Hi.
Yeah.
Hello? Okay, great work. In a lot of assemblies, you have requirements for force. Are you planning to include force in the policies, or?
So we currently do not have any force or torque feedback in our current network. Our policies are purely state-based, based on joint angles, plug and socket poses, and end effector poses. We do have upcoming work from our lab that is doing force sensing sim to real transfer on nut and bolt tasks. And it does allow to learn a more compliant policy for such like fine-grained manipulation tasks that allows moderate force use to better align the parts together.
Thank you.
Yeah.
Okay, so if there is no more questions, we can conclude the session and thank the speaker again.
Hello, everyone. We are going to start the session. I would like to introduce the chairs of the session. So I'm here with Dimitri Miller from QUT Center for Robotics, and I'm Janet Bogue from Stanford University. And we're delighted to have our first speaker on stage. This is Dylan Schell, presenting an abstract theory of sensor identification.
Thank you. So indeed, this paper is called An Abstract Theory of Sensor Identification, and my co-author, Yulin Zhang, is currently at Amazon Robotics. Now, most of the people in this audience already probably know what an event camera is. Unlike a standard RGB camera, which has frames that processes differences, this paper, we're not actually studying event cameras, but we're asking the more general question of, if you give me some other sensor, say an IMU or a LiDAR, is there an appropriate notion of an eventified version of this? Is there an event-based IMU, for example? Can one speak meaningfully of an event-based version? And is there an appropriate notion which applies generally, and would such a sensor be useful? So because our paper treats this problem at a high level of abstraction, it'll apply to a bunch of different systems, a wide span of sensors, So for example, we have a vacuum cleaning robot here. There's a complicated drone capable of both flying and driving. These are all examples, worked examples in the particular paper. So the foundation for our approach is to consider an operator which takes a particular sensor specification as input and transforms it into an event version of that sensor. So sensor A is eventified into a form of sensor A prime. In this paper, we don't think of sensors merely as turning energy into bit-encoded signals. Rather, they can potentially do some computation. So the theory builds up from elementary sensory computational devices, treating a sensor and some basic information processing unit as a single atomic element. We think of such devices as transducers, mapping from inputs to outputs in a way that can be stateful. Inputs arrive one symbol at a time, and they get processed, modifying state, and produce an output symbol. This proceeds for strings of symbols, and a stream of inputs will produce a stream of outputs. Now consider such a string of inputs, and suppose we pay close attention to two adjacent elements. If the space from which these Y symbols are drawn has some structure, we can talk meaningfully about a difference or change. So we'll show the raw signal space in black and the changes in blue in the slides. So now imagine we have two sensory computational devices. If the top one takes the sequences of the raw signal and the second one here processes a stream of changes, then given the first device, we ask if there exists a second one which produces outputs which match. If this is the case, then we have a drop-in replacement for the traditional sensor with one which processes incremental changes. That is, we have a substitutable event version of that sensor. Now, whether such an example exists will depend on several factors. It depends on what is lost in computing the changes. It depends on whether what was lost is important in mapping the input streams to outputs. It will vary as a function of task, and also how the robot environment coupling constrains the sort of sequences which can arise. In this paper, we provide an algorithm that can answer this question for any finite state device. And it's constructive in the sense that it will yield a sensory computational device that processes the changes if and only if one exists. So now returning to where we were before, suppose that the raw signal space might be equipped with the notion of equivalence. So here this delta might mean that we see no change. In this case, we have a sort of neutral element. And here now when we're processing these streams of neutral elements, they express the fact that no changes occurred. So if the stream is only being produced when there are changes, then those are not going to show up. And this models circumstances in which the signal indicates that an event has happened. We might ask exactly the same analogous question: does there exist an event processing version of this? And as before, we provide an algorithm that's constructive and will yield the answer if and only if such an event-based sensor exists. So going back to this, if we consider the orange elements as representing no change, we can also consider the case when you probe the sensor faster than changes are occurring in the environment. So this would introduce multiple of these orange neutral elements. And you can ask the same existential question. And again, we provide an algorithm that provides the answer. So far we've discussed three cases. The first models instances where the raw signal in black is transformed into deltas in blue, and this is basically a model of synchronous operation. Secondly, when symbols appear only when changes occur, that gives us the event-triggered case. And the last case deals with rapid polling of the sensor. In the paper, there are actually more other general forms of aggregation that can be provided when we think about the additional regularity or structure to the signal space. And it turns out our paper has algorithms and also some results for those too. So to summarize, our paper contributes a theory to answer the question of whether for an abstract sensor, a useful eventified version exists. The answer depends on what information must be preserved for the task being modeled, and on the regularity of the signal space, where having specific algebraic structure can be helpful. It also depends on the environment-robot coupling and how that constrains interaction. And additionally, we studied the effect of different access modes and their impact. For each of these cases, we have constructive algorithms for finite sensory computational devices.
We have time for questions.
Dylan? Down here.
Yes.
So I understand that event-based cameras have advantages because at the physical level, you're getting better performance and higher speed and so on. If you're going to use a classical sensor at the physical level and then computationally turn it into an event-based stream, what are the benefits in that case?
Yeah, so I don't know that there are benefits in that case. But this is essentially a model of some component, right? So it depends on where you draw the boundary between what you're modeling. So you could, for example, suppose you're interested in asking whether there's a useful event-based LiDAR and discover that, in fact, for the tasks that you have in mind, they are useful. Then you could go to Hukuyu or whomever, and you could say, okay, now you need to build me an event-based version of this, which you would then do in hardware, for example. Yeah, I mean, there are also instances where you can learn things about, for example, with a particular sensor, if you're going to use changes and then you modify the task, then the task may now become harder than the previous sensor permitted, and that may mean that you actually decide that you have to sacrifice some of the benefits of your event camera and fall back to a traditional camera.
One more question?
Thanks, Dylan. I really like this. It's when you use the notation, the sensor, the prime. I thought you were going to say something around some kind of derivative that's involved in there. So I'm curious because it seems like there's some kind of structure that you're actually using there, and I'm curious if there's an integral version of that as well.
Yeah. So in the paper, so I deliberately use this ambiguous word "change" to not try to overload the term. We do have a notion of things that look like derivatives in the paper. And in fact, if you come by the poster, I'll show you there are even some things that look like integrators. And they're related to each other in order to show, you transform from one to the other. The analogy to calculus is only an analogy though, so we have to be careful with that.
Let's thank the speaker again. Our next speaker is Samson Yu, and he's going to present Octopi.
Hi, Tess. Okay. Good afternoon. I'm Samson from the CLEAR Lab from the National University of Singapore. Today, I'll be presenting Octopi, a work that connects task perception and large language models for robotics. So we humans, we use the sense of touch for many tasks that might have visual ambiguity, such as picking the riper fruit from two fruits in the supermarket. So in recent years, roboticists have been working on giving robots a sense of touch. We have created tactile sensors that help robot tasks like object manipulation. So a common machine learning approach for this task is to collect some data and train a single model. If we have a different task, we do the same and train a separate model. So what if we could connect touch and language and use language as a unifying abstraction for diverse tasks instead? In this setup, we specify a task with a prompt, and the prompt will specify the task at hand. So let's say we have a different task, object recognition. We only have to change the prompt. We do not have to train a separate model. Okay, this allows us to leverage the common sense knowledge that LLMs have from being trained on internet-scale language data, such as softer fruits being usually riper, and also provide physical grounding for LLMs. So a straightforward approach is to treat tactile videos as natural images and use existing vision language models. However, there's a large domain gap between tactile videos and natural images that the VLMs are trained on. So to bridge this gap, we propose a tactile language dataset, PhysicClear, and a tactile language model, Octopi. Let me get into details of PhysicClear first with the tactile videos and annotations. So PhysicClear contains tactile videos of 74 everyday objects. They are annotated according to 3 physical properties: hardness, roughness, and bumpiness. So we chose these as a starting set because they are potentially easy to label, easy to detect, and also useful. Okay, so this is a demonstration of how my collaborator, he collected the tactile videos with a gel-side sensor and a pressing and twisting motion. So using the tactile videos and annotations, we create an LLM training and evaluation suite with 5 tasks, 4 for training and 1 for evaluation. So there are more details in the paper, so let me just get into one training task, object property description. So in object property description, we have 1 tactile video and a language description. The language description contains the 3 physical properties I mentioned earlier. So we hope that a language model trained with this task can learn tactile features that correspond to the 3 physical properties. Okay, so finally, let me get into the tactile LLM. So for the tactile LLM, Octopi, we use Vicuna as the base LLM. The task prompts are converted to word embeddings using Vicuna's word embedding layers. We added 2 custom tokens, tag start and tag end, to indicate the start and end of a tactile input. And the tactile input is converted to embeddings using a visual encoder and a projection module. So these embeddings are used to train the model. So now let me show you one downstream task that our model can be used for, object parts classification. On the screen, I'll show you two tactile videos, video A and video B. Now let's see how Octopi does inference with these two tactile videos. So first, I asked Octopi to describe the tactile videos. A is described as soft and rough, and B is hard and smooth. I then asked Octopi to match these two tactile videos to two parts of a toothbrush, the bristles or the handles. So Octopi can reason that A is more likely to be the bristles and B the handle. Okay, so you might have noticed that Octopi outputs property descriptions. So we find that these property descriptions improve its performance consistently across all its tasks. Okay, finally, let me show you one final downstream task, avocado ripeness classification. So first, the robot arm presses two avocados on the table. So with the tactile videos as inputs, Octopi will describe the two avocados. So the left avocado is described as moderately hard, while the right one is described as hard. So then Octopi is able to reason that the left avocado is riper because it is softer. Finally, the robot arm will put the left avocado into the bin. Okay, in this work, we connect touch and language so that hopefully robots can only need to use a single model for diverse tasks involving tactile inputs. We have PhysicClear, where we are in the midst of adding more data, and and then we have Octopi, where we find that property descriptions improve its performance, and we are working on version 2. For more information, find me at my poster session or scan this QR code for my website. Thank you.
Questions?
Hello. Okay, yeah, I wonder if it's like you did try to combine this information, the tactile images, with force or torque information from the wrist or anything, or is that possible or important?
Yes, so your question is whether we'll add more useful modalities for robots? Is it? Yes, so this is definitely in the works. We are working with some collaborators to add different like force, temperature, because they'll be useful for different properties that right now the gel set sensor might not be able to detect. Yep.
More questions?
Hello. My question was also, I guess, kind of similar. I was curious, like, when you were collecting the information for your data set, like, were you like applying a consistent force for each object that you were testing or that you were adding to the data set?
Yes, this is a great question. So right now the force is not consistent, but we try to make it as consistent as possible, but because for the training set, it's collected using, it's pressed by my collaborator, and he uses somewhat different force each time, but we try to make it as consistent as possible. So the future work will add more like robot data, so hopefully it's more consistent.
All right, thank you.
All right, let's thank the speaker again. The next speaker is Yanji Ze, and he's going to present 3D diffusion policy.
Yeah, hello everyone. Before start, let us see some videos achieved by our method. Our robot can make a dumpling and pitch it adaptively, and also drill the cube. And we also find the emergence of tracking ability. Okay, today I'm excited to present our work, 3D diffusion policy, generalizable with model policy learning via simple 3D implementations on behalf of our team. You can find more details on our project website. Our human beings possess remarkable maneuvering skills, like wrapping a dumpling or juggling balls. These skills are complex and require fine-grained model control. Our goal is to enable robots to learn such textual skills efficiently. There has been significant progress in recent years in learning textual skills. One line of work uses imitative learning to teach robots from humans, such as Ching's work and Harder's work. Another line of work focuses on using large-scale simulation and reinforcement learning and transfer them into real world, such as Chen's work and Huang's work. In this work, we mainly focus on imitative learning. Imitative learning has achieved great advances in recent years. One major progress is to using diffusion models as a robot action generation model, as discussed by Chi in diffusion policy. However, one possible problem of diffusion policy is that it still requires a large number of demonstrations to be effective. And whether diffusion policy could solve challenging tasks with very high dimensional address space, such as textual manipulation, is still yet unclear previously. This brings us to the question, what are we missing in our current approaches? One answer is that the world is inherently 3D. A lot of methods often overlook this fact. Let us start from a simple toy experiment to see why we need 3D as perception. In this experiment, we use 5 demonstrations to train independent learning methods as visualized in red dots, and evaluate them in 1,000 different positions. The successful trials is marked as blue dots. We observe that our method, DP3, reaches point distributed over the 3D space, which shows that DP3 generalizes with just a few data. We have shown that 3D mutation could be helpful, but there are so many ways to represent 3D information, such as voxel, point cloud, depth, and maybe implicit representation such as neural raised field, and maybe Gaussian splatting or something. So what could be the best way to represent 3D for diffusion policies? In this work, we found that very simple representations are highly effective. We introduced 3D diffusion policy, or DP3, which improves diffusion policies with a very simple point cloud-based representation. DP3 first converts the point cloud from the scene into a compiled latent vector and uses diffusion policy to predict the actions conditional on these visual features. Yeah. So why do not we use a more complex representation? We conduct some ablations and find that our simple representations are actually very effective. In the first experiment, we found that DP3 has almost the same performance as Oracle state in simulation, and it's better than voxel, depth, and 2D image. In the second experiment, we found that some point cloud encoders that are widely used in the vision community are actually not that helpful, even their pre-trained version. But why this happens? We choose PointNet to figure out the reason. By gradually modifying a PointNet into a DP3 encoder, we found that the Batch norm and the TNet in PointNet significantly hinders the learning process, and removing them would be good. We designed interesting and challenging real-world tasks with an illegal hand to show the power of DP3, such as drilling, dumpling, rolling, and pulling. We also evaluated 17 simulated tasks and 4 real-world tasks. A lot of tasks are textual manipulation. We show that DP3 is generally more effective than image-based diffusion policy, while it has a very competitive inference speed, since our 3D representation is very simple. Thanks to the usage of point cloud representations, DP3 by nature has several generalizing properties, such as spatial, instance, camera view, and appearance. If you want to see more videos, please check our website. More importantly, we observe that baseline methods often result in safety violations, while DP3 seldom has safety violations. This may be due to the usage of 3D information in the real world. But why safety is so important? Do you find that 2 different illegal hands actually appear in my talk? Yes. What happened is that the right hand we initially used was broken, maybe due to a lot of safety violations. So later we have to use the left robot hand to show the video. Okay, maybe that's all. For more information about DP3, you can explore our project website. You are also welcome to visit my website for more works. Thank you for your attention.
Questions?
All right, thank you for the great talk. So I wanted to ask about the safety, because you mentioned that you think that 3D diffusion policy results in fewer safety violations, but can you comment more about why you think that would be the case? Like you said something about the 3D representation, but I wasn't clear on that. And also near the end of the talk, you showed the broken hand. But you said it might have been due to safety violation, but was that because of the baseline method or because of 3D diffusion policy?
Yeah. I think, so the question is, the safety violation, where it's from is actually improved by 3D mutation, and whether our 3D diffusion policy could also cause the safety violations. Yeah, so I think in our real-world experiments, we find that there are 2 factors. So if we want to just use few demonstrations, the policy currently maybe cannot learn well. So that is I think the main reason that causes safety violation. For example, if you just use 10 or 20 demonstrations for image-based policy, they may have not fit very well in this real world space. And since real world is very hard, a lot of things would change if you just during the time, like the day and the light is different, and the table is different, the object setup is different. So in such complex thing, if you just few demonstrations, I think the most independent algorithm such as different processing will not work out. So I think that's the main reason that causes the safety violations. So what we want to show is that our 3D implementation could learn efficiently and effectively with just few demonstrations. So that would make the safety violation much less. And I think another reason is that it's not just efficiently. It's really capture the real world in 3D. So for example, if you reach something, there's a point there. So in our demonstration, we never reach collision the point. So our policy may not collision that point also. Yeah, but if you use that image based, you may not understand that thing. Yeah, there are many two reasons for that.
Thank you. I think there was like one microphone that has potentially reached someone else. Yes, okay.
For the quantitative result, may I ask, you are comparing diffusion policy with 3D diffusion policy. Are the number of the demonstrations the same or different?
Yeah, sure. So we want to try to compare them very fairly. So the demonstrations, the training epochs, and a lot of other factors like the inference, sampling time, sampling steps are all the same. So only the difference is the 3D representation thing. And also we keep the image size the same. So our 3D point cloud is extracted from the depth image. So we keep the image, 2D image and the depth all the same size. Yeah.
Have you compared it to other baseline other than diffusion policy?
Yeah, I think for the video representation backbone, we compare some other encoders and other 3D implementations like voxel, depth or something. And for the policy backbone, we also compare like BCRN and IBC. But I think there's another grade we call ACT. I think that is all great, but we have not tried on that. But actually we show that for the different region backbone and for the different policy backbone, maybe our current approach is very good.
Thank you.
Thank you very much. Let's thank the speaker again.
Thank you.
The next speaker is Mohan Kumar Sri Rama, and he's going to present HRP.
Hi everyone, I'm Mohan. I'm a master's student at Carnegie Mellon University. Today I'll be presenting a work on using human affordances for robotic pre-training, called HRP for short. We would like to learn visual representations from human video because it's very hard to collect robot data. Prior work such as R3M and MVP have tried to do this, but surprisingly, these representations fail to outperform standard vision representations on manipulation tasks like grasping and pouring. So our key insight is the self-supervised learning loss used by these representations fails to capture actionable information from human videos. So in this paper, we asked the following question. Is there a better way to learn visual representations from human videos? While prior works only focus on visual pre-training, in HRP, we go beyond this to incorporate human affordances. As you can see on the left, we start with standard vision representation that include VC1, clip, etc., and apply affordance-based fine-tuning on top of this. We use this VIT as a starting representation for downstream behavior cloning tasks. Now that we have an understanding of the overall framework, let's try to understand what exactly these affordances are. We use a standard off-the-shelf hand tracker to extract 3 key affordances. To begin with, we have contact point. These are 2D contact points on 2D images. Secondly, we have hand pose. These are hand centers, a few frames in the future. And finally, we have active object, which is the point at which the contact is actually made. We take these affordances and distill them into a vision transformer. A key thing here is we use a layer norm fine-tuning. We fine-tune only the layer norm while keeping all other layers frozen. We perform extensive robot trials, over 3,000 of them, to obtain results for our project. So now let's dive into the results. So we apply HRP on 6 different baselines, ranging from Ego4D, ImageNet, to VC1.
So we find that HRP improves the performance of all these baselines by at least 15%. And when HRP is combined with Ego4D and ImageNet, it produces state-of-the-art results, and none of the baselines outperform even the weakest HRP model. One common pitfall among robot learning algorithms is whether they can generalize across camera views and across different robot setups. To answer this question, we evaluate HRP on 2 different camera views and 3 different robot paradigms. This includes a dexterous hand and a completely different arm. As you can see, HRP sustains performance even when pushed across 2 different camera views and 2 different robot embodiments. We have a dexterous hand and a completely different arm. We want the robot learning community to easily assimilate HRP into their existing robot learning pipelines. With this intention in mind, we apply HRP with a diffusion backbone, and we see that the performance still sustains, and HRP boosts the performance. So let's look at what components of the system actually contributes to the performance. So one question we might ask is, why can't we directly use the teacher network that was used to extract affordances and use it for pre-training? We find that HRP's unique distillation mechanism is crucial and it boosts performance. Another question is, why don't we completely fine-tune the entire network? Is layer norm really required? We find that layer norm fine-tuning, the simple trick, really boosts performance. For the final ablation, we try to understand which among these 3 affordance labels actually contribute to the performance. We see that object and hand losses are the key components, while contact does help for certain data sets. To summarize, we introduce an actionable representation that can add on to any existing pre-trained baselines, boosting its performance greater than 15%. And we evaluate these models extensively across multiple tasks and across camera views, performing ablations with real-world tasks. To learn more about HRP, please visit our website. And yeah, I'll be happy to answer questions here as well as our poster. Thank you.
Thank you. Questions? Then maybe I have a question. You use these different losses, and I'm wondering, how did you pick them? Or do you think there are more that you could use, basically, that you could extract from these videos that you haven't yet exploited?
Yeah, that's a very good question, actually. Like, boiling down to these losses, like these were the most fundamental losses. We had other losses like tracking the wrist trajectory in 3D and also like predicting 3D poses as well. So one thing that we noticed was it was very difficult to sweep through all these parameters, right? Like, I would definitely see that like adding more losses would help, but we wanted to strictly stick to 2D losses for this work.
Okay, thank you.
Hi, thanks for the great talk. I'm curious if you looked at object-object interactions as well. So in addition to people picking up an object, how does that placement then affect how they use that object as a tool or interact with other objects in the scene?
Yeah, actually, that's a very good question. I think for this, these kind of losses, right, it kind of limits the data source that we can use, because like having tool interactions and object-to-object interactions, the number of frames that you can actually get to train on these losses is pretty limited. So if we can actually mine more data that contains object-to-object interactions and tool interactions, I'm pretty sure like we can incorporate that easily into our HRP framework. Yeah, thanks for the question.
We have time for one more short question. Okay, in that case, let's thank the speaker again and bring your questions out at the poster session.
Thank you.
So I'd like to invite the next speaker, Lawrence, up to the stage to present Mirage.
Okay, so hello everyone. My name is Lawrence. Happy to present our work called Mirage, cross-embodiment, zero-shot policy transfer with cross-painting. So there are many different robots. In a classical paradigm robot learning, we collect data for each new task on a specific robot hardware, train a policy, and repeat this process. This is costly and inefficient. In this work, we ask, can we, instead of recollecting the data and retraining the policy every single time, can we transfer a trained policy from one robot to another zero-shot? There are a few different paradigms in cross-embodiment learning. Cross-domain imitation usually involves learning correspondences between the source and target domains. In transfer learning, prior work has explored using RL to fine-tune the vision encoder, a value function, or the policy. Recently, there's a trend of learning from large multi-robot data, such as RTX, Octo, and OpenVLA. In this paradigm, deploying on a new robot usually involves co-training or fine-tuning. However, this still requires large target robot data. Can we achieve zero-shot transfer? So we are inspired by these related works. In World, the authors mask out the human hand and robot hand to align human videos and robot videos and operate on the background. In Robot-Aware Visual Foresight, the authors mask out the robot and learn the visual dynamics model on the background. In AR2D2, the authors use a virtual robot and render that into the image. In this work, we combine these ideas to transfer a policy from the source robot to the target robot. How do we do that? Well, one of the main reasons why a policy trained on the Franca does not work on the UR5 is because the policy has never seen the UR5 before. What if we replace the UR5 in the image with a Franca at the same pose to create an illusion as if the Franca is performing the task? Now the policy knows what to do. We call this process cross-painting, masking out the target robot and in-painting the source robot. And then we can feed the cross-painted image to the policy and get the actions. Importantly, this happens at test time, which means we can get zero-shot transfer. How do we cross-paint the robot? Well, given the target robot image at test time, if the target robot camera angle is different from that of the source robot camera angle the policy is trained on, we can use the camera reprojection to reproject it back to the source robot camera angle. And then we can mask the robot out using the robot URDFs and joint angles. And then we can in-paint the background using the fast marching algorithm, and then put the rendered robot back in. What do we need? We need a robot URDFs, the camera matrices, and a renderer, which we use Gazebo for flexibility. We conducted extensive simulation and physical experiments. In Sim, we use Franca as the source robot and Canova and UR5 as the target robots. Here are some quantitative results. The blue bars show the source robot performance, and the orange is directly deploying the source robot policy on the target robot without cross-painting, and green is with cross-painting. We can see that cross-painting is crucial in achieving high success. In physical experiments, we experiment with 3 embodiments, including different robot and gripper combinations. For each task, the source policy is a diffusion policy trained on about 200 to 400 demonstrations on the Franca robot. And additionally, we also compare with Octo, fine-tuned on the combined multitask data. And here are some example videos showing the source robot demonstrations that the source policy is trained on the Franca robot. Here is Mirage performing on the target UR5 robot. The video on the right shows the actual target robot rollout, while the video on the left shows the cross-painted image that are actually fed into the policy, which is trained on the Franca. And here are some other tasks, such as the opening drawer, stacking cup, as well as the toaster oven task. Here are some example videos of not applying cross-painting. We can see that both diffusion policy and Octo have a significant decrease in policy performance. Quantitatively, we can also see that cross-painting is crucial for achieving success in real. Mirage also works with wrist camera and multiple cameras. Here we can see Mirage cross-painting the gripper into both the wrist camera view and third-person camera view simultaneously. For code and more videos, please check out our project website. Thank you.
All right, questions?
I was wondering, when doing in painting, it would lead to a lot of artifacts in the image, right? And you input that image to the policy. So does that lead to some kind of performance drop?
Yeah, so there will always be a performance drop between the source domain and target domain if you don't fine-tune the policy. And the closer you make the in-painting better, like you align the training data, the better. Of course, one of the main benefits of doing that in the image space is you can visually inspect how well the cross-painting image look like. And if it looks reasonable, then you will expect a good performance. But of course, there will always be some drop.
Thanks.
Hi, fantastic presentation. It seemed that all the examples of source and target robots seem to have very similar joint configurations and allows for clean in-painting between them. Do you see how this could expand to sort of a little bit more differences between those targets?
Yeah, that's a good question. So in this work, we do have some limitations. For example, we assume that both robots have similar workspace that are reachable for performing the task, and we do not consider collisions and like weird joint angles. For future work, if we allow fine-tuning, then we can take consideration of more demonstration data or using RL fine-tuning to adapt the policy on the target robot.
Thank you.
Maybe one last quick question here.
Yes, I was wondering if it's possible to use image generative models, and if you tried that.
Yeah. So it's actually in our current extension work, we are trying to do that rather than at test time, doing a test time adaptation, which require real-time speed, so we cannot use diffusion model there. But if we do that in training time to use data augmentation, then we can use diffusion models. And in that case, we can actually relax some of our assumptions, for example, known robot URDFs, known camera angles, because like using a segmentation model, diffusion models, they are more generalizable.
Yeah, thanks.
Let's thank the speaker again. So I'd like to invite the next speaker to the stage to present broadcasting support relations recursively from local dynamics for object retrieval in clutters.
Hi everyone, I'm Yi Tong. I'm a junior undergraduate student, and this is Rui Hai, a PhD student from Peking University. I'm super glad to introduce our paper here, Broadcast Correlation for Clusters. And nowadays, there are many clutter scenarios in our daily life. It's very difficult for a robot to manipulate in these scenes because it's very easily to cause damage to the other objects, such as collision or falling. So we need to infer superpolation before manipulation. But superpolation is not very easy to infer. For example, if we just use a straightforward method, we can see three main drawbacks. The first one is inaccuracy. We can see the corner, the boot, and the cuff, it has long-range dependence and indirect correlation with the target, so it can hardly be inferred by a single straightforward model. And the second drawback is a boot on the top. We can see it can be, the falling can be avoided if we choose the better travel direction. And the third one is only to know which objects are supported by the target is not sufficient. We need to know the support relation inner the supported side, so we can know which one is the first and which one is the second to manipulate. So because of these reasons, I want to propose our main methodology called recursive broadcast. And I want to introduce broadcast mechanism first, which can infer the support relation between a target object and its corresponding adjacent objects. So we just first infer an optimal direction to retrieve, which we'll call the least potential collision or falling. And then under the given optimal direction, we will judge whether the object will move or not, which means the support relation is this or not. So the local region support relation can be obtained. And then we want to expand the local region to the whole scenario. So we just start with broadcasting the target and find which objects are supported by the target and call them child nodes of the target. And then we just rebroadcast the child nodes, and then the child nodes of child nodes, we just continue this way recursively to find the whole scenario for relation and until reach a convergency. So the complete support relation graph can be obtained. And the initial observation is partial because of the occlusion. So under manipulation, some occlusion may be removed, so we can get a better estimation. So we rebroadcast the objects and get a better refinement and estimation of support relation.
We learn point level affordance to select the best grasp point in the cluster scene and propose the safe manipulation orientations in the clusters. The right images show that the affordance can generalize to diverse objects in different categories and geometries. Our real-world setup includes one Franca Panda robot and one Kinect depth sensor. The left video shows the building process of the supporting relation graph, and the right video shows the corresponding manipulation in the real world. The supporting relation is first broadcast from the target object, and then the nearby objects that are supported by the target objects will recursively broadcast their corresponding supporting relations. And then finally, the whole supporting relation graph will be generated. And we will first retrieve the object that is not supporting other objects in the graph. This process is repeated many times until the target object is retrieved successfully. Also, we have demonstrated our performance in different diverse scenarios. For more details, welcome to visit our website and our poster in the afternoon. Thank you so much.
Any questions from the audience? Yep.
Have you considered the case where you are not allowed to remove the other objects? They have to stay perhaps in the same container? So here you always remove an object, right? If it blocks your target.
In that setting, all objects are removable, and so we want to avoid the creation or falling of other objects. If the other objects are unmovable, it cannot be falling or creation. It's also the definition of our setting.
Yeah, understand. Yeah, I suppose there are cases that are movable, but you don't want to remove them from that space, so you just have to kind of protrude that pile. But yeah, interesting work.
I think the question back there.
Yeah, I had a similar question to Costas. I think like when you're using the graph, it seems like you're using it to pick things out of the cluttered scene directly. But are you actually able to use the relationships that you're determining through broadcasting to actually determine whether the item is pickable or not? And if so, like how do you incorporate that into your model? So I guess like the question is like, are you actually like reasoning about what is pickable in that cluttered scene based on like the relationships between the different items?
In fact, in our setting, the object is pickable when it is not supporting other objects in the supporting relation graph. And then it is pickable as it has some pickable points in the supporting, in the affordance. If the object satisfies these two rules, it is pickable.
Great, let's thank, we might have to move on just for time, sorry. Let's thank the authors. So now I'd like to invite Jeanette, my co-chair, to present the work on consistency policy.
Thank you. Yeah, I'm presenting today consistency policy, which are accelerated visual motor policies achieved through some consistency distillation. And consistency policy completes inference 10 to 100 times faster than diffusion policy with comparable success rates. Diffusion policies are popular in robot learning due to their expressivity, continuous action spaces, and training stability. However, they have long inference times, and the reason for these long inference times is that diffusion policies generate actions through an iterative denoising process that is visualized in this figure here. And we present consistency policy, which distills a vanilla diffusion policy into a new model made for single-step inference. We denoise the initial random action in one forward pass of our policy network. So here's a visualization of the diffusion process in the image domain. And to generate training data, we take samples from the data at time step 0 and add Gaussian noise. At the maximum time step capital T, we end up with pure noise. We then teach the diffusion model the reverse diffusion process to go from pure noise to a signal in multiple steps, as shown in the bottom here in green. And our distilled policy learns to jump the entire reverse process in a single step. For accuracy, we can also increase the number of denoising steps. Okay, so here's how the distillation of a diffusion policy into a consistency policy works. We sample time step S, U, and T along a trajectory of the diffusion process. We denoise once using the teacher diffusion model, shown here in green. And then we denoise with the student model, shown in blue here, to time step S, which is our consistency policy. And then we bring both trajectories to the same diffusion time step S using the student model under stopgrad. And then we bring both trajectories back to 0, which represent our original data distribution without any noise. The loss between these final positions is the objective we optimize against. We evaluated our method in simulation on these 6 tasks using either images or states as input, and we find that consistency policy produces similar success rates to 2 diffusion policy variants shown on the left, while being many times faster as shown on the right. We also evaluated on 3 real-world tasks, pick and place, contact-rich insertion, and a long horizon task on a mobile base. And in this case, all of the consistency policy is run on a very slow laptop GPU. And our single-step consistency policy is competitive with diffusion policy while being much faster. Okay, so here are some real-world rollout examples for you. Notice that consistency policy on the left finishes before diffusion policy on the right, as indicated by these green check marks, and is also smoother due to the reduced lag from the inference time. So these videos are real time as well. So now we play the contact-rich insertion task, also the videos in real time. And diffusion policy, again, here on the right, is slower and produces more jerky motion than consistency policy due to this inference lag. Finally, we have the long horizon task on the mobile base. This video is sped up 4 times. And the lag due to the inference speed is less noticeable here because of the policies being deployed over Wi-Fi. But consistency policy still has an edge in speed and smoothness of motion as well. So in summary, consistency policy speeds up diffusion policy inference by 10 to 100 times while maintaining performance, but we also encounter 2 limitations. So first, because the consistency objective requires an ODE-based teacher, both our teacher and our student models display less multimodality than the stochastic differential equation-based diffusion policy. And second, the performance was somewhat lower for the 2 long horizon tasks, likely due to inherent difficulty of learning a single-step policy rather than a many-step policy for these types of long horizon tasks. Thank you for your attention.
I think we've got the first question over this way.
Hi, thank you for the great talk. Can you hear me all right?
Yes, I see you.
Okay, how did you find your choice of S and T influence your results?
How did my choice of what influence the result?
Like S and T, the time steps that you select for the teacher-student models?
I'm sorry, now I also have to look. Oh, the time step I selected.
Yeah.
Okay, that's a good question. I think, I don't know, actually. That's a good question. So I'm just here because my students couldn't come. And that particular detail, I don't know, but it's a very good question. Thank you. Sorry.
Yeah. Yes. Yes, I was wondering, when you evaluate this in the real world, do you use the same data set with the same frequency, or did you have to like overcome, like since the consistency policy is faster, did you have to do any modifications to make it work in the real world evaluation?
I think the question was if we use the same frequency in the real world task for the consistency policy.
Yes, at the dataset side, but also in the inference. I guess the inference is faster for the consistency policy. So I wonder if the dataset is modified in some way to make this work.
I'm really sorry. I have like a really hard time understanding you. Sorry for that.
Is the dataset used to train the both policies the same frequency? Or is that important that they're the same frequency, where since the consistency policy inference frequency is higher?
The data on which the diffusion policy and the consistency policy is trained is exactly the same. And we also use the same. So basically, we need a teacher policy, right? Like, and that one is trained exactly on the same data and has the same frequency. And then we distill that, right? So there's no difference between the two, the baseline and the consistency policy. I hope I answered your question.
Okay, I can see it at the poster as well.
Yeah.
All right, let's thank the speaker again.
Thank you.
And lastly, I'd like to invite Han to the stage to introduce closure.
Hello everyone, I'm Han. I'm very glad to present our paper, Closure, Fast Quantification of Post-Uncertainty Set. So we focus on the problem of 6E post estimation. So unifying framework will contain 2 steps. In step 1, neural networks are trained to generate neural measurements, such as 2D to 3D matches, 3D to 3D, and post-hypothesis. So in this equation, X denotes the unknown points to be estimated, Y denotes the measurement, epsilon denotes the measurement noise, and the function G governs the measurement between the post and the actual measurements. And in step 2, we leverage MLE framework to formulate an optimization problem to seek the optimal post hypothesis. Examples will include PMP, point clouds registration, and rotation averaging. But what can go wrong with it? So the first drawback is that the distributional assumption on the measurement noise is always Gaussian. However, in practice, it's not true. So here we show a comparison between the empirical distribution of real noise against a Gaussian distribution, with different levels of outlier filtering. The real noise distribution of a neural network deviates far from a Gaussian distribution. Also, they fail in almost all of the Gaussianality tests. The second drawback is that solving the MLE optimization problem only returns a single estimation, and a provably correct uncertainty quantification is missing. So next, we propose a paradigm shift and show how to formulate a post-uncertainty set, which we call PERS. Instead of assuming the noise satisfies certain distribution, we just assume the noises are unknown but bounded. So why it's better? The key insight is that the noise bounds can be calibrated from the noise, regardless of what neural networks are used. We do so using conformal prediction. We then use the set membership estimation framework to formulate a PERS, which is a subset of SE3 defined by inequality constraints. So the nice property of PERS is that uncertainty quantification comes for free. So what does a PERS look like? We show that for 2D to 3D and 3D to 3D matches, PERS can be characterized by certain constrained mechanical systems. And for post-hypothesis, PERS is an intersection of multiple geodesic balls. Our key contribution here is to provide a fast algorithm to approximate the non-convex PERS. Inspired by related work in robust control, we propose to find the minimum enclosing geodesic ball of the PERS. However, finding such a ball is not a very simple task. So we can, for example, output a point estimate together with a worst-case error bound. So how to find it is an NP-hard problem. To approximate it, we provide two algorithms. One is named GRCC and is currently also being presented at L4DC. So the second is our algorithm, which is called closure, and it finds an inner approximation. Let alpha and gamma be the size of inner and outer approximations. We can output a certificate of approximation called eta. The closer eta is to 1, the tighter the approximation is. So how does closure find such inner approximation? The crucial insight is that if we can densely sample the points on the boundary, then the ball that encloses the boundary points will guaranteed to be the inner approximation. So it works as follows. It starts by initial set of the points inside the purse, and then closure leverages GPU acceleration to perform parallel random walks on SU3 until the samples hit the boundary. So finally, closure uses the minimum ball algorithm to compute the enclosing geodesic ball. And also we test closure on some real applications. So we find that not only closure can run in real time across different applications, also the certificate of approximation is very close to 1. Also we compare the error bound returned by closure. So the blue line returns to 2D to 3D in 2017, and the red line returns to 3D to 3D matches in 2020. And lastly, the yellow line is corresponding to the foundation pose in 2024. We clearly see that the continuous reduction of pose uncertainty. Also, foundation pose only has 4 degrees of worst-case error bound. Please come to our poster and visit our paper for more technical details. Thank you so much.
Any questions from the audience? I think just here.
Oh, thanks for the great talk. Have you compared your method with the graduate non-convexity or another outlier robust perception things? Thanks.
Yeah, that's a very good question. So far we do not find many very advanced methods to do so. So we compare with one method, which is a RANSEC, and just randomly sample points. Also because we propose two methods at the same time, one is for inner approximation and another is for outer approximation. We just compute the ratio between them, and we found the ratio is already very close to 1, which means that our approximation is actually very accurate compared to the ground truth. Thank you.
Okay, thank you.
Okay, I think that's going to be the end of the perception session. Let's thank the speaker again and all the speakers for presenting. And we'll move over to the plenary.
Hello, everyone. I have been assigned the rather redundant task of introducing our second keynote speaker, Professor Dieter Fox. As you may know, he is the Senior Director of Robotics Research at NVIDIA, as well as a professor in the Allen School of Computer Science and Engineering at the University of Washington. Dieter started his research from the area of robot estimation and mapping, but now he's work covers the entire fields of robotics and artificial intelligence with a focus on learning and perception. He's a prolific researcher. He has published more than 200 technical papers, some of them here at RSS this year. And he's also co-author of a very popular textbook on probabilistic robotics. He has been recognized as the fellow of IEEE, AAAI, and ACM, and he's also the recipient of the 2020 IEEE Pioneer in Robotics and Automation Award, as well as the 2023 IHCAI John McCarthy Award. But if you check his CV, I think the most important line there, and I think the one that he probably regrets the most, is that he served for RSS as program chair back in 2013. So, everyone, Dieter Fox, where's Robot ChatGPT?
Thank you very much. I just want to see whether subtitles. Yeah, thanks a lot. I actually gave a talk at RSS 2017. I was just thinking that at the time it was, all the rave was about just the upcoming all deep learning. And of course, by now, actually everybody is doing something with learning. But at the same time, we don't talk about deep learning anymore, right? It's all about foundation models and LLMs and things like that. So kind of details of neural networks don't really almost matter anymore, right? We are all using similar architectures and things like that. So I think it's been some really exciting time. And the motivation for this title is, of course, because that's a question that I've been asked a lot, and I've been asking myself a lot, and I'm sure many of you are also often being asked, like, hey, what's going on, right? We have all these great things happening in language and vision, and ChatGPT is solving everything, and general AI is partially solved, at least what people claim, and in robotics, we're really not making that much progress, and I'm just thinking, okay, where are we in this endeavor? And as a heads up, I'm not going to answer that question actually, right? Or I'm certainly not saying give you the solution for it, but I just want to share kind of where I think we are right now in this respect. So, and I want to, of course, put it mainly in the context of the work that we've been doing in manipulation and also the simulation techniques for manipulation training. So to put this now in with respect to the techniques in generative AI, by generative AI I mean all these techniques around transformers for language models and diffusion models. I think it's really fair to say that the progress has been truly astonishing, right? For experts in the area, for non-experts, even like people as us, we were really surprised, I think, by the capabilities of these large models that we've seen in especially initially mostly with language models, but more recently with vision models, speed, generative models, right, like stable diffusion, but also visual understanding has become way, way better than it's been just a few years ago. And that makes it so much more relevant for robotics. And I think the key reason for why we've seen this progress is three key points here where I think on the one hand side, of course, there are these vast amounts of training data for these kind of models that are at internet scale, right? We're talking about millions and millions of images that these models are trained on, and also, of course, huge amounts of text, like the whole text on the internet. And the idea is that if you train models on such large amounts of data, that somehow all the tasks you throw at them at deployment time is almost kind of becoming in distribution, meaning these models have seen virtually everything. Of course, we all agree it's not quite true, but conceptually, right, it's really amazing that you can see these transfers, but again, they don't have to transfer that far outside of the training distribution because the training distribution is just so large. At the same time, of course, now we have these models that are able to digest that kind of data, right? Like especially these transformer kind of techniques now combined also with diffusion methods. So that's another key ingredient, right? The data doesn't help you if you don't have the model that are able to scale with the amount of that data. And finally, the nature of that data is, it's not just random images or something like that, or random words. It is text and images and captions that were generated by human with some purpose in mind, right? So which means this text is not random, but there's some meaning to this text. There's grammar behind this text that was generated and content that people wanted to convey through this text, or be it also code and things like that. So because of that, they can train these models mainly through supervised learning, what we as roboticists would call behavior cloning, right? Because if you think about these texts, there's the input is a part of the text, and then the models are trained to predict the future words that are coming up, right? So this is coming from a robotics perspective. If you think about words as time steps, right? And then we see, for example, you could imagine you observe a robot doing something, and now you're asked, okay, give me the next control output, right? That is what we then call behavior cloning, and it's very related to the kind of techniques that have been so amazingly successful in language and also in visual training. So the problem is that these methods don't just work immediately on robotics, and I think there's, of course, two key problems. On the one hand side is what roboticists know very well is this, what we call Moravec's, Hans Moravec at CMU came up with this Moravec's paradox, is that the things that we always believe to be easy turn out to be hard, and the things that we thought are hard turn out to be actually relatively easy. So meaning that, for example, playing chess, and by now even playing Go, is relatively well suited for computers and for learning and becoming better than humans. And the things that we always thought that are like super trivial, like picking up this bottle, those are the things that are actually the hard ones, right? And I guess we all are constantly in the business of convincing people that it isn't as trivial as everybody thinks, right? Because it is something that is so natural to us humans, and also it's something that we see, of course, in nature so much, right? So we always think that AI is only about the stuff that separates us humans from all these animals, but I think it's really about this physical intelligence that we really need. And at the same time, another aspect is, of course, that we just don't have the data that these models have that they are trained on, because there is no vast amount of data that is readily suitable for kind of behavior cloning techniques for robots, because there are not sufficient robots out there, right? And the robots, they are not good enough to automatically generate that kind of data. So the hypothesis for this here is, especially as it relates, again, to this ChatGPT, RobotGPT idea, is if we could only generate data sets that were large enough and had the kind of variability that we've seen for the vision and the language kind of data sets, then the kind of models that are being deployed, then there might be a chance that we could train models that somehow are vastly superior to what we see right now, and I think it could be a real step up in the general robotics capabilities compared to what we have right now. The key questions in that context are, of course, on the one hand side, okay, how are we going to get the data, right? Because that's, of course, extremely costly. And also, what kind of models could we train on that data? And that's what I want to discuss in the remaining part of this talk. So if we're looking at what's going on in especially some recent advances in, for example, in humanoid companies, and I'm sure you've all been following the cool videos that are going on the web, and also the evaluations that these companies are getting, and also, of course, from the research community, some works I show here. I think we've seen some really, really cool success on using behavior cloning type techniques for manipulation, right? And I'm using behavior cloning in a very lax way, so it could include things like fine-tuning and dagger-style distribution shift handling and things like that. But overall, it's really mainly driven by this idea. We teleoperate robots and collect data through these teleoperations, and then we train with, again, similar behavior cloning techniques to what are being used in the vision and language domain, and train them to replicate those behaviors, and then you see these amazing, cool demos what these robots can do. The key problem at this point, I think, is actually that, of course, there is a lot of kind of overfitting to these demonstrations going on, which means the notion of what we're seeing in these language models where you really see some, let's say, interpolation between all this text and they truly come up with new things, is that in these demos, they are all kind of, if you think about the whole space of robot manipulation tasks, then all these demos are kind of little tiny point solutions, right? Where now I have a point solution for picking up that object, but only when it's exactly at that location, right? And what we don't see yet is really some kind of interpolation or generalization across these point solutions. So for example, some of these demos that you've seen, very impressive ones where a robot might then pick up a plate and things like that. It turns out if you move that plate a little bit, the robot won't be able to pick it up anymore, right? So, or there were also cases where overfitting, for example, to table heights, right? If you put a robot into a new environment and the height of the table is different from the height of the table it was trained in, then the policy might just fail. Right? And these are some surprising things that go wrong, but at the same time, of course, again, it shows just the complexity of these problems. So the question is, where can we maybe get more of the data from that we need to train at some point policies that generalize better? So there's different ways of generating data. On the one hand side, people look into watching just videos on the web, right? Because there's humans demonstrating many dexterous manipulation tasks. There's also data collection efforts out there where people where people put a camera on themselves and then collect data performing tasks in the world. And I think these data sets are going to be extremely useful and they are highly relevant and related to robotics. But at this point, I think the gap between those data sets and, let's say, real robot deployment is still a bit too large. So meaning that there's, of course, the embodiment gap between the human hands and the robot hands, and also the data doesn't have quite the supervision signals that we would like to have for behavior cloning. But they are certainly very good also, for example, for pre-training, and if you think about world model training and things like that. Another approach is, of course, a real-world teleoperation, and that is what many companies are currently betting on, just kind of hiring people to teleoperate these robots and generate training data for them. And I think it's an open question how far we will get with this, right? It's clearly a very powerful technique, but at the same time, scaling is just going to be tricky because it's very expensive, both on the hardware, because you need the hardware to do the teleoperation on, and on the humans to do the teleoperation. And finally, of course, there's simulation, right? And there's been quite some successes on training robots in simulation. The big advantage, of course, is that you can scale it much easier and you can randomize the training data sufficiently. For example, you can place objects at any location, and by generating maybe data with these randomized positions, you can make sure that your model doesn't overfit to a single position and things like that. So there's many advantages to this, but of course there is some tricky pieces like the sim-to-real gap, and also where do we get all these assets from that we can use to simulate. But I actually believe that simulation can play a key role in this domain just because of its ability to randomize over appearances, objects, and also spatial relationships and everything. So in the core part of this talk, I want to actually focus on some of the work we've done in this domain, especially like how we use simulation for training, and also kind of how I think we can scale this up to generate more data that is necessary. So in the first part, I just want to give you some examples of work we've done on training some capabilities in simulation that transfer also to the real world. The first is this kind of work on grasp training. How do you train a robot to pick up objects, for example, and without even training or using real-world robot data? So we did this work here where, for example, if you want to, for example, you have an asset, like in this case, it's the spam can from the YCB object data set. Imagine you have a 3D model for this object, and then what you can do in a physics simulator, you take this object model, and let's say you have a gripper that you want to train on this object. Then what you do is you just randomly generate gripper poses, okay, thousands of them, And then for each of these randomly generated gripper pose, you just put it in a physics simulator and say, okay, what happens if I close the gripper and shake it? And only in the cases when I had a good guess, the object stays in the gripper. In the other cases, the object kind of flies away or does something else, right? So with this rejection sampling approach, what we can do is actually, we can now get for this object a set of thousands of gripper poses that actually will be successful according to the physics simulation, right? I hope that makes sense. And of course, GPU, we can do this in parallel and very fast. And if we now have a data set of, in this case, we use like almost 9,000 object models. You do this for a large data set of objects. Now what you have is a labeled data set of objects with gripper poses that will work on them. And you can now generate scenarios where you place the object in the scene, and you can also label where the gripper should go in order to pick up the object. And also what you can do is you can render the scene from a viewpoint as a robot would look at it, let's say from a point cloud. And you can now train a model, like the most recent one we did a series of models, but the most recent was M2T2, the transformer-based models on point cloud input. You can now train a model that takes as input a point cloud and outputs possible graphs for the object, okay? So again, the key trick here is that in simulation, we take advantage of the fact that we have ground truth assets and shape models and everything, so we can make sure that the physics are correct. But then we distill this or transfer that to a real-world model by training that model on point cloud. So the model has not access on the shape model of the object, for example, right? And then we can also train a perception system in this context. And this is a system here, I just want to give you an example. Here, for instance, where the robot, here's a Franka robot in the scene and has to pick up an object. And imagine you want to tell it what object to pick up, and you just give it an image, as you see in the upper left, of this case of this little pot. And then we also have a segmentation model that is not segment anything, but we call it object seeker, but that was also trained solidly in simulation, and it's trained such that you just give it an image of an object, and it segments out the object in the scene. You can see the segmentation masks also here in the upper part, okay? And once you have the object segmented out, you can use the network that was trained to generate graphs, and the robot can pick up the object. Okay? What's interesting here is every single component here was solidly trained in simulation, which means the graph generation is trained in simulation, and even the visual perception that does the matching between the image and the segmentation in the scene is also purely trained in simulation. Okay, you just do enough randomization on that data, and then you can generate pretty large data sets to do that, right? In this case, even the collision checking is trained in simulation, so that you can handle collisions with occluded pieces of the scene. So this works pretty robustly, and again, the key advantage of this is because in simulation you can randomize things enough that it also works with different elevations and things like that, and object poses and stuff like that, right? That is because you can vary that easily in simulation. Now, instead of grasping, let's briefly look at placing things. This is work that we did with Anthony. He's somewhere here, maybe in the audience even, I don't know, but he's at the conference, Anthony. He did this work with us on training a diffusion model for placing objects. So imagine you have a book, and you want to place it in this bookshelf. First, you have to figure out where is the right spot to put it. And another interesting aspect is it's kind of a multimodal problem because there's multiple positions where you could place it. And how we did this here is the following idea. Is you generate a simulated 3D environment. And in this case, for example, there's this blue book object that you can place in here. And it's all kind of, you can represent it now as point clouds. And what you do in simulation is you just perturb the position of the book, okay? And you perturb it more and more. And I'm sure the word noising here already tells many of you what we're going to do next is we're just going to use that as training data to train a model that does denoising. So it's a denoising diffusion model that now takes as input a point cloud with a noisy position of the book and tries to make it more similar to a target position that actually fits into the shelf. Okay? I hope that's the same way, for example, these diffusion models for image generation are trained, right? You have an image, a clear image, and then you noisify it stepwise, and you reverse that noise process through a trained model. And here we do the same way. We know where the book belongs. We noisify the position, and then we train the model. And here's just an example then in sim what the denoising process actually looks like. Let me show you that again. And the nice thing is it's multimodal, which means the model actually uses, depending on just a randomized initialization, it can come up with different positions where you place it. And actually this also works then in the real world. Okay, so the model just, it doesn't have a model of the can, right? And it doesn't work perfectly well, as you see, but it can now kind of pick up the object, and based on the observed point cloud, it can decide on, through that process, it can decide on where to place it. And it comes up with actually a variety of different positions and things like that. It also works for books. I'll give you one example here. And even for, let's say, a slightly more tricky thing like the cup hang task, which is also something that's being used a lot. But it kind of gives you this idea, right, that training this in simulation is actually not too hard, right, because it's pretty easy to noisify things. So far, the tasks that I looked at were mostly on kind of relatively easy from a physics simulation perspective, right? So then what we looked at is industrial kind of assembly problems, and it turns out that these tasks require very high precision on the placement side. For example, NIST, they used to have this benchmark task board where you have to do this very fine-grained insertion task or thread a nut onto a bolt and things like that. Now they have also deformable objects in them, but they had this physical board that on the left side that you could actually buy to train and test your robot on. And I was always surprised that why is there no simulation version for that? And it turns out that simulating these kind of things is not trivial. So here's just one quick example. Threading a nut on a bolt, and by the time when we did this work, simulation was extremely slow for these tasks, just because the assets have to be super fine-grained modeled and things like that. And it turns out the best one was like 350 times slower than real time, which kind of beats the purpose of using simulation, because if you want to do training in sim, you want to have something that's faster than real time. So then, and that was an RSS paper 2 years ago, Yasha and his team, they came up with this work, worked with the simulation team, and they did some magic on GPUs and using signed distance fields as a representation. And they were then able actually to simulate 1,000 of those in real time in parallel, rather than a single one 350 times slower than real time. And once you do that, you can of course now go to start training policies in simulation. Okay, just because it's now so fast, you can really do reinforcement learning. And then over time, we did several lines of work on showing that we can actually also train policies that transfer to the real world. And Bingji just gave a talk in the morning session. I'm sure you all saw this. So we can now simulate various of these tasks and transfer them after simulation zero shot to the real world, to the corresponding same assets. And we can also start to train policies that are not for a single object, but go across objects. And you can see where this is going. As we scale these things, we can train more and more general policies. And one question came up actually in the talk this morning, after the talk about force feedback. So this is work that is not out there yet, but just want to show an example of assembly using actually force torque feedback from the Franca, from the joint. It doesn't have a force torque sensor here, but just from the joint feedback. And here this Ireti and his team are working on that with Michael as an intern, did this, where they now can do multi-step assembly, where the positions can actually place at different locations, and there's an object pose system in their foundation pose, and then it picks up the objects and places them at these pretty precise locations, and it's using force feedback in order to put it in there. Again, the force feedback is also trained in sim, and then we get the transfer to the real world. Another one is touch feedback. Did work on simulating gel site sensors, and we can also actually transfer those policies using the tactile feedback into the real world. All right, one final example, just on this notion of also learning more dynamics tasks. I'm sure many of you have seen this kind of work where it's about training these cube in-hand reorientation tasks in simulation and do it so that they transfer to the real world. Okay, this is Ankur did this on the Dextream side. And what's interesting here is the policy that was trained is not just, let's say, a physics-based policy, but he also trained the perception side of this, just to show that we can start to train actually RGB perception that is robust enough to transfer to the real world. Okay? So far, the focus has been just on showing kind of that there's hope that simulation actually can be used as a tool to train things and then transfer them actually robustly to the real world. Now I want to talk a bit about one aspect of simulation is how we can use it actually to scale up the data generation, because scaling is, of course, one of the key problems we want to look at. So how can you use simulation to train robots? There's different kind of techniques. On the one hand side, the key thing is, of course, in sim you can do reinforcement learning, and there's been a lot of success, especially also on the locomotion side, humanoids, how we can train reinforcement policies that transfer to the real world. I showed you some examples also from the industrial side here. The key advantage is that, of course, you can train very general policies and very complicated policies. The tricky piece is often coming up with the reward structure, and the training can be rather inefficient, so it's not quite an out-of-the-box experience, but there's been some exciting work, for example, from Jim's team at NVIDIA, collaboration with UPenn, the Eureka work, and the most recent Dr. Eureka, where they use actually LLMs to generate reward function code that you can then use to train your policy in. And there's other work also, of course, outside NVIDIA that is using similar related ideas. Another approach is, for example, using teleoperation, right? There's a lot of work where you have 3D environments, and now you teleoperate your robot to generate demonstration data in simulation, and then you can, for example, benchmark how well you can train on that. And then there's also work on mimic gen on how you can multiply these demonstrations. The nice thing is that you can train complicated and teach it complicated tasks. The problem is, of course, still the scaling, because it's just like real-world teleoperation. You still need people that generate that teleoperation data, right? So scaling is still kind of an issue here. Then another one is kind of where you use some form of planning in the loop, where you do kind of motion generation automatically. But even most of these settings, they don't do like fully automatic planning, and they still require quite some human effort to set up, for example, often waypoints and things like that. But the key trick here is, with respect to scaling, is setting these environments up is often very difficult. And also, automatic planning doesn't really work well for these context-rich tasks that I just showed you in the previous section. And finally, some direction that's going on right now that's also very exciting, just leveraging generative AI, LLMs, diffusion models to, for example, generate assets automatically, 3D assets, to generate tasks automatically, to place them in the environment, the objects, and then even have LLMs that generate solution plans. And there's work on using LLMs then even to come up with whether a certain part of the task should be done by reinforcement learning or automatic planning and things like that. So really exciting direction. But I think it's fair to say that at this point, it's not quite robust yet to really work well enough in this context. But I think this is a very promising direction that various labs are pursuing here. So what I want to talk about is just briefly about how we can actually leverage a technique that roboticists and AI researchers know very well, how we can leverage that, and that's called task and motion planning. So the idea of task and motion planning is that, for example, in an environment, you describe your system at two levels. One is kind of a logical representation of the state of the world, where you reason about constraints and preconditions and effects of actions, and then you have a lower level system that reasons about continuous motion and things like that. So for example, here you could imagine the robot. The goal of the robot is cook the content of the tea kettle. The tea kettle is this thing here down here labeled A. And how you represent that to the robot is you would say the initial state that describes what is the configuration, joint configuration of the robot, what's the position of the tea kettle, is the gripper open or closed, and things like that. And then you describe the goal as, well, the tea kettle, the content should be cooked. And then it automatically generates a task plan that solves this task. Okay, we don't need to go into any details here, but the key trick is it needs to plan both at the continuous level and at the higher level abstraction of these actions, right? And this can be done very efficiently, and then in this case, for example, the outcome is a full kind of motion plan for the robot. The nice thing is that this can be done fully automated. In the real world, this is still very difficult because of partial observability, but the cool thing is, since we are in simulated environments, we have access to all the state information that these task and motion planners actually need, right? And once we can generate that kind of data, how we can go about using it for training is on the so first we generate environments and tasks, right? And that, of course, requires typically still manual setup. And then the one limitation of this task and motion planning system is that typically they perform planning, let's say, in a kinematic space, which means they don't do full physics-based simulation. But what you can do is you can now take these plans generated by the TAMP system and you can run it through a physics simulator like Isaac Sim, and then you can throw away the demonstrations that don't work and just keep the demonstrations that are kind of verified by the physics simulator. And then you do behavior cloning, right? Because we have all the data, we can simulate the perception and everything, and then hopefully successfully deployed in the real world. And we did this last year with Murtaza as an intern on this work called Optimus, and he then trained a relatively small still transformer model on these tasks, a perception-based transformer model, and then was able to train policies for all these kind of settings here. And it works actually already very well. But what this highlights is really, again, that we can scale these demonstrations now automatically, and this was like 250,000 demonstrations, but you can imagine, of course, where we need to go is like billions of demonstrations and more task variety. Now, one limitation of this kind of work is what many people will also, of course, realize is that TAMP isn't quite good enough yet to solve all tasks, right? There's a lot of stuff for which we need RL or teleoperation. So the idea of this other line of work was, it's called human-in-the-loop TAMP, where the idea is if you want to train a task like this one that I show here on the left, which I'm sure there's many instances of it now, right? Like making espresso, handling the espresso machine. It turns out that the context-rich interaction, the task and motion planning system doesn't quite necessarily get those right. So the idea could be, how can we break this task into pieces where we can leverage the TAMP solutions and other pieces where we then use, for example, teleoperation, right? So the idea is here to mix teleoperation, human teleoperation with TAMP, and then what you get at the end is a system that kind of does planning for solving tasks, but it uses, let's say, model-based TAMP solutions for parts where it can, and for other parts, it uses human teleoperation trained data. Right, let me just show you here what this looks like. Here during training, for example, in this task, for certain parts, it's using TAMP, and for these insertion tasks that are much harder, it hands control over to a human teleoperator, and then the human teleoperator does the harder one, okay? The advantage is there's much less burden on the human teleoperator because you only need to do the things that the TAMP system can't do, and we also incorporate these human teleoperation action into the TAMP process, which means they become actions over which the TAMP system can reason, which means they also have preconditions and effects and things like that. And we can learn these from the data as well. We can also parallelize that across a multiple TAMP system, which means one human could, for example, instead of waiting until the TAMP step is solved, we can just have, whatever, hundreds of robots being trained with temp, and whenever the teleoperation has to take over, that is the piece that is handed to a human, and the human just does one teleoperation after the other one. Okay? And once this is trained, we can then deploy it. And even during deployment, of course, there's also this kind of mixture between temp and automatically trained policies from the human data. Okay? We showed also that on the one hand side, on the left side is the time it takes to train these models. On the right side is success rate, where blue is not using temp, only using human teleoperation, and the purple is where we have this combination of teleoperation and temp. And on the one hand side, of course, combining it saves time because the human doesn't need to do all the work. And it actually turns out that it also generates more robust policies. On the one hand side, because we only learn the pieces that we need to learn, and also because actually automatically generated solutions are somewhat more consistent, which turns out to be easier for behavior cloning. Okay? Now, this also works actually in the real world. This is not sim to real, this is real to real. But you will see here also that now, after training, the system can. And this now works from far less demonstrations than what we used to have to do beforehand. Okay, and on the right side is, of course, we can also do the espresso thingy. And you can see that the model is just automatically switching between temp policy and the pieces that the reinforcement learning policy trained, or the behavior cloning policy learned here. Okay. And you can imagine, of course, where this is going now is as a next step, incorporate reinforcement learning into this framework too, right? So that we have a system that combines automatic planning with human teleoperation when necessary, and reinforcement learning also for certain parts where it's necessary, because these different techniques have different advantages and limitations, and we want to actually, in the end, cover all of this, right? But I think with this combination, we can really start thinking about generating very, very large-scale data sets that we can then use for behavior cloning of much more capable systems. One question is also on the scene generation. So, for example, we also now want to move to doing all these demonstrations and training in articulated kitchen scenes. We have some work going on that's led by Clemens Ebner, scene synthesizer, where we can, all the scenes here you can see are actually procedurally generated. So we can generate millions of them, right? It's also automated with the texture generation. The layout can be changed and randomized over. And what's important, of course, is that these kitchens are also consistent with the physics simulator. So we can do full physics simulation in them, and we can do then the task and motion planning kind of task in these environments too, by placing objects and things like that. So this is still ongoing work. Another work I want to just plug on Friday, I actually present the 5-minute talk for your deformer, which is some work that my student Zoe did on actually using LLMs and diffusion models to train a system that can take an image from the internet of a kitchen, as you can see here, and then automatically generate a URDF of the scene, right? Which, of course, if it would work perfectly well, that is the ultimate solution, right? But, of course, the robustness, as we see with many of these techniques, is not quite there yet. And I guess the system on the left is just more, let's call it sim-ready, as some of this work on the right. Okay, so this is about scaling. So I think now where we're going is we really have, on the one hand side, we have the randomization capabilities in sim to train these policies, and we can scale them up. And now I want to talk about how we can connect all of this to actually going towards these more large-scale integrated large vision model or vision language models. And a lot of this is actually kind of independent of whether the data comes from a robot or whether it comes from simulated data, right? So how should we even think about integrating these large-scale models with robot capabilities, or the other way around, right? On the one hand side, there's a lot of work. I just pointed two of the earlier work. One is also from us. Ishika, I think, is also here, proc prompt. But the idea is where we take, for example, we leverage LLMs or vision language models, right? And the input is, for example, some text, an image to the model, and the model then provides some way of calling, for example, a skill that the robot then executes, right? So, for example, you could imagine a skill could be pick up an object or open a drawer or something like that, right? And the idea is that we just take an off-the-shelf model, and that then generates a bounding box or something like that, and the robot then executes on this. I would call this kind of a loose integration, right? Because we are really at the mercy of how good these vision language models are, right? Because we're just using them and then and operate on the robot skill level for us. And of course, this has been very promising, good results we're seeing a lot, especially using also these prompting techniques. There's this what's called in-context learning, which is kind of a more complex idea of prompting. But again, I think the limitation is really that we're just leveraging these models as they are. Another approach is we just do all end-to-end training, where we say we need to train a single model that takes in text, images, and, for example, information about the robot state or history of robot state, and the output is really kind of at the control level. And when I say control level, for the controls people here, I'm not talking about whatever, 1,000 hertz or something like that, but anything that is related, let's say, for example, to joint configuration, right? So even 10 hertz or so in this context, let's call it control, okay? So there's still a lower level control underneath this. But what I mean is that the output of the model is in the configuration or workspace of the robot itself, right? And we've seen some work, I think also super exciting, from Google DeepMind RT2 and the most recent OpenVLA models, where the idea is you're using these vision language models and you're treating articulations and actions kind of like language, right? And you're either repurposing existing language tokens to reason about these actions. I think this is what RT2 did, for example, or you just fine-tune enough and use these outputs just as numbers or things like that. I think the limitation with this is it's just really difficult to build models that just monolithic models that solve all these tasks that we want them to solve, right? And also conceptually, I think from a robotics perspective, I think we often think about some more hierarchical representations, right? Where you say you have a lower frame rate, higher level semantic reasoning, and then you have a higher frame rate conditioned control planning reasoning, right? We see this in autonomous navigation and also manipulation reasoning. So again, I think this is just very difficult to really scale to get the quality of models that we want. And I think for me, kind of the way I'm thinking right now is kind of the truth would be somewhere in the middle, where we have at the input we have text, image, robot state information, and then we have dedicated vision language action models, which means these are not necessarily off-the-shelf models, but these are models that are dedicated also to the robotic settings. And then these models somehow, there's an interface layer, and these models somehow communicate to a low-level control policy what it should do, right? And there's actually a lot of work going on kind of with this thinking in mind. On the lower level policies, you could imagine these could be diffusion kind of policies. This interface between the upper model and the lower model, there are people looking at kind of points or bounding boxes where, for example, the model could say, pick up the object in the bounding box, right? And that is how you communicate between the upper and lower level. Or it could be trajectories and things like that into the images. But I think ultimately, I think where we want to go is it should just be embeddings, right? Because that is what the strength of these models is, reasoning about these learned vector spaces and how to communicate with each other. I want to give you a little bit more context on that. Yeah, I think I'm pretty reasonably good on time here. So just as an example for the first approach where you just take off-the-shelf models is we did this work proc prompt where the idea is, for example, you have this image on the left and you have a task like sort the fruits on the plate and the bottles in the box. And what it did in proc prompt was we used GPT to generate Python code, okay? And through examples, through these prompting examples, we informed GPT what the form that code should look like, right? So for example, we told it what are the actions that the robot can actually execute, what are the objects that are currently in the scene, and then you give it some examples of what action might look like. This is a very simple one, but we also did more complex ones. And now imagine if you want to do something like this, and you look at the sort fruit problem here, then what you do is you just feed that into the GPT and say, okay, here's a function that we call sort fruits on plate and bottles in box. The naming is actually needs to have a meaning. And then you have a vision model that detects the objects on the table. There's a banana, a bottle, da-da-da. So these are also with pre-trained vision models. And then you ask the language model just to say, okay, now generate Python code that executes this, right? And then the Python code just calls these lower level skills that we trained for object manipulation, and then it actually works very well. Okay? This is what I call the somewhat loose integration, because we're just leveraging these models as they are, right? The problem with doing this is that there's just limitations how good these models are for robotics tasks. I think many of you are aware that it's often they have astonishingly good results, but then as a roboticist, when you look at the kind of how well they do on 3D reasoning and things like that, then suddenly you realize they're clearly not good enough yet, right? So in this context of placing objects and picking up objects, there's some very recent work. I just want to give you one example here on that Monsieur Mentao is doing on leveraging VLMs for spatial reasoning. So imagine on the left side, let's look at this image up here. Yeah, you see my mouse. This image, the scene, and the task would be place a green container between the yellow paper wipe and the white cup. And you would imagine that that should not be too hard, right? And you can actually get a language model to generate input for a vision language model that says then locate the free space between the yellow paper wipe and the white cup. And there is vision language models that are trained for these kind of tasks. And I'm just showing you the result that we're getting from 3 of them. This one is a QNVL pivot, which is using a different kind of interface, and GPT-4V. And you can see that none of them actually, this generates a bounding box around the mark. This one generates a dot somewhere down here, which is clearly not between the two. GPT-4V thinks, okay, I should label the yellow paper wipe. So clearly, they're not solving this task properly yet, right? And on the right is just another example where you say, locate the inside of the white cup, and none of them really succeed. The closest is GPT-4V, where it at least labels the cup, but this one here looks at the paper wipes and things like that. So the idea was, how can we improve the capabilities of such models to become better at these tasks, because they're really important for robotics. And it turns out for placement, the interesting aspect is the models are particularly bad at reasoning about placement in free space, and that is because they are trained on data sets that refer to objects. There are not many data sets out there that actually refer to free space, because, I mean, who labels free space in YouTube videos or something like that, or on the internet, right? So that is why they are not good at this, so we need to generate more data. In this context, I want to just briefly step back and say how these VLMs are actually trained. And there's various of these what called open source VLMs. Open source in the sense that you can download checkpoints and you can download the weights and the structure of these models. And because you can download that, you can also fine-tune them. You can keep on training them. And this is just the Lava model, which is, I think, one of the best known models. And what they do is, so to train them, they take a pre-trained language model, okay, and a separately pre-trained image encoder. Let's do clip or something like that, okay. I don't know exactly which one, but it doesn't matter, but a pre-trained image encoder model. And now the problem is, if you want to combine the image model and the language model, that they need to be somehow aligned. They need to learn how to communicate, right? So what they do is the following. In a first step, they keep the language model, okay, because the language model is just trained on so much data that is super capable, supposedly already, right? And then they take the image model and learn a projection from the image tokens, the image encodings, into the language space such that the language model can reason about these images. Okay? So there's a data set that they use that contains images annotated with desired outputs, and then they fine-tune this projection layer that maps image from image space into language space, and then after that, they actually fine-tune the whole model on these tasks. Okay? The advantage is that you don't need internet scale data to do this, but you're just fine-tuning it, and this can be done much, much faster, right? Another network out there that's actually from NVIDIA, VLA, that is also doing a similar related approach. They did some different techniques for the fine-tuning, but overall, it's in spirit very similar. And the capabilities, if we look at this exam, it's pretty astonishing, right? I mean, I'm afraid I don't have time to go through everything, but it's kind of here, it's analyzing the image, it sees the bottles, knows which bottle, it relates the bottles to the text on the menu and to the price, and then it can tell you how much you would pay for the bottles on the table, right? So pretty amazing. But again, they're pretty bad at the kind of reasoning that we need for robotics, right? So going back to this task of placing objects in the scene, we did this work with RoboPoint, where the idea is we want to fine-tune the model for spatial reasoning, and what we did is we generated in simulation, again, randomized scenes, these scenes that I just showed you also previously. We put objects into the scene, all simulated, and then, of course, because it's pretty easy to figure out spatial relationships like behind, left, and between, because we have ground truth information for these objects, and then we can generate a labeled data set that says, okay, here's an image, and here's a bounding box, for example, tell me which object is behind it and things like that. So we can do that in a fully automatic way. And then we can use the same fine-tuning approach that they use for the lava kind of models with our data in addition to this, right? So we use our data and some vision data as well to fine-tune it. So for example, again, during fine-tuning, the input is an image here on the left, and also the text that we automatically generate that says here like, whatever, find a few points in the vacant area to the left of the object marked by the red box. It's pretty awkward, but the model can actually handle that. And the desired output is actually pixel coordinates for the language model. So the language model outputs pixel coordinates that it thinks are positions where there is the free space, okay? And we can fine-tune that, and it actually works pretty well. Here's some examples. We compared different techniques. But for example, these bounding boxes are outputs from GPT-4V, and it's getting something pretty well. But if you look at, for example, the one where I'm putting my mouse, where it says the dinosaur model at the bottom, it's getting that kind of very wrong. Or between the green block and the white block in the back, it's labeling that space, but it should actually label this space down here. And now if I switch to the output from our model, the fine-tuned large-scale model, we're getting significantly better results on that, okay, through these points in the images. And of course, then you can use this on a real robot to know where to place it. We also did some evaluation. Details are not necessary, but the key is it's significantly better than any of these other models, even if you do in-context learning or things like that. I'm getting very close. And oh yeah, one important aspect here is, so we did this fine-tuning, but the model remains its language open world capabilities. So there are these benchmark data sets that you test these large models on, and after training, the performance on these general benchmarks is as good as it was before, at least as good. Okay, so we're not losing those capabilities, but we can fine-tune it for robot tasks, right? So I think on the one hand side, what we've seen so far is that these fine-tuning these large-scale VLMs is very promising, but it only works for tasks that are somewhat matched to what they're already trained on. And I think for robotics, we really need much more capable models. It's really, truly vision, language, action models. And for those, I think we need to go beyond fine-tuning because we need to introduce, I think, new modalities to do that. And that, the very last piece here, is where I think somehow, in some form, we need to go. And I want to show this is one model that's coming out of NVIDIA, but there's a whole community working on, they're called multimodal large language models. And this is kind of what XVILA, what the team did here, is they trained something like Lava, right, like vision and language, but they said we train a model that takes as input not only language and images, but also videos and audio, for example. And they're leveraging pre-trained encoders for all of these, right, that are very robust pre-trained models. And then they say we also have output models that can generate output in this form. So they have diffusion models that can generate, of course, language, images, video. You can even use stable diffusion in here or something like that, and also audio. Okay, and then what you do is you train all of this system together, and through pairwise annotations, details, I'll point to, there's an archive paper out there. But the key trick is now that we have like these really large-scale models that can communicate across these different modalities. I don't have time to show this example, but it's, of course, impressive. Otherwise, I wouldn't have shown it. But now, getting back to robotics, I think where we need to go is, instead of saying we just use, for example, vision and language and try to generate robot controls by treating controls as if they were language, I think we need to think about adding new modalities to these kind of models, right? And these new modalities should include things like joint state. They should reason about dynamics in the world, or physical dynamics. They should reason about touch and also, for example, depth information, right? Because we need these models to become much better at 3D reasoning. And then also on the output side, we need to have diffusion models that, for example, can generate desired output. And that is exactly what diffusion models, what we're seeing right now, right? Many of these diffusion actor kind of techniques out there, I think they can be connected to these large-scale models through this multimodal training and this idea of training embeddings and connecting them. I think this is a super exciting direction to go into, right? Because again, we need to connect these models very tightly. And now I'm coming to my summary slide. Is that okay? Oh, yeah. I'm just taking away from your coffee break, so don't feel too guilty. But, to get back to the question asked, there's still a way to go, I think, till we're really at a robot GPT kind of moment, right? There are some promising ideas and glimpses of things that are starting to work, but we're not there yet. And leveraging these existing techniques is also very powerful and promising, but there's a clear ceiling on how far we can get with that, right? So I think what we as a robotics community need to do is we really need to get involved in training and expanding these large models, right? Which means we cannot just be consumers of the things that the vision and language and learning people give us. We need to get into the business ourselves because we are the ones who know about 3D understanding, 3D reasoning, control policies and things like that. So again, we need to make sure that these open world models have robust 3D geometric understanding. We need to get involved with benchmarking and things like that. And I think these multimodal LLMs that I just described, I think is a very promising direction in which we can go to have a fully integrated idea of vision, language, action, and robotics reasoning. And of course, obviously, I think simulation can play a really important role here to generate the kind of data that I think we need to train these very large models and capabilities. And with that, I'll thank you, and I'll thank all the people, of course, that were involved in this. Thank you very much.
Perhaps we can take 4 or 5 minutes out of the poster session and the coffee break for some questions for a very interesting talk. We have one here.
Yeah, really a great talk. May I ask, what is your opinion about the GPT-4o? Maybe because it can understand the video, and maybe with GPT-5 it can fully understand the video. Will it be really helpful for manipulation tasks and everyday operation if it can understand video? Maybe it can do everything, right? So thanks.
Yeah, that's a great question, GPT. Or even when you look at Sora or these kind of things, right? When you look at the videos these models can generate, there's clearly some kind of 3D understanding in there, right? But from my experience, on the one hand side, I'm really looking forward to any improvements on these models, and I'm sure they're gonna improve dramatically, right? And we should always be ready to leverage those capabilities and improvements. But at the same time, I think without a dedicated focus on training models for robotics, I think it's not gonna be enough to just leverage these models, because whenever we apply them in the robotics domain, we do see that there are quite some limitations still, right? Even when the first results you see look very, very promising, but I think in robotics the problem is it really reveals immediately if something doesn't work well enough.
Question over there.
Do you have any recommendation to deal with flexible objects on robotics instead of come back and retrain everything for all the instances of different forces of each of the models as the collections you mentioned? Do you think that we can reach a point where we can use real-time diffusion models for specific instances and forces that we can take from the robot in real time?
Yeah, so do you mean by flexible, you mean deformable objects or just, okay. Yeah. Because there's also flexibility with respect to the types and objects and kind of things you can do with them. With respect to deformable objects, I think on the one hand side, going back to simulation, there's some promising work that, for example, we've also done on speeding up deformable object simulation. The problem is that often these techniques are way too slow because it's often finite element methods and things like that. So there's, again, on the one hand side, some promise on the simulation side, and on the other hand, yeah, I guess just some more real-world data that we can augment with simulation data. I think there's various tasks where it's just going to be really, really hard to just do everything in simulation, right? So I think we need a combination of simulation data and real data for that.
Hello. Yeah, here. So let's say I wanted to follow your advice and do this multimodal end-to-end model thing. I feel that there's something important missing on that slide, which is that, for example, for a language model, the architecture of transformers and the task of masking are really effective, like inductive bias for that problem. And so I guess for robotics, what's the analogy? You know, what do you think is the role of the model and the task, and how should they change if I'm doing this kind of thing for robotics?
That is a great question. And I have no idea, because on the one hand, there's always a question, right? Is it model structure or is it data, right? And I don't think anybody can claim they know for sure what it's going to be. So on the one hand side, you could argue maybe if we use a vanilla transformer architecture, let's say with multi-view, so that I believe learning manipulation policies from a single fixed camera pose is always going to be too brittle. I do believe in some kind of depth representation, even on the input side, multi-view or something like that. But who knows, if you train them on enough data, maybe they can do the accurate, for example, precise 3D reasoning. At the same time, you might have seen in the morning, Ankit gave a talk on this RVT2, for example, where we're also looking at some more specialized transformer architectures that are better suited for 3D reasoning. And when you go back to, for example, this idea here, if you go here on the right side, on the output side, that is where, for example, then these kind of models could come in, right? You could imagine that the high-level reasoning of a model is maybe more in visual 2D space, and the low-level control policy space, that is more where you do explicit 3D reasoning, right? There's many, many choices, unfortunately, that we have to explore, but I think we need to get started on investigating those choices in a more thorough way by benchmarking them and really seeing what works better, because I don't think anybody has the perfect answer to that.
Thank you.
Is there any last question?
Hi, over here. Sorry, to your right.
Dieter on the right.
Anyway, great talk. I was just wondering, you talked about some of the limitations of getting demonstrations in simulation, and you proposed human-in-the-loop TAMP, which is still going to be bottlenecked by humans, right? So I'm curious, we see that for ChatGPT, you really need kind of internet-scaled data to make it learn something interesting. But if you're bottlenecked by humans providing demonstrations, then we can't really scale up simulation in the way we want, right? So what's your thought on that?
Yeah, that's why I put in the that also like the generative AI-driven simulation techniques, right? I think ultimately, again, the good thing is with all the progress we are seeing, let's say outside of robotics, image generation, video generation, we should not view this as, oh, they're solving all our problems. We should view this as opportunities for us to use them. And I think leveraging those techniques, for example, on the simulation side is clearly a very promising direction. Getting the kind of robustness into these techniques is, of course, still kind of an open question. And I can imagine it's going to be ultimately a combination, right, of these techniques and the more, let's say, traditional simulation kind of techniques. But I think it's only going to get better, right? So I think that's actually a positive thing that we see there.
Dieter, can I ask a very high-level question?
Yeah.
So for many academics, it's actually difficult to get the resources to work with these large models. Yeah. So it seems the audience agrees.
Yeah.
So what's your opinion? What should academics do and how can they progress?
It's tricky. Some of them, actually, that's why I'm also so, let's say, bullish on these multimodal and large-scale open source models, because fine-tuning them can actually be done at academic scale, right? So that's the whole idea, that you don't need to be OpenAI, NVIDIA, Meta, or Google in order to do this kind of stuff, right? So the fine-tuning that went out on this RoboPoint that was done, it's still, what was it, A100 for a good bunch of hours, but no, but I mean, we need to face the reality that you do need some kind of, let's say, I just call it parallelized processing capabilities, but I think it's not hopeless, right? So, and if you wanna, no, I mean, hopeless in the sense of even if you wanna play the game with the large-scale models, right? It's not a close community that can do this. I think the open source models is where everybody can get involved in. And I think that's really important, and that's what we really wanna push forward. That's a promising direction. And if you wanna, I mean, train a model like ChatGPT from, that's just, I don't know who can do this.
Great. Let's thank Dieter again.
Thank you.
Welcome back, everybody, to this last session of the day. Please take your seats. My name is Nico Sunderhoff. I'm with the QUT Center for Robotics, and together with Anoop Arur from Amazon Robotics, it's our great pleasure to present and chair this last session of the day, which is all about navigation. We're going to make a little change in the program and actually start with the paper number 4. So for the helpful people up there, if we could please load the video for number 4. There's no author for this paper, so we'll just start playing this. And then hopefully we'll have the second author ready to present paper number 2 after that. Here we go.
Hello everyone, my name is Amir Hossein Chahe and I'm presenting our work on dynamic adversarial attacks on autonomous driving systems. Autonomous vehicles' decision-making systems must be robust against adversarial attacks. Among these, physical adversarial examples are particularly implementable and pose significant risks. These traditional methods typically involve placing patches directly on target object. However, the effectiveness of such attacks varies with changes in angles, distances, and lighting conditions as highlighted by previous studies. The image in this slide provides an overview of how attack success rates decrease under different environmental conditions. Our motivation is to strengthen the security of autonomous driving systems by probing potential vulnerabilities through sophisticated attacks. Our objective is to challenge the resilience of these systems by manipulating their perception and decision-making processes. We propose using dynamic adversarial patches displayed on a moving vehicle's screen to deceive object detection models. Our work makes 4 significant contributions. First, we introduce a dynamic adversarial patch approach. Second, we develop the Screen Image Transformation Network, SITNet. Third, we integrate positional loss into the training process to increase the success rate of the attack. Lastly, we shift the focus from merely attacking perceptual systems to influencing the decision-making algorithm of autonomous vehicles. Here, we outline our attack and experiment setup, in which 2 robot cars, namely patch car and the camera car, are interacting with each other at an intersection with a traffic sign. The camera card uses a DNN-based object detector and LiDAR to perceive its environment. The patch card displays adversarial patches on its screen to mislead the camera card. So our goal is to maximize the probability that the object detector misclassifies traffic signs, impacting the decision-making process, where the F is the detector model, phi is the input image, theta is the model weights, P and B are the prediction confidences and bounding boxes, T is the transformed patch, X is the benign images, SC and SP are the position of the cores, phi is the environmental parameter. We designed the objective function for generating the adversarial patch to optimize both the prediction confidence and the positional accuracy. It maximizes the probability of the target class and the overlap between the predicted and actual bounding box of the target class. We collected a dataset with over 8,000 synchronized LiDAR and image recordings. The data were clustered based on the positions of the patch card and target, which is traffic signs. This clustering helps in optimizing patches for a specific positional context, enhancing the attack's effectiveness. There are significant differences between how patches appear in simulation versus in real world. Our SIGNET helps mitigate these differences. The network simulates the color and contrast transformation that occur when patches are displayed on a screen, ensuring that the adversarial patches remain effective in real-world conditions. SIGNET is trained using a weighted sum of mean squared error, perceptual, and total variation loss. These include MSE for pixel-wise differences between the predicted and real-world images, where n represents the total number of pixels in the image. The perceptual loss measures the difference in style between images at the feature level rather than the pixel level, utilizing the first known layer of the pre-trained VGG19 network to extract feature maps, with m being the total number of elements in these feature maps. Additionally, total variation loss is employed to enhance the smoothness of the upload images. This pipeline illustrates the process for optimizing adversarial patches, which includes clustering the dataset, applying transformations via SIGNET, and optimizing the patches through backpropagation. This structured approach enhances the robustness and adaptability of the patches. Here we demonstrate dynamic adversarial patches where the camera card and screen card arrive at an intersection. The patch on the screen card can mislead the camera card to detect a go sign as a stop sign, allowing the screen card to pass first. We implement this in various backgrounds and lighting conditions to showcase the robustness and effectiveness of the dynamic patches. For full video, please scan the QR code. We compare the success rates of dynamic, static, and printed patches in deceiving object detection models. Dynamic patches consistently show higher success rates across different types of traffic signs compared to static and printed patches. The dynamic patches maintain their effectiveness across a wider range of distance and angles, proving their robustness in real-world conditions. In conclusion, we introduced dynamic adversarial patches displayed on moving vehicles. Our SIGNET simulates real-world environmental effects, and our experiments demonstrate high success rates in deceiving autonomous systems. Future work will focus on developing real-time defense strategies to enhance the robustness of autonomous driving systems. Thank you for your attention. For further inquiries, you can contact me at ac4462@drexel.edu.
All right, so that was paper number 4. Unfortunately, none of the authors could make it to the conference, so if you have any questions, please get in touch with the authors directly. That brings us to paper number 2. Demonstrating Arena 3.0, Advancing Social Navigation in Crowded Environments.
Okay, hello everyone. My name is Lin Kestner. I'm a postdoc at Harold So's lab at National University of Singapore, presenting a paper, Arena 3.0, Advancing Social Navigation in Crowded Environments. This is a work done in collaboration with my previous uni in TU Berlin and TU Munich. Okay, so why do we need Arena 3.0? We all know that simulators are an essential part of the development cycle in most robotic applications. Especially for navigation, more specifically social navigation, we will need to have very close replicas of realistic worlds to test our approaches. Arena 3.0 addresses 4 main problems that currently exist in simulations. First, realistic human behavior is very difficult to simulate, and lots of simulators use oversimplified models for a simulation. Secondly, generating simulations of environments is very tedious, especially for realistic ones, and time-consuming. Third, to evaluate and assess your approaches, unified benchmarks must be conducted, which leads us to our fourth problem, that although academic papers and new approaches appear on a daily basis, it is oftentimes a great struggle to reproduce and integrate those into your simulators, because everyone is using their own platform setup or specific settings that may work for them but not for you. So to address all these problems, Arena 3.0 provides a variety of modules and features. So let's have a look at the key features of Arena 3.0. So right now we have over 20 state-of-the-art navigation approaches, ranging from classic approaches such as DWA, TEP, or learning-based approaches trained with DRL or imitation learning. Our platform also includes 15 different robots spanning from 4 different kinematics, such as quadrupeds, car-like robots, or holonomic ones. And to address the aforementioned problem of the human simulation, we include and extended 6 different social force models to choose, ranging from very simplified models such as Awkward to models such as the deep social force model, which was actually trained on real human movement data. And one key feature of our simulator is actually a world generation tool, which can generate randomized worlds in specific settings, such as canteens, offices, or warehouses. And this is abstracted across 3 different simulators. We also provide 10 different task modes, ranging from randomized tasks, where everything is just planned randomly, to very specific scenarios, such as rescue or exploration missions. And we also cover 40 different real replicas of environments, such as the NUS campus or hospitals, which you can select and run your approaches in. Okay, let's have a look at the system design of our arena. So it aims to be very modular and abstracted, so you can plug and play the modules. The first module contains tools to generate worlds and scenarios, so you can either choose our randomized world generator and select from default worlds, or even build your own world using arena tools. Next is the population of those crowds. So for that we have 6 different social force models and also extended them with human-robot interactions and other social interactions. Development of navigation planners happens in the 3rd module, which is based on move-based flags, and we also included a number of state-of-the-art planners. Due to the abstract design, all these functions can be executed on 3 different simulators based on your specific needs. Finally, with the evaluation class, we can record data from these simulations, generate plots, benchmark them, and assess the results. These 3 main modules are indicated as Arena Core, which are, again, completely abstracted and can be run across the 3 simulators. Here you can see some demonstrations of the world generation process. On top, we can see the generation of canteens. At the bottom, we see the generation of different mazes. The generations happen at runtime, and we can observe that each world is completely randomized and different to the previous ones, which is essential for training and testing and have a variety of different environments. We have many more environments and exciting features, which we will demonstrate in the demo hall. Come to our demonstrations to see main features, such as I will demonstrate the generation of thousands of different simulations across 3 different simulators. We also showcase different social force models, planners, robots. Another nice feature is our variety of different task modes for benchmarking, such as random mode or specific scenarios. And we also will showcase the new version of Arena Web, which is our companion web application in which you can design your own world scenarios, even start test and training runs without even installing Arena, totally from the web. To experience all those features live, come to our demonstrations again, check out our open source project. Everything is open source. So we will also present even newer features of this Arena in another workshop called Arena 3.5 on Friday at the social navigation workshop. So make sure to swing by. That's it. Thank you very much.
Thank you, Lin. Are there any questions from the audience? Any question? I can ask a first question. How realistic are the behaviors of the simulated humans? Did you get a chance to run any evaluation, or is there any quantifiable, similarity between real humans and what the simulated ones are doing?
Yes, a very good question. So, yeah, this is one of the main issues, of course, with simulators. We experience, of course, not so realistic behaviors in our previous versions, where we just use very simplified social force models. So now we integrated, that's why we integrated more social force models, such as the deep social force model, which was trained on the real human data set. Of course, we don't have any specific metrics that we can test. It's just subjective for now. We just say, okay, it looks more realistic. But yeah, it just looks more realistic to the previous versions. But in future, we plan actually for our next paper to include like more models which will model these behaviors more realistically. Yeah, but currently we don't have any metrics to assess that. Yeah.
Thank you. Any question from the audience? There's one in the front row here.
Hey, very interesting work. Thank you for the presentation. So my question is about how exactly you generated the furnitures and like the placement of them in the world. So I noticed in the office scenario, they are kind of very neatly aligned, but I think in restaurant scenarios, they are like kind of very random. But I think in the real world, like in restaurants, offices, they are like the placement of the furnitures, they are usually very structured and you know, they follow like a certain pattern. Just wondering how to like generate them according to these kind of
Yes,
patterns.
very good question. Yeah, yeah, you're right. Like currently, the furniture is just spawned randomly at random positions. It's very hard to have like some kind of structure or something. What we are working on is incorporating some semantics to it. Actually, for our fourth version, Arena 4, we also incorporate some LLMs to have more semantics in it. For example, in the chair is always next to the table, placed next to the door or something like this. So then you will get a more structured environment, of course. For now, it's just completely randomized, focusing on the obstacle avoidance of the robots and yeah, to have a very challenging environment for the robot. Yeah.
And one quick question up there.
Thank you. Really nice tool that you've developed. Any plans to define trajectories of humans so that they resemble sort of like hospital behavior or warehouse behavior, factory behavior, et cetera, et cetera?
Could you repeat the question again?
Do you have any plans of integrating specific behaviors of humans in the environment rather than having it completely random? Because they differ in different environments. Humans behave differently, right? Yeah.
Yes, very good question. Yes. This is also actually tackled currently by our team. We want to integrate more human object interactions, actually. For example, humans moving the chair, or at a hospital, maybe they have to interact with different furniture or human-robot interactions. Yes, we are currently integrating this, which is a little bit more complicated than it sounds. But yeah, we are working on it. So it is ongoing work. Hopefully, it will be presented next year. Yeah. Okay.
All right, let's thank the speaker again. And next up is paper number 3, Rack Driver.
Can I start? Hey, hello everyone. My name is Jian Hao, and today I'm going to present to you our AG driver generalizable driving explanations with retrieval augmented in context learning in multimodal large language model. And this is a joint work with my collaborators and supervisors, Shuyang, Daniel, Bo, Paul, Lars, and Matt in University of Oxford. Sorry, just a second. Yeah, so the idea of this works, we want to make the autonomous vehicle decision-making process understandable and transparent to human. Since currently there's learning-based models, the inference process is not interpretable, so which makes the general public, including the passengers, cannot just easily trust this promising technology. So one way we find is very effective is we want to provide these natural language explanations to interpret these driving actions by all kinds of agents. So thanks to the development of these foundation models, including multimodal large language models, we can now make these models, as I said, explainable and a generalizable decision-making agent specifically for the purpose of driving. That is to make it to perform this driving action explanation and justification. Yeah, so here's the system overview of our multimodal large language model with the retrieval augmented mechanism. So the first things the model do is it takes in these video frames as well as a few seconds past signals as the representation of the current driving scenario. And then this is going to be projected through a linear layer into a hybrid representation, which is then going to be used as a query to search in a database where similar experience from the human expert demonstration is going to be fetched and then projected and then prefixed to the current driving scenario, which is as in-context learning examples. And then all these embeddings is going to be projected through the text encoder as another cross-modality projector, which is then processed through the large language model as the decision-making agent. And then the decoder will then turn the embedding back to the language space and perform the tasks, including driving action justification and the next control signal prediction based on the task instruction. So the key contribution of our work lies in this retrieval augmented generation mechanism. The idea is, in autonomous driving, the usually problematic cases comes in those long tail edge cases where you don't have that in your in-distribution training data set. So if you have your training model trained on the in-distribution data, it cannot usually work well in the out-of-distribution generalization cases. So what we want to do is we want to try to leverage these very few cases, perhaps like the human demonstration, and we want to deploy that in the inference time and to see if it can actually help the model to generalize. So as we just described, we use this current driving experience to query from a database, and we fetch some similar experience in the past data, in the experience database with the human expert annotation, such that is the correct action and correct justification to do. Then we use the in-context learning capacity of multimodal large language model, which allow us to improve this inference at deployment time. So to quantitatively evaluate our method, we train our model on the training split of BDDX, and then we test it on the test split of BDDX as an in-distribution evaluation. On top of it, we also test our model on SACS London, which is a different set of data collected by our own on a very different location from BDDX as a zero-shot out-of-distribution generalization cases. And as you can see in the table here, we deliver promising improvement by using this in-context learning mechanism compared to all these baselines, both in distribution and out-of-distribution performance. Sorry about the pace. Yeah, so here are some qualitative examples of the actual predictions from the model. And this is from the in-distribution of BDX test set. As you can see over there, it's a bit quick, but like the explanation is in general sensible. And also here is some out-of-distribution performance from the SACS data set. Yeah, thanks for listening.
Thank you. Any questions from the audience? There's a couple here in the front, but somewhere in the back was first.
I have a question. Thank you for the talk. I have a question regarding using the LLM in the autonomous driving scenario, because LLM is not a really fast or real-time model. What's your take on this, like when it's applied in the real-world scenario?
Sorry.
So when you apply your model in the real-world scenario, is it too slow? Like?
Yes, thanks for the question. So I assume you're asking about inference time.
Yes, yes.
Yeah. So currently, this is not deployed on the real robot at real time. So the model currently runs only at 1 or 2 hertz, which is indeed quite slow. So the video sequence we provide is about taking 8 frames. So if you have a video, for example, like a very low resolution 4 hertz, you can have a 2 seconds video each time. So each inference you are processing like a video for 2 seconds, then it can more or less run in real time. But yes, we haven't really making a closed loop fashion for the evaluation. But like the general idea is to have it to perform this explainable decision making and explain the inference process to human.
The orange cube up there.
Thank you very much for your talk. I may have a naive question here.
Sorry, could you just raise your... over
all
here.
the way to the back. Hi. So I'm not familiar with the architecture of your system. Are you explaining the video input, or are you using also the command or the policy that the car is executing?
Yes, thanks for the question. So the input of this model is a series of video frames. Yes, it's the driving video from the first person view camera, and also some past. So the control signal, like the acceleration, the course, and the speed of this corresponding to this video. So these are the only two inputs to this video. And the next will be the task instruction, like what kind of task you want the model to do. For example, it's please explain the decision making by the driver, or please predict the next control signal.
Thank you.
Thanks.
All right. Thank you very much. Let's thank the speaker again. So that was paper number 3. Now we're coming to paper number 1. I hope you're keeping up. This paper is called GOAT, Go to Anything.
All right. Hi, everyone. My name is Mukul. And in this paper, we present the Go-to-Anything agent, the first lifelong learning agent capable of multitask navigation to objects, however they are specified. GOAT is the first universal navigation system that can navigate to any object specified as an image, language, or a category in completely unseen environments without requiring pre-computed maps or locations of objects. Here you can see it look for a sync image, language describing a teddy bear, and language describing a cup in the end. Let's first discuss the problem we tackle. Imagine dropping a robot in an unknown home and asking it to tidy up. What makes this challenging is that the robot needs to explore the environment, detect and localize relevant objects, remember object locations, and navigate to pick or place objects. In any realistic deployment setting, a general navigation primitive should be multimodal and it should be lifelong to be able to remember object locations. Now let's look at an overview of our system. As the agent moves through the scene, the perception system detects object instances and localizes them into a top-down segmentation and instance map. This memory allows the agent to localize and navigate to any previously seen object instances. Next, a global policy takes this lifelong memory and a language, image, or category goal and outputs a long-term goal for which the local policy outputs actions. Talking about the perception system, it takes as input the current RGB, depth and pose, and uses off-the-shelf models to segment instances and estimate depth to fill in holes for reflective objects. These detections are then projected and added to a top-down map of the scene, along with their images for the instance memory. This instance memory clusters object detections and object across in time into instances using their location in the top-down map and their category, and saves the images in which it has been viewed. When a new goal is specified to the agent, first it searches the object instance memory to see if the goal has already been observed. If an instance is found, its location in the top-down map is used as a long-term point nav goal. Otherwise, the global policy outputs a frontier-based exploration goal. The local policy then simply uses the fast marching method to compute actions to move towards the long-term goal. Coming to the results, we evaluate GOAT in the wild in 9 unseen homes and compare 4 methods for 10 trajectories per home for a total of 90 hours of experiments across 200 different image, language, or category goal instances. Let's look at a full episode of the GOAT policy in an unseen home. Here we show the first-person robot observation, a third-person view, the current goal, which is an image of the kitchen sink, and the semantic map that is being built. As the agent explores the scene, observed objects are added to the instance memory and the map. Every new instance seen is matched against the goal image. Once the sink has been seen and correctly matched, the agent navigates to it directly. For the next goal of the teddy bear description, the agent first searches the instance memory for existing matches and begins exploring when none are found. For the next goal, which is an image of the couch, the agent finds a match against previously observed instances and navigates directly to it. Following this procedure, GOAT is able to successfully reach all goals specified in this episode. And here we show the GOAT agent operating in a different unseen home. We compare approaches in terms of success rate per goal within 300 robot actions and efficiency through SPL. GOAT reaches 83% success rate and 0.64 SPL. When removing the persistent memory or instance-specific information or using clip features of entire images like prior work, success rates and SPL drop significantly. Additionally, GOAT performance improves with experience in the environment, going from a 60% success rate at the first goal to a 90% success rate for goals 5 to 10 after thorough exploration. In the same scene, with the same goals, we see that our system performs more accurate matching than baselines, and the use of instance memory allows effective localization of previously observed objects, whereas baselines with no memory can repeatedly explore the same area. This leads to robust and efficient navigation in the real world. The GOAT policy can be easily deployed to downstream tasks like pick and place and social navigation. Here is a GOAT policy searching for a bed, then a specific teddy bear and bringing it back to the bed. Here you can see the GOAT policy plan around a person to reach the refrigerator, then remove the previous location of the person from the map after the person is moved, and successfully follow the person while updating their location. Additionally, GOAT can easily be deployed on many different robotic platforms. In summary, we present the first universal navigation system able to navigate to any multimodal goal specification in a lifelog setting in completely unseen environments and can be readily deployed for tasks like pick and place and social navigation. Thank you.
Thank you. Questions? Here in the front, the blue cube.
Hi, great presentation. I was wondering how you deal with, I was wondering how you deal with objects that move occasionally, like chairs, or like if you buy a new couch and switch out your old couch or something like that.
So if the objects are moved during the map creation part, then it won't work. So you will have to reinitialize the agent with an empty memory. But yeah, we are assuming that scenes are static when all of these episodes have been provided at once. But if you happen to change any of the scene configuration, you can then reinitialize the memory and then the agent can take the first few episodes to be able to get familiar with the environment and then be able to leverage that for further goal specifications.
The orange cube in the back.
Hi, over here. Thanks a lot for the talk. I had one question about the memory efficiency that you get, because I would imagine when you have, let's say, larger houses with like multiple rooms, multiple objects and all that, it would be like scaling very, like at an n square level or something like that.
So we're not maintaining a 3D memory of any way. It's just a top-down segmentation and instance map. So the size of the memory matrix would be just directly proportional to the number of objects that you have. So if it's like 300 cross 300 top-down map, then the number of channels would then represent the number of objects. But it does not blow out of proportion as long as you have a reasonable number of objects in the scene.
Thank you.
We might move on in the interest of time. Sorry, please just go to the poster afterwards. Let's thank the speaker again.
Thanks.
Hi, so talk number 5 is hierarchical open vocabulary 3D scene graph for language grounded robot navigation. Please welcome the speaker.
Hello, my name is Chen Guang. Today we present hierarchical open vocabulary 3D scene graphs for language grounded robot navigation. Current dense visual language mapping, such as VR maps and concept fusion, struggle to scale to larger scenes due to their large storage overhead. One way to tackle this challenge is to use 3D scene graphs such as Hydra, but it only supports closed-set semantics. A recent work concept graph proposed to integrate open vocabulary features into a 3D relationship-based scene graph, but they do not explicitly model the hierarchical semantics. So we propose HOFSG for open vocabulary mapping of large-scale environments using 3D scene graph hierarchies. The creation of HOFSG involves 2 stages, namely creating a segment-level open vocabulary map and creating a hierarchical scene graph. In the first stage, the pipeline assumed the consumption of RGBD sequence with autometry. And for every RGB image, we use SAM to generate class-agnostic masks. And for each mask, we encode the global image, the subregion image, embedding, which are fused with weighted sum. And this is used to update the mask region in the global pointwise, update the global pointwise feature in the mask region. And at the same time, we back project these masks to perform the per frame segment, which are incrementally merged sequentially. And then for every fully merged segment, we extract all the global pointwise feature in it and then apply dbScan clustering. And then we look at the major cluster and select the feature closest to the cluster mean as the segment's feature. In this way, we can create a segment-level open vocabulary map. In the second stage, we need to explicitly model the floors, the rooms, and objects as nodes in the hierarchical scene graph and encode them with open vocabulary model or like embedding. At the same time, we also construct a navigational graph spanning across different floors. To obtain the floor node, we find the peaks of the height histogram of all the points in the building and then filter them to get a list of height ranges which can be used to segment the floor. Second, to derive the room node, we compute the 2D histogram of the floor point cloud in the bird's eye view and apply the watershed algorithm to generate the region mask. And then, to generate the navigational graph, we compute the Voronoi graph of every floor's free space and connect these Voronoi graph with a camera post lying on stairs. One highlight of the HOF-SG is its way of computing the room embedding. Given the camera views, room regions of the floor, we can assign the camera views to the room region that they belong to and compute their clip embeddings. And then we can apply k-means cluster to extract the k-representative feature regarding this room. During the query, the user can provide a list of clip-encoded room categories, which can be used to compute the cosine similarity between the room feature and the category feature. And later, we can use argmax to derive k-opinions of what type of room it is. And later, we can use majority voting or argmax to determine really the room type decision. Okay, to enable the language-grounded navigation with HOF-SG, we break down a lengthy instruction such as find the toilet in the bathroom on floor 2 with large language model into 3 concepts, namely floor, room, and object. And then we can sequentially query the graph at different levels and then progressively narrow down the search space. And after getting the target, we can use the action graph to plan the path from anywhere in the building to the target. Here are some visualization of the scene graph we built in the Habitat 3D semantic dataset. So we evaluate the open vocabulary 3D semantic segmentation performance of our methods, and here are some qualitative results on replica. We also evaluate the language-grounded navigation, like navigating to go with language. And here are some example trials showing that the robot is able to navigate across different floors. Okay, in the real-world testing of the language-grounded navigation tasks, HOF-SG enables the querying at floors, rooms, and object levels, and this actually facilitates the constraint search and allow for a more detailed target specification instead of simply prompting an object category. Okay, thank you for your attention. For more information, please come to our website, hofsg.github.io, or come to our poster. We provide the code. Yeah. Thank you.
Any questions for the speaker?
Yes, thank you. This is interesting. I'm curious, how do you think about tracking changes to the environment? Because I would imagine that that's happening. Do you have to rescan entirely, or is there a way to annotate things as they move?
Yeah, I think this is a very smart and very good question. So far the community is focusing on the static environment, including the gold paper just now, and also our work. So we actually have an assumption that the world is not changing, which is not making sense. So I think it will be a really good direction to work on in the next, for example, like the dynamic scene, like object get moved from place to place, or something like that. Like how do we update our knowledge about the environment on the fly? This is a very impressive problem to solve.
Okay, thank you, because I think there's a lot of people as they get older, they're putting things down and they forget where they put them. So it'd be very helpful to have that when they have to to find my glasses and things like that. So thank you.
Yeah, thank you.
We can have one quick question.
Okay. Hi, thanks for a nice talk. My question is a bit similar to the previous question, but relates to whether you can build a graph online. So when you explore a new unseen environment, you could also imagine like in some kind of disaster scene or something like that. So you want to use semantic information for exploration. Can you build a graph online, or do you need to first collect like a large data set of point cloud and then have to build the graph offline, I mean?
Yeah, I think making it online is really a difficult task. For now, our method work offline, and we expect the input of our RGB sequence, which is pre-recorded, and then we kind of compute the odometry of these camera poses, right? And then we build up offline. I think there are several bottlenecks that prevent the method really work online. For example, like SAM, clip, this kind of methods, some of them are working quite slow. And the second thing is the merging of the object over time, right? Because after maybe several hundred frames, your objects storing in the whole scene is already maybe at the 1,000 level, and the merging of it, you need to match the current observation to every one of them. This is really a bottleneck. Yeah.
Thank you.
Thank you.
Okay. Thank you, everyone. Next presentation is Screw Mimic.
Hello. Just a heads up, this paper is not about navigation, but manipulation. I'm Arpit, and I'm glad to present Screw Mimic, a bimanual imitation method from human videos. Manipulation in human environments often requires coordinating the motion of two arms. However, such bimanual actions are challenging due to the higher dimensional action space and a need for synchronizing both arms. One way to teach robots bimanual actions is to teleoperate the robot to collect demonstrations. However, it is difficult to collect demonstrations for bimanual tasks. An easier and more scalable approach is to directly learn from human videos, but this is challenging as well due to the differences in morphology and the difficulty to cleanly parse the video to obtain robot actions. So how can we facilitate bimanual manipulation in robots? Our key insight is that several bimanual tasks can be represented as screw motions with a simple 1 degree of freedom screw axis as shown here. This virtual joint constrains the motion in a way that either matches an existing physical constraint in the environment or just facilitates the manipulation. This insight helps in several ways. First, in perception, the screw axis representation helps to cleanly parse human demonstrations. And secondly, in exploration, it provides a more efficient action space. Thus, we introduce Screw Mimic, a novel method that leverages this insight for one-shot visual imitation learning of bimanual manipulation from a single human demonstration. Screw Mimic works as follows. It first takes a single human video as input. It then extracts the contact locations for both the hands. Screw Mimic then uses an off-the-shelf hand tracker to obtain the trajectories of the human hands and infers the screw axis by analyzing the relative motions between them. Based on this information, Screw Mimic extracts a screw action, sigma, consisting of the left and right hand contact locations, the screw axis, and a possible additional left hand trajectory. But we want a solution to generalize the perceived screw action to novel object instances and poses. To achieve that, in the second step of Screw Mimic, we train a model that predicts screw action from an object's point cloud. Due to the noises in the human hand tracker and the differences in morphology, the direct robot execution of the observed screw action may fail. So we introduce a screw action policy fine-tuning module. For a new trial, the robot obtains an initial screw action and executes it. If the initial strategy fails, Screw Mimic implements an iterative refinement in the screw action space with a cross-entropy method. In each episode, a screw axis is sampled from a distribution, and the corresponding trajectory is executed and ranked based on a self-generated reward. This reward considers episode length determined by grasp loss or reaching a force threshold. The fine-tuning stage runs for a maximum of 5 epochs with 5 episodes each and stops whenever a success is achieved. Screw Mimic then extracts the screw action from the successful strategy. The new successful screw action is further used to improve the prediction model as shown. We evaluate Screw Mimic on 6 real-world bimanual tasks where we want to assess if a single human demonstration is enough for Screw Mimic to achieve success. Here you can see the result for the stirring task. The robot first executes the initial strategy based on the prediction from the screw action from the prediction model. Since that fails, it employs the screw action fine-tuning stage. The robot explores by sampling different screw actions from a sampling distribution and updating it after each epoch. As the epochs progress, the sampled screw action brings the robot closer to achieving success, ultimately attaining it. Screw Mimic can achieve success in all bimanual manipulation tasks by watching a single human demonstration and subsequently performing real-world fine-tuning. Please refer to our website for more videos. We also explore if the screw action prediction model improves from robot interactions to reduce the need for new explorations. The picture shows prediction from a first model, M1 in red, trained with data from human video, compared to the predictions from a second model, M2 in green, trained with the refined screw action after exploration. The results shown here are for novel object configurations. The second model provides more accurate predictions and generalizes better to unseen poses. We also evaluate the generalization of screw mimic to new objects. Depending on if the differences are larger, as in this previously unseen bottle, or smaller, as in this new roll, the amount of exploration for a new object may be more or less, but in any case, screw mimic is able to manipulate these completely new objects. Moreover, after interacting with them and retraining, it succeeds almost zero shot for new configurations of those objects. While in our experiments, we focused on the relative motion between the hands and did not consider the absolute motions of both, our method is general enough to cover any absolute motion. Here we show an example of the stir task with a left-hand trajectory. Because the screw action focuses on the relative axis between the hands, it generalizes to any single hand absolute motion. In summary, screw mimic shows how various bimanual actions can be represented by a simple 1 degree of freedom screw joint, how the screw action representation helps in a more accurate human demonstration interpretation and efficient exploration for the robot, and finally, how screw mimic can continually expand its manipulation capabilities to new objects. Thank you. Please visit our poster session.
Any questions for?
Success and failure.
Yeah, so in this case, in the real world trials, the human determines the success and failure. But I think there is we can use a VLM to detect success and failure in this case because it's pretty binary.
Did you do anything with forces or moments, or is it purely kinematic? Is it purely geometry, or do you handle, is there forces and moments considered?
Do you mean we use forces to evaluate the reward of how good an episode is, an interaction is, meaning that if there's a force threshold reached, that means that it's doing something that's not supposed to be done. And so we rank that episode, we give that episode a lesser reward. Is that what your question was?
But you don't plan, for example, to have a specific force and moment applied, like if you're twisting?
Oh, right. Yeah, no, we don't, this is only position control. We don't do force control in this.
Okay, thank you.
Okay, thank you, Arpit. I think the rest of the questions we can do in the poster session.
Yeah. Thank you.
Next, paper number 7, NAVED, video-based VLM plans the next step for vision and language navigation.
Okay. Hello, everyone. It's my honor to present our recent work titled NAVED, Vision-based Vision Language Model plans the next step for vision and language navigation. Vision and language navigation requires the robots to navigate in diverse and unseen environments following free-form instructions. Compared to existing VLM method, NAVED stands out in 2 key aspects. Firstly, NAVED is the first video-based vision language action navigation agent. It leverages the power of foundation vision language models to extend VLM to real-world applications. NAVED plans the next step action in an end-to-end manner. By using pre-trained large models and co-tuning with web-based data, we enable the transfer of general-purpose knowledge to our VLM agent, significantly improving its generalization ability. Okay. Secondly, NAVED navigates in a human-like manner, relying solely on real-time video streams from a monocular camera, without need for maps, odometers, or depth input. Encoding historical observations as video provides a more informative and adaptive context than previous method. Without need for maps, odometers, or depth input, NAVID alleviates generalization challenges caused by odometer noise and discrepancies in depth perception and navigation maps, making it easy to deploy. NAVID takes in 3 types of input: the historical sequence, the current frame, and the instruction. Both the historical video and the current frame are processed by the observation encoder to extract instruction queried and instruction agnostic visual tokens. The instructions are processed by BERT to extract textual tokens. Furthermore, we use special tokens to distinguish different types of data. This allows the model to learn from multiple modalities at the same time, helping it avoid overfitting to the navigation task. Finally, NAVID generates 4 types of action. The robot keeps executing the generated actions until it receives a stop. Our training data consists of 2 parts. For the navigation data, we use the VLNCE simulator on R2R training set. We gather 2 types of navigation data. Action planning data involves predicting the next action based on historical videos, current observations, and given instructions. Instruction reasoning data involves generating instructions from a complete observation video. We hope this data helps the model learn to align navigation videos with instructions. The web-based data includes text, image, and video QA data. Furthermore, since the model needs to understand noisy trajectories during real-world navigation, we use the DAGA method to collect an additional noisy navigation data. Altogether, we accumulate 1.2 million training data. We begin by experiments in the simulator. In the R2R cross-split test, NAVID performs on par with the sort method. However, NAVID only relies on video. In the R-cross-R cross-dataset test, which involves more complex instructions, our method achieves the best performance, which shows our strong generalization ability. Finally, we test NAVID performance in real-world scenarios, selecting a variety of environments. Compared to existing baselines, NAVID shows significant generalization improvement in real-world settings. Here are some examples. In the first example, you can see that NAVID effectively distinguished 2 different target objects. The white box does not appear in the training set. NAVID can still identify it. We also test NAVID in outdoor scenes, which are different in style from the training data. NAVID can still understand and execute the instructions. Furthermore, we give NAVID more challenging tasks that include multiple target points and actions. NAVID can effectively understand and follow these longer instructions, especially in recognizing objects like glass walls and glass doors. Okay, that's all. Thanks for attention. For the discussion, please join us at the poster session. Yeah.
I have a question about how long the video history are you keeping? Like given like 100 row of seats, and I say at the 50 row turn left, can the robot remember how many I have passed?
Well, yes, we record the whole video to the input to our models, and we use 4 tokens for each frame. So in our result, and I think the NAVID can remember his previous actions. Yeah.
And I want to know if all these seats are identical, how can you take the difference between these rows? Can you counter the identical thing you have seen?
Wow, yeah. I think this is a good question. And I think one feasible solution is to drop out some historical observations. Yeah, and I think I will do this in the future work. Thank you.
We'll have one last question.
Hi. I have a question. So nice work, by the way. And then how do you deal with visual corruption? For example, when you are in the outdoor, then there's some blur, visual corruptions. Then how can you deal with that?
Wow, I think this is the charm of the large visual language models, yes. And this model is pre-trained on billions of images. So the generalization abilities, I think, can be verified, yeah.
Let's thank the speaker.
Okay, thank you.
The final paper for the session is RACER, Epistemic Risk-Sensitive RL Enables Fast Driving with Fewer Crashes.
Hey everyone, my name is Kyle, and I'll be talking about our work on training risk-sensitive RL policies in the real world. So when you're training an agent in the real world, you need to consider a lot of different factors from when you're training in sim. For one, irrecoverable failures during training interrupt the learning process, they require human intervention, and they can cause a lot of damage. So the central problem is, of course, how do you know what a risky state looks like if you've never actually seen one before? We're looking at, in this paper, the autonomous off-road driving setting, where a fast policy might be right at the edge of the set of safe policies. And so here, the safe policies are in green, unsafe policies are in red. And we really want to get right towards the edge of that. Of course, you can be safe by being extremely conservative, like the blue dot here, but this isn't going to be very performant. If we try to improve the blue policy in a completely risk-neutral way, we end up with an unsafe policy. So instead, we want to start with a conservative policy and slowly and incrementally approach that border. This is just sort of an analogously to that last figure that you saw. We start by driving very slowly, and we start by learning a policy that is able to do basic navigation behaviors at low speeds. And then eventually, after training sort of converges, we end up with a policy that's able to perform very agile driving behaviors. So to accomplish this, we start by modeling the critic as a categorical distribution over returns, as in distributional RL. We apply the CVAR risk metric, which truncates the distribution like this and takes the expectation of this worst case distribution. This is risk averse, so it wants to avoid uncertain states. Apparently I got the slide timing wrong. Here we go. So we additionally act risk-averse to epistemic uncertainty by using an ensemble of critics, so not just one. And then when they disagree, the CVAR will penalize that further. So naturally, this is sort of pessimistic in this sense, right? The CVAR of a mixture distribution, when you take all of these things and combine them, is always going to be less than the average CVAR of the individual members. We call this difference the CVAR gap, and we sort of quantify it a little bit in some theoretical sense. So this difference right here is, that's a CVAR gap. It's always going to be positive, which means that you're always going to be pessimistic when your ensemble members disagree. And we also show some theory that it correlates very well with this thing that we call the tail Earth movers distance, which is just a measure of disagreement on the sort of tail distribution of the different ensemble members. And we show that this bound in practice is fairly tight. So we test our algorithm in a real-world setting where a robot is driving a course defined by GPS checkpoints. And we see that we get good performance in outdoor driving settings, especially at convergence, while learning entirely online completely from scratch, so no sim. We get high-speed driving, and we reduce the catastrophic failures during the training process. We compare to a few different safe RL methods, notably that a lot of these other existing methods are intended to improve the safety of the converged policy, but we're able to, using this epistemic uncertainty quantification, act much more safely during the training process. We use this sim I developed that's maybe a crude analog of the real world, but it still has the basic features, which is that trying to turn very aggressively causes a rollover. And you can see that if you drive slowly or if you smoothly turn, you get less of that rollover behavior. Looking at the underlying ensemble members, we see that in the regular case, the CVAR is very sorry, here the CVAR is in blue and the mean is in red. The CVAR is very close to the red for a sort of unimodal distribution, but then when we have a low probability outlier event, the CVAR sort of takes that into account and upweights it, and we get much more conservative behavior in those types of states. We can actually also, during training, look at the ensemble members themselves. This is in a near failure state, and we see that this red ensemble member is actually able to quantify that, hey, this is a risky state, while the other ensemble members haven't quite learned that yet. And because CVAR is, in this ensemble case, pessimistic to disagreement, it's going to upweight that red ensemble member and focus on its predictions. And of course, as training converges, all of these ensemble members will start to look the same. We also compare it sort of sweeping across the conservatism level, the amount of the tail distribution that you use, and we find that we get a pretty good trade-off between safety and between performance. Notably, we get very good safety with sort of default setting, but you can trade that off a little bit as we go. Yeah, and there are a couple other baselines here that maybe it's best not to talk about right now because it's a little cluttered, but please come to the poster and please feel free to ask any questions. Thank you.
Hello?
Orange in the front?
Yeah.
All right.
Next up. I'm wondering, so this is a kind of, as you said, it's a trade-off between how safe it is versus how performance you can get. And I'm wondering, is there a knob in your method that can like continuously tune between the safety and the performance of the final algorithm? And, and also a follow-up on that is, what's your idea on like how this trade-off is close to the Pareto curve, the optimal potential Pareto curve? Yeah.
Yes. So I guess as I wish I still had that figure up, but as we saw in that last figure, we don't. I mean, in the extreme conservatism case, we do sort of start to reduce behavior, but actually. Adding a little bit of this conservatism actually improved the final result, or improved the final performance, which is a little bit counterintuitive, and I think that's a little bit down to how online RL in this sort of sense works. I think having a lot of failures early in training can really hamper the learning process. So I think we're actually improving over the risk-neutral sense in performance even, but there is that conservatism knob that you can trade off, which is basically just in CVAR, you take a tail distribution. It's just how large that tail distribution is. And sorry, I already forgot your second question. It was how close you think it is to Pareto, right?
Right.
I think it's fairly close to at least the Pareto frontier that we can get with existing methods, although I'm not convinced that existing methods are, perfectly saturating what a true expert could do. Yeah.
Right? Any last question? Oh,
so thanks for a very cool talk. Something that I wanted to clarify is it looks like your simulator is deterministic, right? Like there's no intrinsic randomness. You're not like adding random noise to the dynamics.
So the robot in the simulator is actually blind to the terrain noise. So in that sense, it is partially observed or equivalently stochastic from the robot's perspective.
Right, so you're not using camera image.
So yeah, in that case, we're not using the camera image, yeah.
Got it. So I was going to say that it seems like if you don't have noise, then it might be possible to have a policy that is as aggressive and as agile as possible while having 0% failures, given that you're missing information and you're modeling as noise. How do you translate that into a meaningful way to deploy this on a physical system, given that if you fail, potentially your real robot will break? What is an appropriate, how do you find an appropriate alpha or an appropriate level of conservativeness so that this is actually a meaningful trade-off?
Yes, so, okay, two things there. The first one was sort of regarding stochasticity, I guess, in this case, right? And I'm forgetting what my point was. Sorry, my train of thought just ran out. But in the real world, when we do sort of set this up, it's sort of important to note that this won't, and it sort of is fundamentally intractable to avoid all failures without, or without some additional injected knowledge, and this sort of operates without injecting any domain knowledge. I think you do have to inject some sort of domain knowledge if you want to get perfect safety. Although I think, again, with these sort of aggressive driving type settings, you're never going to get perfect safety. We're sort of just aiming for getting better safety during learning. Oh yeah, and the other thing was this sort of stochasticity argument. I think that is true at convergence, where if you have a deterministic environment, you're going to be able to do that. But if you really care about during training being safer, that isn't going to help you, right? Because you fundamentally have not learned all that there is to learn. Thank you.
That ends the session on navigation. Thank you for all the speakers once again.